conference for stand-in of Bernd Bischoten, who is regretting it a bit that he's not here himself, but I'm very happy to take over for him. The talk I will be giving today has the title Towards Ballistic Spin Transport in Bilayer graphene. At the bottom you see two schematics of typical spin transport devices, where you have a spin hosting material, here graphene, and four contacts, two to the left and two to the right. The inner two contacts are ferromagnetic and separated by an insulator from the hosting material. Now the goal I want to present here is to build such a device which shows ballistic spin transport and where we are able to turn on and off the spin manipulation by an external electric field. In 2017, ICQMT also suggested to use bilayer graphene instead of graphene. Why bilayer graphene? Intrinsically, it has a rather weak spin orbit coupling of about 60 to 70 microelectron volts and is a zero band gap semi-metal. It's not working. Yeah, no, it's working again. Perfect, thank you. But if you apply in such a structure a perpendicular displacement field, you break the symmetry between the lower and the upper layer, and you can open up a band gap. The size of the band gap can be tuned up to a few hundred millielectron volts by the strength of the applied displacement field. Now, what's even more important here is that at small momentum around K and K prime, these bands live on different layers. Here in this configuration, the valence band in red is hosted by the A1 atomic orbitals of the lower layer, while the conduction band in blue is hosted by the B2 atomic orbitals of the upper layer. Now, why is it interesting that each of these bands live in a separate layer of the bilayer graphene? That is, if we bring bilayer graphene into close contact with a strong spin orbit coupling material, for example, tungsten disulfide, we will have a proximal and a remote layer. And only the proximal layer will experience hybridization. So we have one layer which has strong spin orbit coupling due to the proximity, and one layer without strong spin orbit coupling because it's just too far away for hybridization effects. Due to this hybridization, there will also be some internal dipole forming, and we have an internal electric field. So it's expected to see a gap even without applying any kind of external electric field. Now here's where this layer tuning from before plays its role. The conduction band in this configuration is entirely hosted by the proximal layer, so it shows strong spin orbit coupling. The conduction band is hosted by the remote layer, so it only shows the intrinsically weak spin orbit coupling. If we now start to apply an external electric field, we can either apply it in the same direction to the internal field or in opposite direction. Going in the same direction, we move here to the right. We just increase the band gap. However, if we turn the electric field around, going to the left, at some value where the external electric field becomes larger than the internal electric field, we start to flip around which band is hosted by which layer. Now here, the valence band is hosted by the remote layer. If you keep your Fermi level all the time fixed in the valence band, you can switch by the sign of the external electric field between strong spin orbit coupling and weak spin orbit coupling. This is why ICQMT et al. Suggested to use bilayer graphene here in these kind of devices instead of single layer graphene. The first evidence for this layer tuning has been reported on in 2019 by Island and al. They characterized bilayer graphene on monolayer tungsten diselenide encapsulated in HBN with graphitic bottom and top gate. They used not transport penetration but penetration field capacitance measurements to characterize this device. The bright yellow areas are an indication of the gap opening, the blue areas are inside of the bands. Now highlighted with these white arrows, you see this point symmetrical feature, which is associated with the Fermi level being pushed through both split bands. And you can see that this feature either shows up in the conduction or in the valence band, depending on the sign of the applied displacement field. So really proving this layer tunability. They also extracted spin orbit coupling strengths of 1.7 millielectron volt. Another paper from the same year by Wang et al. Found 2.2 millielectron volt. Both values agree reasonably well with each other, and they are orders of magnitude larger than the internal value of bilayer graphene. So we really have now an on and an off state for our spin orbit coupling. In order to build ballistic spin transport devices, there are other requirements which needs to be fulfilled. The bilayer graphene needs to show high electromobility and long spin lifetimes. We need an SO material which allows us to keep the high mobility of the bilayer graphene. We need a gating technology which allows us to homogeneously tune the gap over the whole device. And we need, in the end, some spin injection and detection contacts which allow for ballistic spin injection here. To During the course of this talk, I will address different materials here, showing that CVD-grown bilayer graphene is actually an ideal candidate for these kind of devices. I will show you that graphite gates are must-have for homogeneous bandgap tuning, and I will show that tungsten dicynate is an ideal candidate for its own material. Let's start with the CVD-grown bilayer graphene. In 2017, Michael Schmitz from our group reported here on a device based on CVD-grown bilayer graphene from our group. We grow graphene on copper foil. It starts out as a single layer graphene, and in the middle then you will see bilayer graphene as well after some time. This bilayer graphene can be picked up from the copper foil using an HBN stamp after the foil has been left to oxidize. Then Michael encapsulated this in HBN, etched every single layer part away, and just kept this hall bar shaped bilayer graphene HBN heterostructure. He placed an additional HBN on top, so he also included a gold top gate here. Using this gold top gate and the silicon bottom gate, he then started to characterize his device. Here on the top left, you see a typical resistance measurement as a function of top and bottom gate voltage for low temperatures. And this diagonal feature is very typical for bilayer graphene. The white dashed line denotes the charge neutrality point. Going from here into the edges, the corners, we increase the displacement field. So the increasing width is actually already an indication that we start to increase the gap. Perpendicular to this white dashed line, we can tune the Fermi level by this effective gating potential Vg. He also measured the XY conductance as a function of bottom gate voltage for different magnetic fields, and saw this nice Landau-Fein immersion, while large filling factors consisting down to low magnetic field, showing the high quality of this device. In the next step, he measured the conductance as a function of charge carrier density for zero applied displacement field for different temperatures as well. And you see that we have this kind of plateau here, which we indicate to a shifting from diffusive to ballistic transport here. The important thing is that we are able to fit these traces to extract the mobility values. And you see that especially for electrons on the, you see quite high mobility values. At 2K, we get above 150,000 square centimeter per volt seconds. At room temperatures, we still have 40,000. So we are checking already a lot of the boxes on the requirements I had. We are having high electromobility, we have also ballistic transport, and we have a large electromean free path of above 2 micrometers. These measurements, however, also show that you really need low temperatures to really fully utilize the potential of bilayer graphene. How does spin transport in bilayer graphene look like? In 2014, Mark Drögeler from our group reported on experiments in this inverted spin vibe structures using exfoliated bilayer graphene. Inverted means here he's picking up graphene, or bilayer graphene in this case, and placing this onto some predefined contacts. The HBN then protects the graphene and the contacts from any kind of liquid solvents, allowing for high quality devices. Mark found here values of 1 nanosecond spin lifetime. Other experiments in literature are these spin drift using exfoliated bilayer graphene. They found 3 nanoseconds and 7.7 micrometer spin diffusion length. There are also experiments with spin manipulations. Here are the spin interconnects in CVD-grown bilayer graphene. They found 2 micrometers and 250 picoseconds. There are many more publications on spin transport in bilayer graphene. I want to focus now on a recent work from our own group, where we are using these inverted spin valve structures with CVD-grown bilayer graphene. Here, Timo Biswanger from our group designed a new fabrication method. Starting out similar to Michael Schmitz with CVD-grown bilayer graphene on copper foil, he was able to pick it up with his HBN stamp, transferred it into silicon oxide, and etched this into a hall bar. And now comes this new step he introduced. He designed this PDMS droplet with PC foil on top. The PC foil has a high adhesion, so he was able to pick up this pre-etched structure and now place it also on some predefined contacts, and afterwards fuse the PC foil down to the silicon oxide. This method has several advantages. For one, it is fully dry. Again, the bilayer graphene never sees any kind of liquid solvents. Then he was able to really reliably pick up these pre-etched structures. The most important advantage is that due to the dome shape of this droplet, he's able to locally press down the CVD-grown bilayer graphene onto the contacts, enabling good contact between the bilayer graphene and the cobalt aluminum oxide. Let's take a look at some measurements. Timo measured at room temperatures in a diffusive transport regime, and as he had only one gap, he was not able to open up a gap. Here on the left side, you see again resistance measurement is a function of gate voltage, and you see this typical Dirac peak. The charge neutrality point of this peak is very close to zero applied gating voltage. So we really have small residual doping, meaning the HBN really protected our bilateral field. Here in the middle, you see these Hanle curve measurements for parallel and antiparallel spin contact configuration. Let me explain to you how these kind of measurements are done. Here again a schematic of the spin transport device. We have the two left contacts where we apply current, the two right where we measure non-local voltage. For zero applied out-of-plane magnetic field and both injection and detection contacts being magnetized in the same direction, we get here a peak. If we start to flip around the detection contact, we of course get here a minimum. Now if we apply an out-of-plane magnetic field, the spin starts to precess and we break away from this minimum and maximum, and we get essentially this curve here I'm showing in the middle. The width of this peak does depend on the inverse of the spin lifetime, meaning the sharper the peak, the higher the spin lifetime. Timo found values of 5 nanoseconds and 25 micrometers, which is of about 24,000 square centimeter per volt seconds. In the next step, he took a look at how he can tune the spin diffusion lengths and spin voltage will drop. If you start to increase the source drain voltage until a point C, where the energy difference between source and drain becomes equal to the band gap we introduced with the displacement field, then current can start flowing again beyond this point C. This also means that we can directly extract the gap value from the difference of point A to point C on the y-axis. Now for graphite-gated bilayer graphene, we find this nice singular diamond shape here, showing great tuning of the Fermi level, and as the area inside of this diamond is very homogeneous, it also shows that the gap is very clean. How does it look like for gold-gated bilayer graphene? We clearly do not have this singular diamond anymore. Instead, we have a lot of smaller diamonds slightly shifted against each other. The gap value we can extract here, black dashed line, is much smaller than what you would expect, white dashed line. What's even more of a problem for our spin transport devices now is this small shift of the diamonds relative to each other. This means we have a variation in doping and tuning across our whole device, making gold not sufficient for a homogeneous tuning of the band gap across the complete device. So we really need graphite gates here. Okay, I've addressed the spin hosting material, I've addressed the gate material, now let's address the SO material. Here we find that measurement of the 2D line widths of the graphene placed on different substrates. We are interested now in a substrate with strong spin-orbit coupling, so we have the band gap. I only need to address now if we have spin-orbit coupling. In charge transfer experiments, this is usually done by taking a look how weak localization is converted into weak anti-localization. Both are interference effects due to a path forming a closed loop, and it's time reversed. They emerge if you apply a magnetic field, which adds a phase and breaks your interference effects. Then weak localization starts to show as a dip in the correction to your conductivity at zero magnetic field, and weak anti-localization as a peak. These kind of measurements have been done a lot for graphene and tungsten diselenate. Here, for example, Wang et al. In 2015 measured the change in conductance as a function of applied out-of-plane magnetic field for different gate voltages. And you see the peak here in the middle is very narrow, so it's easy. Let's take a look at our measurement. Here we measured the change in conductance with applied out-of-plane magnetic field for different gate voltages, and we made sure to check both sides of the band gap. Now you might start to wonder, why do we expect to see some kind of these weak localization effects even though the mobility is so high? The answer is we use the trick in our device. The bottom gate is much broader than our top gate, so it tunes our leads. As for negative displacement field, the bottom gate being also negative, our leads are p-doped. With the top gate, we can truly choose how our doping is. For negative values, we are also p-doped underneath the top gate. For positive values, we are n-doped. In this case, we get p-n junctions at the edges of our top gate, forming a cavity, and thus are able to observe weak anti-localization. This part here is a zoom in here, and you start to see now clearly the peak, and if I average over all these traces, I get this nice weak anti-localization peak here in blue. Now, slowly shifting the displacement field to positive values, I destroy this weak anti-localization effect simply by destroying the cavity. Okay, we have high mobility, we have a large mean free path, we have a great tuning of the band gap, and I have shown you clear evidence of spin-orbit coupling. The next step we are currently still working on is to build such a heterostructure for spin transport devices, but this is not something I can show you yet. Let me conclude my talk. I've shown you that CVD ground bilayer graphene shows high electromobility and long spin lifetimes, being an ideal candidate for this tunable spin hosting material. Also, tungsten dicent is an ideal candidate for SO materials, and hopefully I've shown you that graphite gates are a must-have for homogeneous bandgap tuning. The only thing I was not able to address are the spin injection detection contacts. Here we are currently working on an approach where we want to incorporate into our heterostructure ferromagnetic 2D materials. This is also something we're still working on. With this, I'm at the end of my talk. I would like to acknowledge and thank all these people, either by working together on the measurements and providing data, or by material, or also by very fruitful theory discussions. And I would like to thank you for your attention.
Thank you so much. Do you have any questions?
Thanks for a very interesting talk, and I have two questions. So the first thing is like as we know, like TMD, WF2, there's a lot of defect. It doesn't matter that how you grow, but it still has a defect. The question would be that what's the effect of the defect on, like gap formation and spin transport?
Okay.
And second question is because recently
with the chrome germanium telluride, I think. We haven't tested anything else. It's very much at the beginning. We recently got also a glove box to start to test out material not stable in air. And we have no feeling yet which material is ideal. So I guess we will test these as well over time. But these ferromagnetic contacts are still very much at the start. Just recently we have students started to work on this. So the other question was the defects in tungsten dicynate, right? At the moment we are still using exfoliated tungsten dicynate as a material, which
So coming back to where we started with graphene, and graphene is known for nanoelectronics because of high achievable mobility, because of its linear dispersion, and gate tunability and ballistic transport. From the point of spintronics, these carbon atoms have very low spin orbit coupling and no hyperfine spin interaction, which means that it's theoretically very long spin diffusion length is possible with a very high spin lifetime. And this has propelled research interest in exploring graphene for spintronics. For example, this is the first seminal work by Tombras et al. In 2007, where they have used an exfoliated sheet of graphene, and these are cobalt electrodes, and they tried to transport spin currents by injecting electric currents from this cobalt electrode into graphene and detecting with another electrode, similar electrode placed at beyond 2 micrometers distance. And if we compare this device with the same group's device on a metal spin valve, one could clearly see that a lot of improvement is made, and this spin transport achieved in this device is achieved at room temperature. So the way it is done is basically that one can inject electrically, and one can change the chemical potential of electrons, spin polarized electrons, detect that by flipping this magnets from parallel to anti-parallel configuration, and that leads to obtaining this spin wall signal. This is a spin transport. In case of spin precision, a perpendicular magnetic field is applied whereby the electrons presses about the magnetic field, and there is a continuous change in the spin signal, which can be fitted to an equation that contains a diffusion part, a relaxation part, and a precision part. And from there, the spin lifetime can be determined. So a lot of attempts have been done, and state-of-the-art reports say today that a spin diffusion length of 10 micrometers and a spin lifetime of 1 nanosecond can be achieved in graphene spintronics. So what started from graphene spintronics, now we have 2D spintronics. This is the review. This is another review. These are some recent reviews. And I tried to put here an oversimplified summary of what has happened, like understanding the spin relaxation physics, enhancements in spin transport, use of barriers like hexagonal boron nitride, proximity effects, spin charge interconversion, thermoelectric devices, and spin valley devices. So a lot of things have happened. Despite all these effects, if we really want to harness all these effects, at the base, the platform is graphene. So we need to realize high efficient quality spin transport in graphene, and not only in graphene, but it's in any form of graphene, but a large-scale form of graphene, which means the challenge boils down to a large-scale implementation of this is the necessity, and also the reliability of such a thing. And this has actually been the motivation for my research for the last several years. So to go from here to here, there are some challenges, because here one can obtain single crystals. Here the intrinsic nature is very polycrystalline with grain boundaries, defects, and corrugations, and one can keep on adding more and more fabrication-related defects. Despite that spin transport has been demonstrated, it is feasible to see spin transport in this kind of devices made of carbon chemical vapor deposited graphene. So the question is that those values are of the order of 150 picoseconds. Can we go to higher values? Can we enhance spin communication through wafer scale graphene? This is the question that I've been exploring since several years, and we have been able to see that with channel length, the resistance increases, scales linearly with a reasonable mobility of even commercially available chemical vapor deposited graphene. And what we have been able to see is that in this report, which we published in 2015 with some of my ex-colleagues, we have been able to see that spin transport is possible in commercial graphene over 16 micrometers at room temperature. And this yields a spin diffusion length of 6 micrometers, which is higher and competitive value compared with when we compare with the state-of-the-art reports in sophisticated devices that have been prepared on high mobility graphene. Also, we obtain a spin lifetime of 1 nanosecond. So this is the spin bring contacts closer and closer, which means that there is an influence of contacts, which actually shifts this Dirac point here. As a consequence of that, what we see is that the sheet resistance of graphene changes also, and the contact resistance of these contacts with graphene also, the interface resistance also changes. So when we took this into account, we started to realize that we can keep electrodes very far from one another, and we started investigating extremely long channels that are much beyond, bigger than the kind of exfoliated graphene sheets that one can get. So for the first time, you can see that this is 10 micrometers, this is 13 micrometer channel, this is 51 micrometer channel, and this is 36 micrometer channel, which is the longest channel in which spin signal was reliably, robustly observed. And we could go even up to 45 micrometers spin transport. We can clearly detect spin transport in these channels. And we could also do the spin precision experiments, and we obtained a maximum spin diffusion length of 13.6 micrometers at room temperature. So it's like a spin diffusion length of 14 micrometers nearly, and a spin lifetime of 3.5 nanoseconds, which is the highest. And we could even see that these measurements, when we performed a measurement, even after 10 months, we saw spin transport. And all these things showed a specific kind of behavior that indicated that if we also saw that even under ambient conditions, when we opened the valve and allowed the ambient conditions, we could still see spin transport and obtain the same kind of values of spin diffusion length and spin lifetime. So spin transport is quite robust in this case. So, and when we tried to see the dependence of momentum relaxation with the spin relaxation times due to Elliott-Jaffet or Dekanov Pearl, what we see that in this kind of case, we see that the spin relaxation due to Dekanov Pearl mechanism seems to be the most dominant mechanism. So we ignored the spin relaxation due to Elliott effect. So instead of the conventional method, we tried to employ only the decanopyral mechanism to evaluate the spin diffusion length. So what we tried to do is to make an empirical model to take spin orbit coupling below the contact and in the bulk of graphene, different kinds of values for spin orbit coupling, and try to find an effective value using this empirical value. And we tried to, for different lengths of separation, we tried to calculate the spin orbit coupling from the experimental values of lambda. So we got these values and we tried to plot them and fit with this model, and we find that that beyond a certain point the spin orbit coupling becomes like 20 millielectron volts, which is what one can expect for graphene on large-scale graphene on standard silicon substrates. And we see that when we try to see what is the value, the floor that one can get here, spin orbit coupling, and put it back here, that value like 18.5 microelectron volts, we obtain that we could go up to a maximum of 15 micrometers, which means that we hit the roof of what is available as the maximum spin diffusion length that's available for chemical vapor deposited graphene. So I have many slides, but I can stop at any stage having said one story about how contacts influence spin diffusion length in graphene. What we try to further investigate is that these contacts are much more complex. So to do that, we try to see how metal oxides, which we use between the cobalt and the graphene sheet, influence beyond charge transfer. So in order to do that, we try to deposit graphene on the metal oxide on top of graphene sheet. And we tried to measure its electrical properties and did some complementary experiments to understand what happens to the metal oxide graphene interface, which is key for efficient spin injection. So this is work which we recently published. What we observed is that the metal oxide shifts the Dirac point quite a lot. For both, we used two kinds of oxides which are widely used in graphene spintronics: aluminum oxide and titanium dioxide. With titanium dioxide, usually high spin lifetimes beyond nanoseconds are detected. With aluminum oxide, there has always been a problem with pinholes, and spin lifetimes of 100 or 200 picoseconds has been reported, maximum values broadly. So for both these kind of oxides, we saw that there is p-type doping for both these kind of oxide. And there is a huge change in the Dirac point, shift in the Dirac point. So a lot of doping happens due to charge transfer. And it can be seen that the mobilities for many devices, for both kind of aluminum oxide and titanium dioxide interfaces, we saw that the mobility remains more or less the same before and after. So, and also the minimum conductivity that one can get these points. So what it means is that the electrical properties of the sheets are more or less intact, which means but despite these things, what we observed is that we tried to do some complementary experiments like a photoelectron spectroscopy to determine if these oxides are fully oxidized. And what we see from the energies where we can expect this to happen, we saw that the titanium and aluminum are nearly fully oxidized. At the same time, we could also pick up some contributions in case of titanium and aluminum oxide of sp3 contributions that are dominant compared to what pristine graphene case. And when we tried to do the Raman spectroscopy of all these samples, interestingly, for the aluminum oxide case, we see the emergence of a sp3 defect D band, which is absent for pristine graphene and graphene with titanium dioxide. So there must be something happening, extra additional titanium sp3 defects. So the story turns out to be somewhat like this, that these sp3 defects, so in order to understand how the bonding takes place, we did DFT calculations, density functional theory calculations, which revealed that in case of aluminum oxide, based on how it interfaces with graphene, there can be additional p-type doping and sp3 defects, which can offer a magnetic moment of up to 1 Bohr magneton, which can actually influence spin relaxation, enhance spin relaxation through the resonant scattering mechanism. This is a new insight which could also contribute to the explanation of why, in addition to pinholes, the spin relaxation in graphene is found to be quenched in case of aluminum oxide based barriers, and why titanium dioxide shows superior spin lifetimes. Because these contacts are quite resistive in case of graphene spin devices, it's also important to know how much electrical spin injection we can do, up to what currents we can use these devices for high performance graphene spintronic devices. So in order to understand that, what we try to do is to compare with what is state of the art in graphene is 10 to the power of 8 ampere per centimeter square, which is quite higher than what is 1 or 2 orders higher than even copper, the current density. But then even for state of the art polycrystalline graphene, it's higher, but then it's nearly 1 order less than what is reported in small single crystalline graphene sheets. So we tried to investigate this problem because this has practical relevance, and we used again large-scale chemical vapor deposit graphene. And this work has been recently just accepted. It is online. You can search high current limits in chemical vapor deposit graphene spintronic devices. It's published in Nano Research. So what we see is that the problem comes from here. If you see, this is an atomic force microscopy picture of commercial graphene, and you can see this, these ripples. In addition, there are grain boundaries, and the grain sizes are anywhere range between a few hundred nanometers to several microns, like less than 5 microns. And then this is an AFM picture of a device. So you can see that within a scale of 3 micrometers, we can see a lot of mess here. So that mess means ripples and grain boundaries, which acts as hotspots at these grain boundaries. In this report, where they have seen that the performance is compromised because of these things. So this is a problem of practical relevance. In addition, you can also see that there are thermoelectric effects where heating and cooling takes place in different places. So polycrystallinity and contact resistance and thermoelectric effects, these are some challenges. So we tried to investigate in different devices, and what we found is that you can see that this is an IV characteristic curve for a device here. So one can see what is the tunnel barrier nonlinearity that can be obtained here. And after a certain current voltage, you can see that it can withstand up to 6 milliamperes. Then the graphene sheet breaks. It's a 2-terminal measurement. It means that it includes the contact resistances of these 2 contacts as well as the sheet resistance. In order to see what happens to graphene clearly, we tried to investigate it, and we saw for the first time that there are 2 regimes. One regime up to which is a reversible regime where graphene stays okay, and then there is a regime where it starts to degrade for each cycle. So we perform different cycles before reaching the breaking point. And we could see clearly that we could go to 10 to the power of 8 ampere per centimeter square without any degradation for certain samples. So these are different samples with different sheet resistances. So the key is to have low sheet resistance, and that can give a maximum of up to 5.5 into 10 to the power of 8 ampere per centimeter square. It's possible to go, in principle, it's possible to go to lower values. So very high current density can be realized in CVD graphene, despite the resistance, high resistance of the tunnel barriers, which is needed to avoid the circumvent the conductivity mismatch problem for efficient spin injection. And despite this high current, so we try to also explore if spin transport at all is feasible at these high currents. What you can see here is that it is possible up to 1 milliampere, which is like 10 to the power of 8 ampere per centimeter square. And this is the highest reported value. But then the spin signal actually gets quenched, and this happens due to some magnon excitations at high voltage and heating effects at the interfaces. So we need to improve on this. We need to find out some other kind of barriers where this doesn't happen, efficient barriers. So then what we try to investigate. How much time I have? Do I have how much time?
No, you have time.
Okay, great. So so the interfaces clearly impact graphene, as well as to what currents we can make high performance devices out of chemical vapor deposit graphene is now clear to us. So again, our approach is to see what happens to large scale graphene on different kind of substrates, especially substrates influence graphene. And since graphene and other 2D materials are very resilient, it's important to see if we can take graphene towards flexible graphene spintronic devices. But there can be challenges, because the conventional flexible substrates like polyamide, polyethylene terephthalate, or polyethylene naphthalate, PEN substrate, they often come with a lot of roughness, surface roughness. So in order to establish some kind of stable contacts, we have to make even lithography on this, and we have to lay some electrodes. And how the magnetic texture of those electrodes due to the roughness is influenced is unclear. And also there are fabrication challenges, and nature of transport on this kind of substrate is not clear. Especially in the field, what we are aware of is that if we want high mobility, we need to encapsulate graphene or put it on top of hexagonal boron nitride, which is atomically flat. So it is possible to suspend or to put on top of atomically flat substrate to avoid substrate-induced scattering potentials and obtain very high mobilities. But on this kind of substrate, we do not know, because this has more roughness than the conventional silicon dioxide substrate data that I spoke. But then this is quite compelling, because if we see, compared to normal materials, like for instance silicon, which can withstand a strain of 1.5%, it can almost, the 2D materials can actually go up to 10% of strain levels, which makes them ideal for flexible nanoelectronics. In order to integrate any kind of these devices, spintronic applications of 2D materials into this, it's important that we try to investigate this, which is what we tried to do. So we made some devices on flexible substrates with electrodes, but to see spin transport, if it is at all possible in case of graphene on this curved substrate. So first, to establish the resilience of these contacts, we performed magneto-optic Kerr effect on these wires, on millions of these wires, and we could see that clearly for nanowires they have very much resilience compared to thin films, which break after a stress of 3 gigapascal on the same kind of substrates. So once we established it, we also tried to investigate this. And in addition, the magnetic properties do not change much because of the ultra-low magnetostriction, which means the coercivity doesn't change much when you bend a wire, which makes it very resilient. So we tried to investigate that, and we could clearly see that that these devices show spin transport up to 15 micrometers, and we can also even measure them by cooling the wires that connect them to low temperatures. So spin transport on this kind of substrate is very robust. At the same time, it's also very high diffusive, which could happen only when the electrons have high, or the carriers have high electron mobility. So this is, you can see that at different temperatures we could do it. We could observe clearly the spin transport in these different devices. But then we could also observe a spin precision that yields a diffusion constant which is unusually high compared to our devices that we make on normal silicon dioxide substrate. So the value in this case is something like 10 to 20 times enhanced compared to graphene on the similar kind of devices that we make. And quite there is an enhancement also in the spin signal, and this can only happen if the mobility is high. So we found that the mobility was one order higher in this kind of substrate compared to silicon dioxide, which we established through Hall measurements. So to conclude, it's important to understand how contacts and substrate can influence in order to push graphene to practical circuits, to explore more advanced circuits. And to do that, we have been able to see that it's possible to achieve maximum spin currents by contact engineering, by minimizing the contact effect on graphene doping. We can do that, and we also see that the contacts are not very simple. They can be quite complex. They can involve magnetic moments, which in addition to pinholes, even though for titanium dioxide and aluminum oxide, if we do atomic force microscopy, they both reveal the same kind of topography, which means that in one case it is pinholes, they both can have pinholes. So it seems that magnetic moments influence, and then we also see that it's possible to push very high currents through graphene for high performance graphene spintronics, and we can also make such devices on flexible substrates, which opens gateways for other 2D spintronic devices. And these bring many new exciting opportunities which we are exploring. We have some of these results in this review which we elaborated, so you can get this information from there. I thank you once again, the organizers, and thank you all for this your kind attention. And I also would like to acknowledge the agencies that enable this research. Thank you very much.
Thank you. Probably we can get one quick question.
Yeah, thank you, Vankata, for the nice talk. On the last part, on the strain, so do you have some measurements of the spin diffusion in the function of a strain?
This is a very challenging experiment, and for this we are trying to build a cryostat. Now we have reached a stage that we had to redesign everything to see that how in situ strain can influence spin transport. And so now we will be starting these experiments in a month's time. But initial experiments that we did, we got the same question from the referee. So what we tried to do is to bend it manually and put it and measure it, and we could still see spin transport. That did not, it was not so conclusive to make a statement about that this does this. But strain can do many things. It can increase mobility, it can change the effective mass of electron, and many interesting things can happen. So we are looking forward to these exciting new experiments.
Thank you.
Thank you.
Maybe you can ask in the later. We need more. Sorry. Thanks a lot, Vankata, for coming.
Thank you.
It's on? Yeah.
You will be talking about spin-orbit proximity phenomenon one by one.
Okay, so thank you to come here, and I will also thank Ahmed for the kind invitation to present the work that we are carrying out at the Catalan Institute of Nanoscience and Nanotechnology in Spain. So the talk is going to devote to present our research on spin orbit proximity effects in van der Waals heterostructures. So this is one of the main slides of the talk. So I would like to highlight that this work has been carried out thanks to the excellent team that we had in the group. So I would like to highlight the PhD student, Antonio, the postdoc, Williams, and of course, Sergio, that is leading the group. And I will also like to thank the theoretical support that from the group of Stefan Roche at the ICQMT and especially Jose Garcia. So this is the outline of my talk. So I will try to give a brief overview on proximity effects on van der Waals materials. I will also show you spin anisotropy experiments that induced by proximity-induced spin-orbit coupling. And so what I will show you here is that by attaching together graphene with high spin-orbit coupling material like transition metal like alkylgenides, you can strongly modify the spin dynamics in the system. And finally, I will show you some spin-to-charge interconversion experiments, and in particular, how we can generate spin Hall and spin galvanic effects in graphene, and how this figure of merit that measure how efficient is this spin-to-charge interconversion can be strongly improved when you work with these vulnerable materials and you compare with other high spin-orbit, conventional high spin-orbit coupling materials. And if I have time, I hope that I will have time, I will show you some other experiments that are very recently related to spin-to-charge interconversion with transition metal like alkylgenides with reduced crystal symmetry. Okay, so another way to give you a flavor about the topic of the talk is here. So it's the design of artificial material by proximity effects and some spintronic applications. So there are two keywords here. So one is artificial materials and the other one is proximity effects. So what we mean by artificial materials, so we mean that with this, so we work with van der Waals structures that are made of different two-dimensional materials. So here you have an example of the most studied two-dimensional materials that you have. So you have, it's a very rich family of material platform. So you have insulators like hexagonal boron nitride, you have semi-metals, typically graphene, you have high spin-orbit coupling material like transition metal like alkylgenides, you have also some exams here, black phosphorus, Ahmed is an expert here in black phosphorus, and well, here you can see, so there are more than, so there are some reports, some collected databases, so you can see that this is huge. So you can have, so in these databases you have more than 40,000 entries, and indeed there are some algorithms to see how many two-dimensional materials can be stable, and you have this gigantic number. So so this platform is very rich, so you can play, you have a lot of possibilities, and this is a very famous image that illustrates what we do. So we basically combine different two-dimensional materials, and we just take properties. Just for instance, we can combine the graphene that is excellent from the point of view for spin transport. We can combine with high spin-orbit coupling material like transition metal alkylgenides, or you can also use some dielectrics to create barriers or to protect the devices. So there are two ways of doing these stackings. So a quick way to do that is by mechanical exfoliation of these materials, and then you stack in a controlled way. And there is a second way to do that is by physical deposition, layer by layer, in a controlled way. So we do both in our group, but what I will show you here today is these results on this way of stacking. So again here, so what these are proximity effects. So the take-home message is that a proximity effect, so when you combine these materials in these complex vertical heterostructures, the final result of this guy is not equal to the sum of these individual components. Okay? So you can imprint properties that are not in the pristine form. So the most typical example is in parameters like the spin diffusion length, the spin diffusion time, the spin diffusion constant. So now the point is so this technique is sensitive to the spin lifetimes when the spins are precessing in plane. But what's happened if the spins are precessing out of plane? So we have to develop, so there is an evident configuration, so you can apply the magnetic field along the spin channel direction. So in this case, you have spins that are precessing out of plane, but this has some technical disadvantages. So what we developed in the group a few years back is an oblique technique in which we apply the magnetic field at specific angles respect to the easy axis of the ferromagnet. So if the anisotropy is larger than 1, you have these lines here that are above, or if it's smaller than 1, you have this representation will be below this line. Okay, so then this is what we do. In this, so this is a picture of one device, and you can distinguish here 2 regions. So the first one is this. So before that, so we combine metal. So you have metal electrodes here. So these guys and these guys are metals, and then we put these spin-sensitive electrodes to inject and detect the spins. And you can distinguish here 2 regions. One that is a channel that is pristine graphene, so regular graphene. And then we have a second region in which we partially cover graphene with a transition metal decalculator. In this case, it's tungsten disulfide. We did the same with molybdenum disulfide. So I will just show you that we observe exactly the same. So all the results that I will show you here is with tungsten disulfide. So if you go to the regular graphene, and you just carry out these experiments, so okay, let's first measure qualitatively. So remember that this is not it's technically not, it will give you not the quantity, but it will give you the flavor if it's is isotropic or anisotropic. So if we apply the magnetic field in this region in the device with the magnetic field out of plane, and we measure in this region, when we apply the magnetic field out of plane, we have this signal. This is blue, okay? And if we apply the magnetic field along the channel, and the spins start to precess out of plane, we have exactly the same signal. So this means that you have an isotropic system. There is no difference in the spin lifetimes between one configuration and the other. But then blazingly, when we went here to this region, we observed that the dynamics is completely different. Okay? So when the spins are precessing in plane, the signal is strongly reduced. You see that when they start to precess out of plane, so they start here with a minimum signal, but then they start to acquire a magnitude. And they reach a maximum peak when the spins are exactly pointing out of plane. So in other words, what is happening here is that we have a spin filter. So if the spins are in the plane, they are blocked by this bilayer, by this region, while if the spins are exactly pointing out of plane, they can pass through this. So we can block spins depending on how they are oriented in the system. And this is the representation. So this is remember in the cosinus square representation, if we plot how are these curves, the spin signal as a function of this cosinus square of the oblique magnetic field. So here you have what we measure for regular graphene. So this is at the experimental points that drops within the uncertainty of the experiment in a straight line. So it's isotropic, while this strong deviation is a clear indication that we have spin anisotropic dynamics. And from these curves, we can extract what are the spin lifetimes for spins precessing in plane or out of plane. You see that there is an order of magnitude of difference that is significant. So now the question is, okay, what is the mechanisms, how the spins relax in this system? So this is something that was predicted by, well, indeed was not predicted by the group of Stefan Roth. So they asked themselves, okay, so what's happening in this system when you put these two guys together, how the spin relax? So there are 2 scenarios. So one is when you have intra-valley scattering, so it means that the spins are living only in one of the valleys. So if they are living only in one of the valleys, what they show is that you should measure spin lifetime anisotropy at this 1/2. And this is because the spin relaxation is driven by Rashba spin coupling. So in order to observe this strong anisotropic dynamics, you have to introduce inter-valley scattering. So in this case, the spins are flipping from one valley to another, and they see different spin orbit fields when they are here in this valley or when they are here. So they have spin orbit fields in one direction or in another one. So it makes that when they are flipping from one valley to another, they are relaxing through the Diakonov-Perel mechanism. So what we can do more with these devices, so is these experiments based on spin to charge interconversion. So very briefly, there are two main mechanisms for converting charge into spin and spin into charge. So one is the spin Hall effect. So this is, everyone knows. So if you run a current through a high spin orbit coupling material, you can generate an a transversal spin current with the spins pointing out of plane. But you have a second mechanism here, but this the spin galvanic effect. So if you remember what I explained previously, so here we have an in-plane spin texture in the structure of graphene. So if now I run a current in this direction, I will shift these guys and I will create a spin density in plane in a direction that is transversal to the electric field. So this is basically the scheme that of the device. So here what we attach metal electrodes in graphene, and graphene here is again partially covered with the transition metal dicalcogenide. It is tungsten disulfide, the results that I will show you here also. And then we run the current through the graphene. So in principle, you have these two effects. You have spin with spin polarization out of plane that are arising from the spin Hall effect, but you also have this spin density that is coming from the spin galvanic effect. Another question is how we detect this. Again, we use spin-sensitive contacts here, and how we can disentangle and how we can know if the spins that we're detecting are coming from the spin Hall effect or are coming from the spin galvanic effect. It is obviously playing with the geometry of your magnetic field. So if you apply magnetic fields that are, you apply an out-of-plane magnetic field, so the spins that arise from the spin Hall effect do not process, and you will be only sensitive to the to the non-equilibrium spin density that are coming from the spin galvanic effect. And just opposite, so you apply the magnetic field along this direction, the spins that will experience the precession will be only the ones that are coming from the spin Hall effect. So now there is a key aspect on this. This is very technical, but this is essential. So if you want to really control that you have these effects in graphene, you have to be sure that there is no current shunting through the transition metal dicalcogenide. Otherwise, you can have, in the bulk of this transition metal dicalcogenide, you can have spin Hall effects and you can have a spin polarization. So this is what we did before. So in our device, so unfortunately this picture didn't show you a real device. Now you have to believe me. So we attach here also metal electrodes on the transition metal dicalcogenides to characterize this by itself. And what we did is we inject a current, we apply a voltage through this interface, and we measure what was the current that was flowing from the TMD to the graphene. Okay? So these are the IV characteristics that we measure. So you see that here we are in the band gap of the TMD, and then it starts to conduct electricity for this gate. So we did this as a function of the electrostatic gating in the system. So with this electrostatic gating, I didn't mention before, so we are able to control the carrier density in the system. Okay? So by playing with this, we can know when this TMD starts to conduct. And here you have so how is the characteristics of graphene. So you see that the charge neutrality point is at this gate voltage around 15, and fortunately we were in the region in which the the TMD is not conducting. So we were able to measure these effects to just to be sure that we're not current flowing through the TMD, and also we were able to distinguish how the system behaves if you have holes or electrons. So this is again, so in this case we apply the magnetic field in plane. So this is the precession of the spins that are coming from the spin Hall effect. You see this oscillatory signal. This is a clear indication that you have the precession and you are sensitive to this. And this is the same in the case of magnetic field out of plane. So this is then the signal that we are detecting is coming from the spin galvanic effect. So dots are experimental points. Lines are fittings in which we consider a single free parameter, that is the spin Hall angle or the spin galvanic effect. Okay, and these are the figured merits that we have. So you see that we can, in these systems, if you are pretty sure that the effect is occurring in graphene, you can improve the figured merits significantly. Okay, so we did the same for as a function of the gate. So we saw how the spin galvanic effect change sign, and this is just because this is directly proportional to the carriers that you have. So depending if you have holes or electrons, you change sign. But we measured this signal for the spin Hall effect, and we were a bit puzzled because it is also to expect here to see this change with different magnitude for electrons and holes, for some very technical detail of the band structure of the system, but we were puzzled. So why we are not distinguishing this change? Okay, so we introduced another energy in the system that was temperature. So we did we realized the same experiments at different temperature, and then at some point you see we start to observe clearly this peak and dip. Okay, so the problem here at room temperature was that so we have electron hole bubbles, and so temperature fluctuations that basically blur the signal. But if you are able to reduce this energy, so you see that we can distinguish, and so we were very confident with these results. So indeed, there was some calculations from the Stefan Roche group that they observe and they extract exactly the same behavior. From this, we can estimate what are the spin orbit coupling that you have in the system. And we simultaneously measure the spin signal on the right electrode and on the left electrode. Exactly. And then we apply again, so we measure for different magnetic field configuration. So
but the important thing is that you have the two magnets, so then you can see.
Exactly. So you have to measure at both sides, having a spin sensitive in both sides, and then by playing also with the geometry of the magnetic field, you can disentangle all the spin components that you have in the system.
Maybe we have like 7 people break, and then we have an online.
Hello, can you hear me? Hello. Is there any? I can't hear you. Okay. Sorry. I don't know why. The
Hello? Can you hear? Can you
yeah. Okay. Now I can hear you.
Hello? Now we hear you. Do you hear us?
Yes. Okay. That's great. Right.
Can't hear you.
Share. Okay. That's okay. Thank you for your waiting. So, hi, hello. My name is Hiroshi Izuchi. So, thank you for inviting me, especially Ahmed and organizers. And now I wish to share my recent studies. So, so let me. Okay. So about 2-dimensional ferromagnet on chromium germanium tellurides. So I think most of you are familiar with 2D materials, and I know. So already other invited speakers introduced very nicely. So I will more focus on this 2D ferromagnet chromium germanium tellurides. So in atomically thin to the ponderous materials, chromium germanium tellurides is a one of prototypical material. So it's reported in 2017. A key feature is we can cleave down to atomically thin limit while we can keep ferromagnetic behavior with high crystallinity. So this is say number of layers versus Curie temperature, and this is MH curve by measured by Mock. So this kind of feature can be seen in many of 2D ponderous magnet. But also, I wish to note, so in chromium germanium tellurides, somehow we have relatively easy handling. So like it's less air sensitive. So compared to chromium iodide. So that's why I prefer this material so far. And however, we can basically, try our important challenge. So in 2D ponderous ferromagnet, generally, we have a problem of relatively low Curie temperature. In this case, just about 60 Kelvin. And also, until recently, we didn't have spin-dependent tunneling via atomically thin ferromagnetic crystal. That means particularly using ponderous heterostructure, not using cobalt or conventional magnet. And I wish to deliver two topics today. So one is increase Curie temperature twice by using heterostructure strategy. So we have reported before, but we have a major update. So let me introduce this study. And also we have another topic is spin-dependent tunneling. This is reported last year, but I think it's not very, I didn't talk a lot on this, so maybe this is good opportunity to share this result. So first I wish to talk about this spin-dependent tunneling study. So now my approach is using superconductivity to utilize magnetic insulator. So it might be a little bit strange for some people, but you know, I think if we just want to detect spin polarization, superconductivity is very nice tool. So this forms Cooper pair. So basically up and down spin somehow locked. So we can it is now very sensitive to magnetic field. So if we really look into, so in fact magnetic insulator has potential to have spin polarization, effective magnetic field, or some anomalous Josephson phase, while some other, like while keeping low dissipation, meaning this tunneling behavior is basically bringing low dissipation nature. So, but so far there was a problem of material choice, so it was very limited. So that's one major success case is using europium sulfide, that is ferromagnetic insulator. And back to 1980s, MIT group see some tunneling, spin polarized tunneling using aluminum superconducting lead. And last decade, now people can see Josephson effect through this semiconducting ferromagnetic layer, that is gadolinium nitride, and see very nice future that probably that is interpreted with spin polarization and effective field. But as I mentioned, the material choice is rather limited because tunneling needs very thin layer, but thin layer it is hard to grow. But now in the age of this 2D magnetic material, it is very easy to have very thin layer. So now it's our 2D material gives immediate solution for this problem. So now we can try. And another point of our study is actually using Ising superconductor that is very abundant in 2D materials family. So this is most famous in niobium diselenide case, and spin is actually locked in perpendicular to 2D sheets, so basically plus D and minus D near the Fermi level. So now the spin is now really sensitive to this D direction spin. In the we can imagine there is this chromium germanium tellurides here, and then these Cooper pair should be sensitive to this CGT's spin. And also in practical, we can we confirmed that we can build a very sharp interface using these 2D materials like niobium diselenides. So we can now just insert chromium germanium tellurides here. So general motivation is here, just to remind what I talked. So now we want to study spin-dependent coupling in atomically thin 2D van der Waals interface. In this, using this 2D, we don't restrict to CGT, but basically 2D ferromagnetic layer. And whether we can see any new effect, that's our question. And the answer is yes. So I'm not sure how familiar with the Josephson junction. So the structure is here. We have niobium diselenide up and bottom and top, and we have inserted CGT layer, and then we measure the resistance of the junction. So this is a typical signal. So x-axis is a bias current, and y-axis is voltage drop across the junction. So you see very clear zero resistance state. That means we have indeed Josephson coupling between two naive diacerylides across this monolayer CGT or six layered CGT. So if you bias more, at some point you break this, the energy exceeds Josephson coupling, and then you have normal state. So you have usual resistance of the junction. So first we confirm Josephson current, and then we also study thickness dependence and characterize thickness characteristics. So we have some resistance coefficient of tunneling behavior, and also thickness characteristics, which is about 1 nanometer. I don't skip the I skip the detail, but with gap size and so on, it's reasonable. And then if we see the critical current with various magnetic field, in fact, actually we have some hysteresis. That's something somewhat unusual. So from here, of course, if you decrease the magnetic field, critical current is higher, but at some point it jumps, and there is a hysteresis. Also, that kind of hysteretic behavior, or actually implying two energy level, that is seen both 6 monolayers case and monolayers case. And we wondered what it is, and then we constructed actually squids with this CGT tunneling junction. So this is to explain basic principle of Josephson, squids with Josephson junction with zero phase and pi phase. So if you have if your squid has two zero phase Josephson junctions, you have a maximum current at zero field, while if you have zero pi junction, your critical current is minimum at zero field. And so finally, we make this squid. Now one arm has niobium diselenide junction without CGT, and another has one monolayer CGT, and we have nice oscillation and some anomalous behavior. Sorry, this is a monolayer. It's typo. But all right. So we have again, if you have sweeping, if you sweep different weights, you have also different critical current. So all these indicate some kind of two energy levels behavior. And finally, so we make this aluminum, this sample. So we have this squids, niobium diselenide CGT squids, and also several aluminum squids, so that we know exact zero field limit. So otherwise, it's very hard to distinguish the phase, because important is where is this zero field. So by calibrating zero field with these several devices, we finally actually find both phase is neither zero nor pi, so it's very non-trivial. And then actually we had kind of hard time why it happened, but finally we found how can we explain. So if as I said, I think superconductivity is very sensitive to plus minus d spin, so you can have this spin-dependent coupling, spin-dependent tunneling. But if your CGT magnetization is z direction, but if your CGT magnetization is in plane direction, this doesn't really have spin-dependent coupling. So this can explain as follows. So actually, so this with magnetic domain structure, we have pi part and zero part, and if you have the energy of pi part and zero part, actually we have some bistable this kind of energy, and then in fact, this can be applied for the area within the coherence length, but this coherence length is rather high, so we can apply this theory. And in experiment, we can do actually measure many times sweeping and then take hysteresis, and then we can actually confirm whether this is consistent or not. So now we can have two different statistics of escaping from the potential well. So this indeed is consistent with what I explained. So in this part, I have shown the doubly degenerated phi Josephson junction. Phi is meaning it's non-zero phase, non-pi phase, some phase between them, and using that is shown with using atomically thin niobium diselenide and CDT, and that explained by coherent combination 0 and pi Josephson junction segment. So broad message is, all right, we have many interesting 2D material, so we can actually have many potential further improving or further finding novel phenomena. Now the time is rather limited, I would think, but let me introduce this. So I think this basically explained. So last half part, I wish to explain the approach to enhance the magnetism in 2D material. So people use electric field effect, for instance. It is successful for iron germanium tellurides, but also use pressure cell. So you can apply pressure. This is conventional method, and you can change the atomic distance between the lattice. And although the Curie temperature change is small, but we basically and there is rather limited capability of this stretching. So I think we believe this actually can happen in our sample. So this is rather incidentally observing, but before we were studying CGT flake with nickel overlayer, and nickel overlayer, with nickel overlayer, somehow we have additional optical contrast. And then we examine by AFM and see some topography. Actually, the height is high in this additional place. And then we also do cross-sectional TM imaging, and actually, indeed, this has some structure corresponding to this area. And if we measure Curie temperature with a lot of the CGT nickel flake, and then it seems the formation of this linkage somewhat correlate with enhancement of Curie temperature. And there is a story on DFT calculation, so that this indicates lattice stretch may enhance the magnetism. So our hypothesis is here. So if we have some two layers, somehow if we can stretch, so the top layer, it can have wrinkle. So suppose number of atoms is conserved. So if this area is stretched, somehow this area needs to have wrinkle. So we have characterized by Raman spectrum. Raman spectrum shows very good features, and peak position varies with place, and this indicates actually near this wrinkle, lower frequency. That it means tensile strain. And also we have measured a lot of sample and show some correlation. That means basically with wrinkle we have a lower frequency, and we have some correlation with Raman and Mach. So if we have more stretch, somehow we have more higher Curie temperature. That's what we have seen, and we see more device characteristics that basically same thing, but for more devices. And then DFT calculation was done for thicker CDT instead of monolayer CDT reported. And also with tensile strain, we see enhanced magnetism in this either magneto-anisotropy by crystal or exchange energy or even Curie temperature. Right. So finally, we examined scanning TM by using scanning TM method. So on this strange CDT nickel O. So all right, let me remind, if we have CDT and form nickel O by sputtering, and then we have some strain and some wrinkle structure. But we were always, it's without seeing this kind of structure, it's kind of indirect information. But if we really see this atomic place, although we need to, it's small change. So we just see contrast as a function of the position and see some oscillation fits as a function of oscillation. And then we can obtain some, actually it indicates larger lattice constant near the interface with nickel O. And by Fourier transform, we actually see more clear behavior. So near nickel O, somehow lattice is a little bit stretched. All right. And sorry. So this is, and we have more going too deep about how does it happen, but maybe we can save it for question. So lastly, let me summarize. So we have enhanced magnetism in CDT nickel structure, and then we observed correlation with enhanced magnetism and Raman shift, and also DFT calculation support enhanced magnetism in stretched CDT. So this perhaps doesn't really need exact combination of material. So it may be wide. I hope this can be widely used for heterostructure of 2D van der Waals material. So thank you for your attention.
Thank you for very interesting talk. So I have like a couple questions.
Thank you.
So
Yes.
when you mentioned that like when you form the interface between nickel oxide and CGT, that's magnetism in hand, right? And you attribute it to the tensile stress. So what's
Yes.
how stress is basically change the distance and also the bond angle, because that is depend on how the basically chromium distance is far away.
So angle means in plane angle, right?
So did you look into that? I mean, DFT calculation support anything related to the change?
You mean DFT calculation or magnetism?
Yes. Is that change like the chromium's tellurium's distances, or like chromium's tellurium's chromium's angle? How you change this?
Okay, so this is, I think it looks more on the distance itself. So chromium, so this, for this kind of compound, chromium major, there is a large antiferromagnetic exchange energy that decrease quite fast with increasing the distance. So we think that is a reason why we see increase.
We also, I mean, look at like the other system. But I think in this case, like chromium's distances is very far away, so typically would not much affect under the tensile strain. But the other would contribute to it, so you may want to look into it. And you only put it to tensile strain, but since you have like little oxides, the antiferromagnet, so it has a ferromagnet antiferromagnet coupling. So it's a like magnetic positive effect also plays a role here in enhancing the DC and other magnetic properties.
Okay, that's good point. So in fact, some group shows enhancement of Curie temperature with using that coupling between antiferromagnet and ferromagnet. So we also kind of expect it, but so there are some negative data. So for instance, I do not see exchange bias effect, while if we use permalloy nickel layers with same chamber, I can actually see exchange bias. So I don't, so that's why I think what we observed is most likely not because of the from antiferromagnetic behavior of nickel. Yeah, but that's a good point.
You have shown some supercurrent images. Can you tell me, like, how did you compare the supercurrent with other 2D systems that have been used in Josephson junctions?
I myself do not, but back in these days, so there are colleagues who was using, for instance, graphene HBM for the barrier. So we have had some discussion.
And how does it compare with those values?
So for monolayer case, actually for CDT, it was rather high. So it's similar to, it was comparable to niobium dicyanide's graphene niobium dicyanide's device.
Okay, thank you.
So I have a very quick comment on the first question. So because yesterday, I reported our data on the pressure-dependent magnetism of chromium germanium telluride, where we found the compressive strain, it decreases the TC, it decreases the magnetic anisotropy, destabilizes magnetic color. From that, it could follow that the tensile strain would indeed, stretching the lattice, would stabilize magnetic color and enhance the TC. So that is somehow an argument which is put forward also by the speaker.
Okay. Thank you very much for that precious information. I'm glad to hear you are consistent. Our study is consistent. I guess my time is up. So thank you very much again.
Thank you.
Yeah, so thank you for the kind introduction. My name is Klaus. I'm from the University of Regensburg, working in the group of Professor Jaroslav Fabian. I have changed the title a bit to be a bit more generic. So I will talk about these twisted graphene CGT heterostructures, but also about other twisted 2D material heterobilayers. So by now I think we all agree that 2D materials are highly interesting. And on top of that, for every 3D material we now have a
2D analog, be it metal, semiconductor, insulator, ferromagnet, superconductor, whatever you wish is available. And despite each individual material has highly interesting properties, we can combine them in van der Waals heterostructures where proximity effects play an important role. Okay, it's not working. So for example, if you look into such a tri-layer structure, then the effective Hamiltonian will not just be the sum of the individual ones, but rather can be heavily modified by proximity effects. And the prototype material that one typically considers is graphene because it has a weak spin-orbit coupling. Actually, you can say it's absent, roughly. And it also has no magnetism in it. Now, one of the spin interactions that can be induced in graphene is the proximity spin-orbit coupling, as we have already heard today of. So, for example, if you consider graphene on top of TMDC, in this particular case it's MOS2, and if you calculate the band structure from first principles, you will find that the two individual dispersions are very nicely preserved due to the weak van der Waals interaction of the monolayers. And in particular, the Dirac cone is very nicely preserved within the band gap of the TMDC. However, if you then zoom in to the Dirac states, you will find such a splitting of the bands. And this splitting results from the proximity-induced spin-orbit coupling, which is of the Valley-Zeeman and Rashba type. So maybe I'll change this because my smartphone is maybe interfering. Yeah. Now, okay, thank you. Now, another spin interaction that can be induced in graphene is, of course, the exchange coupling. So when you place graphene on chromium germanium telluride, for example, which is a ferromagnetic semiconductor, you will find a very similar situation. The Dirac states of graphene are quite nicely preserved within the band gap. And if you then zoom in to the Dirac states, you will find such a splitting of the bands, which reminds us of the Zeeman splitting from an external magnetic field. But here is not an external magnetic field, it's rather the exchange field originating from the ferromagnetic semiconductor. Now the question is, why is this important? And I think today we have already seen why graphene physics is important. But still, graphene has very nice spin and charge transport properties, and it can be used to perform spin logic operations. On top of that, when you, for example, combine graphene with a TMDC, it can be used as a field effect spin transistor. In this particular case, it's bilayer graphene on top of tungsten diselenide or another TMDC. It does not matter really much. And what is important here is the short rangeness of the proximity effect. So only the lower layer is proximatized. And on top of that, with the electric field, we can then switch the band structure, so we can effectively turn on and off spin orbit coupling in the transport channel, and this can be used as a field effect spin transistor. Moreover, we have already seen that it can also be used to interconvert between spin and charge currents, such heterostructures. Without the need of conventional ferromagnetic electrodes, we could actually switch between spin and charge currents. Now this is very nice, but still we would like to know if we can get another handle on this and somehow control the things a bit more. So we would like to have an on-demand control of these spin interactions and optimize the things for spintronic devices. And one way to do so is via pressure, external pressure. For example, in these experiments it has been demonstrated that the proximity-induced spin-orbit coupling can be drastically enhanced by external pressure. So what happens? If you place such a heterostructure in a pressure cell, you will effectively reduce the van der Waals distance. Thereby, the coupling between the layers is getting enhanced, and also the proximity spin-orbit coupling is enhanced. And if you then do the magnetotransport measurements of such system upon external pressure, you will find such a crossover from the weak localization into the weak anti-localization regime. If you then do the fitting of these curves, you will find that the Rashba spin-orbit coupling can be roughly increased by a factor of 2 with an external pressure of about 1.8 gigapascal, which corresponds to a reduction of the interlayer distance by 0.3 angstrom, which is around 10% of the interlayer distance. And now the second thing that can be done is, of course, twisting. And recent tight binding calculations have shown the following. So when you place graphene on tungsten diselenide, then the Vallée-Zeeman spin-orbit coupling in graphene will follow this blue line. So we have this intermediate maximum at around 15 to 20 degrees of the twist angle, and it then goes to 0 at 30 degrees, which is due to symmetry. The Rashba spin-orbit coupling does not show such a, say, nice evolution. It stays more or less the same over the whole twist angle range. And on top of that, the Rashba spin-orbit field, this in-plane spin-orbit field, can be heavily deformed by twisting. So it has been shown that at 0 degree twist angle, you have such a tangential, typical Rashba field you would expect. But once you twist it to a certain angle, it can become purely radial. Now, if you do actual DFT calculations on large supercells, you will find that the proximity spin-orbit coupling can indeed be heavily tuned, but the results do not completely agree with what the tight binding picture says, because, for example, this Vallée-Zeeman spin-orbit coupling has here more or less a plateau and then drops to 0 at 30 degrees. So what is the consequence of this radial spin-orbit field? So if you do spin-charge conversion experiments, which we have heard of today, and you have such a typical radial tangential Rashba field, then your spin density that you generate will be perpendicularly polarized to the charge current. This is known as this inverse spin galvanic effect or Rashba-Edelstein effect. No matter how you call it, it's the same mechanism. But if you then switch into this radial spin-orbit field, you can also tune the polarization of your spin density. So it can become collinear to the applied current. So with the twist angle, we have actually a knob to tune the polarization of the spin density. And now let me switch gears and come to the actual things I would like to present, which is the engineering of proximity exchange in graphene chromium germanium telluride heterostructures by twisting. So the situation we have is like this. We fix the magnetization of the ferromagnet and simply twist. On top of that, we can apply a transverse electric field to see how the things can be tuned. And what we do is DFT calculations on large supercells, and then we do the effective modeling of the low energy states. And the situation roughly always looks like this. So the Dirac states are nicely preserved within the band gap of the CGT. And now let me discuss on a specific example what is going on, which is the 30-degree twist angle structure. So the overall band structure we have already seen. The two different colors correspond to spin up and spin down. And if you then zoom in to the Dirac states for this 30-degree structure, you will find that the spin down bands are pushed to lower energies compared to spin up. If you place your Fermi level to this dashed line and you calculate the spin polarization that is on graphene, you will find it to be very uniform and negative. And the corresponding model parameters are the same for both sublattices and also negative. Now, where does this come from? If you consider perturbation theory, you would expect that the Dirac states would couple to these energetically closest spin-up substrate bands. However, if you would do that, then the spin-up Dirac states would be pushed to lower energies because energy levels that are coupled repel. However, this is not the case what you observe in the DFT calculation, and it's actually rather the coupling to high energy bands. And in particular, you will find such a pronounced anti-crossing of spin-down Dirac states to substrate bands. And this is, in fact, pushing the spin-down Dirac states to lower energies. Yeah, so the coupling is here. And another way to look into this is within the framework of the projected band structure. So this is again the full dispersion, but now decomposed into spin-up and spin-down manifolds. And the color code tells you something about the percentage of graphene within these states. So blue color means it's pure graphene, red color means it is substrate, and these rainbow colors indicate the coupling. And in fact, for the spin-up case, you will find no coupling to these low energy substrate bands, while there is quite a weak coupling to these high energy levels. In contrast, in the spin-down manifold, you find quite a strong coupling of the Dirac states to these high energy levels. And this is what pushes the spin-down Dirac states to lower energies for this case. And now this is a summary of our most important findings. So for 30 degrees, we have already seen what's going on. We have this negative spin polarization. Spin-down Dirac states are pushed to lower energies, and these are the corresponding exchange parameters for our model. Now, if we go to the 0 degree case, we find exactly the opposite. This is really remarkable. Spin-up Dirac states are pushed to lower energies. And if you calculate the spin polarization, it's again uniform but positive on the graphene. So you can essentially reverse the proximity exchange by twisting. And what is even more remarkable is that at a certain twist angle, this 19.1 degree, you can actually realize antiferromagnetic proximity exchange in graphene. As we can see here, this very nice sublattice character of say positive and negative spin polarization on the graphene. And of course, we did not only investigate these three angles, we did the full angle range scan. And what I summarize here is, say, the ferromagnetic and antiferromagnetic proximity exchange as a function of the twist angle. And what we can see here is that the ferromagnetic one can be tuned rather nicely from positive to negative values when twisting from 0 to 30 degrees. This antiferromagnetic proximity exchange arises only for this special twist angle of 19.1 degree. However, I have to admit that this antiferromagnetic proximity exchange is not very stable, so it depends really very sensitive on the atomic stacking that you employ in your DFT calculations. But still, it's a very nice finding. And of course, we did then also check what the transverse electric field could do. So in these two color maps, I again summarize this ferromagnetic and antiferromagnetic proximity exchange as a function of gating and twisting. And most important is, for example, if you look into this range around 12 degree twist angle, then you can actually switch from positive ferromagnetic to negative ferromagnetic simply with the gating. So you can barely see this in this color map, but still this is a very nice finding that simply with the electric field you can switch the proximity exchange from positive to negative in graphene. Now, why is this important? So this can be actually utilized for spin injection and transport. So when graphene is proximatized in the way I've shown, then the density of states will split up like this. And then the graphene polarization as a function of energy will follow this curve. And recent experiments by the Van Wees group exactly wanted to show this. So they did non-local spin transport experiments, which we have heard of today. And this non-local resistance signal depends on the injector, the graphene, and the detector polarization. And in this case, they were using non-magnetic gold electrodes, which means that the injector polarization is 0. And this also means that we have only 2 contributions left, which is the polarization graphene and graphene, this product, which simply gives you a spin-dependent background. And then this remaining product, P graphene, and the detector one. So the detector is cobalt. And now let's see if graphene really is polarized. This is what they measure. At 0 field, they measure a low resistance state, which means the graphene and the detector, the cobalt, are parallel polarized. At some field, the cobalt switches and we go to a higher resistance state. And at an even higher field, the substrate switches, which brings us back to a low resistance state. So when the substrate switches, the proximity exchange switches, and this means also the polarization in graphene switches. And this experiment very nicely demonstrates that we can use proximitized graphene for spin injection without the need of conventional ferromagnetic electrodes. And now in the remaining minutes, I would like to talk about twisted TMDC heterostructures, and in particular the valley splitting, how we can engineer this. So what we consider are the semiconducting TMDCs, MOS2, MOSC2, and also tungsten-based compounds. And what is most important is this spin valley locking, which we have heard of today as well. And the important thing is, if you do optical measurements, then the plus K valley will react to a sigma plus polarization, and the minus K valley to a sigma minus light polarization. So if you do photoluminescence experiments at 0 external magnetic field, you will find that the PL peaks of the 2 polarizations coincide, right? Because they are energetically degenerate. Once you crank up the external magnetic field in the out-of-plane direction, you will find such a very nice splitting of these 2 peaks, which is known as the valley splitting. And this valley splitting follows this linear trace as function of the magnetic field, where also the G factor plays a heavy role. In this case of bare monolayer TMDCs, this G factor value is around 4. But still, if you apply a magnetic field of 8 Tesla, you get only a valley splitting of 2 millielectron volts. And this is where the proximity physics comes into play. So if you consider a tungsten diselenide on top of chromium triiodine, which is also a ferromagnetic semiconductor, then due to proximity-induced exchange coupling, a valley splitting of around 20 Tesla will intrinsically arise. So these are the data, and so this additional quenching of 1 photoluminescence peak for the sigma plus comes from the band structure simply, but still these 2 peaks are split. That would correspond to around 20 Tesla of external magnetic field. And this is, of course, why we considered this in DFT and checked what does the twist angle do, what does a gate field do to this. And the story goes like this. So if you start with a 0-degree twist angle structure, you can very nicely recognize the band edges of the TMDC here around the K valleys. These spin polarized in-gap states result from the chromium triiodine, which is also responsible for the quenching of the PL peak for 1 light helicity. And this is a calculation without spin-orbit coupling to really resolve the proximity exchange alone. Now, if you zoom into the band edges, you will find a splitting of the conduction band edge and the valence band edge like this. The spin ordering is the same, and we characterize this splitting by a parameter BC and BB. And if you then go to the 30-degree case, you find that the conduction band splitting remains, the spin ordering remains, while the valence band switches sign. So we can again reverse the proximity exchange splitting in the valence band by splitting, which is similar to what we have seen before. And again, we did the full twist angle and gate scan. So the conduction band splitting stays more or less the same upon twisting, but the valence band splitting can be very nicely tuned from negative to positive in this linear fashion by twisting from 0 to 30 degrees. And if you look into this electric field and twist angle dependence, you can find that the conduction band splitting can be tuned in the range of minus 2.5 to minus 0.5 millielectron volts, while the valence band splitting can be heavily tuned from about minus 1.5 to 4 millielectron volt upon twisting and gating. And this has profound consequences for the valley splitting. So the most important result is here. So this is the calculated valley splitting for tungsten diselenide on top of monolayer chromium triiodine when we twist and gate. And the tunability is really giant. So you can go from 0 to 12 millielectron volts in the valley splitting by twisting and gating. These 12 millielectron volts correspond to an external magnetic field of 60 Tesla. And this is really a gigantic field. And this already brings me to the end of my talk. I hope that I could convince you that twisting and gating are two very, very efficient control knobs to tailor proximity physics in 2D material heterostructures. And with that, I thank you for your attention.
In this TMD with proximity effect, do you calculate the anomalous Hall effect? Because if you have such a splitting, maybe...
Yes, one would expect that, right? But we do not calculate it.
No,
So right now we're at the stage that we have calculated all these heterostructures, applied the electric field, explained the mechanism, what is behind this reversal, let's say. But one could do that.
Yeah, because that could motivate, I think, the experimentalists to try, because that's kind of easy measurement. Right?
Yeah, sure.
It's very interesting talk. So you look at like the system that has very low DC, and actually chromium iodide has very low DC.
Yeah, and it's even more unstable, let's say, than
Exactly,
the
and
ZGG.
very sensitive to the oxygen.
Yeah.
So iron germanium telluride becomes interesting candidate because it's also have like perpendicular lattice anisotropy. And recently people also try to basically interface with the tungsten diselenide as well. So that may bring up basically like, you know, close to room temperature, you know, magnetic positive effect. And that could be very interesting system to look at.
Yeah.
So regarding this TMD, I know some work they show that like on top of basically forming interface with other magnetic materials, you can dope magnetic, you know, elements, and that could also enhance Valley spin, you know, Valley splitting. So do you think that would be interesting to approach using two different ways? So one is you dope to enhance that, and then you can form the interface to further enhance Valley
Sure.
splitting.
Yes, I think so. Absolutely.
Thank you.
Yeah, hello. So it was a very nice talk. So I have a particular question for you. So like mentioned previously, like if you put any graphene, very low spin orbit coupled material and TMDC, obviously that will induce spin orbit coupling. Okay, so there are experimental and theoretical evidence that if you put a bilayer graphene on like WAC2, that will actually change the spin orbit coupling of graphene from microelectron volt to millielectron volt, like 15 or 7 millielectron volt. Okay, and also you can tune the spin orbit coupling, and you can actually measure it by doing non-local measurements and other thing. Okay, so people have found both theoretically and experimentally that if you actually tune the perpendicular electric field from negative to positive, the splitting can change from for bilayer graphene from valence band to conduction band. Okay, both like capacitance measurement or normal D measurements. Okay, so my question is, what will happen for monolayer graphene? If you put monolayer graphene on WSC2, what will happen? Because for bilayer graphene, we can understand like the bottom part of the bilayer graphene is basically close proximity to the WSC2. That can actually enhance the spin orbit coupling for the bottom layer. For the top layer, since there is a van der Waals distance between the top and bottom layer, so overall spin orbit coupling is basically small. So my question is, what will happen for the monolayer graphene? So can we act similar to the bilayer graphene? We can actually switch the like proximity induce
No.
with the perpendicular field.
So there is a small impact of the proximity spin orbit coupling upon electric field, but you cannot switch it because in this sense the bilayer structure is really completely
So
different.
Yeah, I know. So what will happen with the field?
So you mean what happens to the effective parameters once you apply the electric
exactly. Experimentally for bilayer graphene, people have found like if you have some phase diagram of D versus density, like D is the field, what I'm talking about, and N is the density. If you see the map near the if you the diagonal is the basically the Dirac point, okay, the diagonal element. People have found some asymmetric dependence also. The asymmetry is coming from the spin splitting, okay.
Yeah, sure.
So what will happen for the monolayer case?
Yeah, so I guess what happens once you shift, say, the Dirac cone within the band gap, you can tune the
For
proximity.
monolayer graphene, there is no band gap.
No, within the band gap of the TMDC. So you shift your Dirac states within the band gap, and thereby you affect the proximity spin orbit coupling. This
How it will depend?
We are running out of time, so probably we can discuss in the
Okay, sure. Yeah, we can just.
So thanks again for the talk.
Yeah, thank you.
So we have the last talk of the session that is going to be given by Professor Andrei Slavin from Auckland University. He's going to talk about spin torque-driven antiferromagnets for terahertz frequency magnonics.
All right. So I will talk mainly about the application of antiferromagnets in terahertz frequency signal processing. This talk will not contain a lot of new physics. This will be a talk of how to design useful devices in terahertz frequency region from a theoretical point of view. I will talk a little bit about difference between antiferromagnetic materials and ferromagnetic materials, and how the antiferromagnets can be used in terahertz spintronics. I will talk briefly about oscillators based on antiferromagnets, and a little more detail about detectors. I will talk about the construction of a resonant antiferromagnetic detector of terahertz frequencies. And then I will discuss the tunability of receivers, how you can make these receivers of terahertz frequencies tunable. Before I talk about the motivation, I would like to say that Louis Néel, who basically discovered antiferromagnets and studied them in detail, in his Nobel Prize address said, these are very interesting materials, but absolutely useless. I will try to prove that it is not exactly that way, although making use of them is not a trivial issue. So first of all, we will be interested in a frequency range of about 10 to the 12 hertz, and it is rather easy to generate everything lower and many frequencies higher than that. But there are practically no natural resonators having resonance frequencies in the terahertz frequency region. And the antiferromagnets are almost the only class of substances which have natural resonance frequencies lying in a terahertz region. What's the difference between dynamics in ferromagnets and antiferromagnets? Well, ferromagnets, they have magnetization, order parameter, and the resonance frequency of a ferromagnetic resonance is proportional to the external field and the dipolar fields, which to a certain extent these dipolar fields can add also the anisotropy fields, and dipolar fields are also almost totally dependent on the shape of the sample. These are demagnetization. And you see that the external field realistically cannot be more than half a Tesla for any portable device. So the frequencies which you can reach are limited by, say, 20 or 30 gigahertz. So if you want to do something which is higher than that with ferromagnets, you need either huge magnets or there is no way. In the antiferromagnetic substance, there are two sublattices which are oriented antiparallel to each other. The field which keeps them antiparallel, this is the internal uniform exchange field or Weiss field, the field which is responsible for ferromagnetic order. This field is about 1,000 Tesla. So trying to interact with this field is almost useless. How big field you can create? 10 Tesla, 20 Tesla, not 1,000. So in some antiferromagnets, you can study statics by changing the external field, and chances to change the dynamics using external field are almost nil. But the antiferromagnetic resonance frequency is determined by the product of this exchange field, internal exchange field, and rather small anisotropy field. And that means that you can influence the frequency of antiferromagnetic resonance mainly by changing the anisotropy field of the crystal. Now, if we want to actually create a generator, we need to somehow excite this eigenmode either in ferromagnet or in antiferromagnet. In a ferromagnet, you can do the following thing. You can actually create the spin polarized current where the vector of polarization will be parallel to the magnetization, and that will create, with a certain direction of the polarization, will create an anti-damping torque, which will try to destabilize the static direction of magnetization, which is actually, in a static case, simply parallel to the external field. If you will try to do something like that in antiferromagnet, we have two directions of magnetization, one sublattice and the other one. And so if you destabilize one of them, you will actually stabilize the other one. So if you apply the external spin torque or spin polarization, which is parallel to the direction of magnetization, in this case to the direction of these two magnetizations, the net result will be 0. You will not be able to excite anything. So there is no chance to actually excite the eigenfrequency. So if you want to excite something, you need to do something else. And what can you do? You can apply the spin polarization perpendicular to the direction of magnetizations in the antiferromagnet. Perpendicular, in that case, what you can do, you can slightly tilt the anti-parallel directions of magnetization. Can you tilt it strongly? No, because you see the force which makes them anti-parallel 10,000 Tesla. So you can probably get tilt of 1 degree or a couple of degrees. But this is enough. If you do that, the tilted antiferromagnetic sublattices will start to rotate in this huge exchange field. And if you will do that, you will get the rotation of this magnetization order in the huge exchange field, and you will get frequencies of this rotation, Larmor frequencies, which are in sub-terahertz or terahertz frequency range. Now the question is how to choose the crystal. And there are plenty of uniaxial antiferromagnets, and among them there are dielectrics, and there are semiconductors, and there are conducting materials. And there are also plenty of biaxial crystals where the anisotropy is more complicated. So the frequencies, the characteristic frequencies of antiferromagnetic resonance, you see range from 1 terahertz to say 160 gigahertz. And this is a hematite where the frequency is relatively low. So it is a kind of a proof of principle material, which is a antiferromagnet, but the frequency is still rather low. So you can use almost a conventional electronics to do experiments with. It was shown experimentally that if you put an antiferromagnet in contact with a ferromagnetic material and you excite a ferromagnetic resonance in the antiferromagnet, in the ferromagnetic materials, there will be a spin pumping into the antiferromagnet, and you, using inverse spin Hall effect, you can actually detect the signal. And that was demonstrated both in chromium oxide, in manganite fluoride, and in hematite. So there is a chance to receive the external signal using the anti-ferromagnet, and the response will be resonant. And if we find a way to tune this resonance also, then we will get both a generator and a receiver, which is continuously tunable in frequency. So our goal, basically in this talk I will talk about only receivers, to create a tunable resonant receiver of sub-terahertz signals based on antiferromagnet to find how it can be tuned, and to find how we can get the output of this material and how can we excite the signal in this resonator. This slide simply summarizes our theoretical project of how to create a generator. And a generator can be created by putting a layer of antiferromagnet on a platinum electrode, and then the current flowing in the platinum creates a spin Hall effect, which creates a spin torque on the boundary. So the antiferromagnet should be very thin. And in that case, there will be a tilt of sublattices and rotation of sublattices in the plane perpendicular to the hard axis of the material. And the equation which describes this is very similar to the equation describing the oscillations in the Josephson junction, where this 1 over exchange field plays the role of the effective mass. The effective damping is usual Gilbert damping, and the Josephson potential is replaced by the potential where phi is the azimuthal angle of rotation and of the sublattices. And the frequency, as you see, can be about half a terahertz when the current density is about 10 to the 8 ampere per square centimeter. And we have here a big specialist in spin torque oscillators as our chair, and he knows that in principle you can reach these current densities in real experiments. Now the receiver. We will try to use the receiver using a very similar device. The device consisting of the antiferromagnetic layer, a layer of platinum or any other heavy metal, where we will supply the AC signal, which is the signal which we are going to receive, plus a DC signal, which I will show can help us to change the resonance frequency in the antiferromagnetic material. And the top layer will actually receive the signal obtained due to the magnetization dynamics in antiferromagnet using the inverse spin Hall effect. I will not discuss these equations in detail. I will simply say that this is the equation for the Néel vector or order parameter of antiferromagnet, which is basically difference between magnetizations of sublattices. This term is the inertial term, where this is the effective mass. This is a damping term. This is a term describing the anisotropy of material, and we will have two spin torque terms, one related to the DC current which we are supplying to move the frequency, and AC current, which is our actual signal. If you do first of all, the static problem, you will see that DC current basically changes the direction of the Néel vector. And this angle is proportional to the current, and that way you change the frequency of the antiferromagnetic resonance. While the dynamic term, AC term, basically gives us the high frequency response. And this high frequency response looks like this. This is a normal resonance curve. As you see, for the material which we are using here, which is, I think, iridium manganate, the frequency is about 450 gigahertz. Our line width is about 60 gigahertz. And although this Q factor is only around 10, this is much better than bolometers, which are used right now to measure the terahertz signal amplitude. We'll also see that the resonance frequency can be tuned by the changing of a current density. Again, this is not a huge change, but nonetheless, it's continuously tunable. And I saw a new paper submitted to Science where this was fully confirmed experimentally. It will appear probably in a couple of months. The line width is not changing with the current, it's almost constant. And the sensitivity of a detector is actually rather large. The sensitivity of a detector, if a detector has a nano size, is about 1,000 volts per watt, which means millivolts per microwatt, which is comparable to the best Schottky diodes or best GaN diodes used, semiconductor diodes. And diodes are not frequency selective. It is very important to understand that you can get a good receiver in the case when the signal is polarized, circularly polarized, and you will need to construct the antenna in a specific way to get the signal to get the response if the signal is linearly polarized. And the calculations show that for linearly polarized signal, if you are not using the external bias magnetic field, you will not be able to receive anything in the uniaxial antiferromagnet. And you will need a biaxial antiferromagnet if you want to receive linearly polarized signals. Circularly polarized signals can be easily received with a good sensitivity. So the intermediate conclusion is that if you want to have a receiver which will work with signals of any polarization, you need to use biaxial antiferromagnetic crystals, and you will increase the sensitivity of a detector if you apply the external bias field. What you can do also to change frequency is to put the antiferromagnet in contact with piezoelectric. In that case, by applying voltage, electric voltage to piezoelectric, you can change anisotropy in the antiferromagnet, and you can change the frequency of antiferromagnetic resonance. And it can be shown that this magnetostriction is different for different crystals. For example, in nickel oxide, it is the coefficient of tuning in 1.6 10 to the minus 2 kilovolts per centimeter, while in the hematite, it almost 2 orders of magnitude larger. And you can extract the signal either by inverse pinhole effect or using the antiferromagnetic tunnel junction, which recently has been demonstrated experimentally. So my final conclusion is that we demonstrated theoretically that antiferromagnets can be used as active elements in resonant generation and resonant detection of terahertz signals. The sensitivity is comparable to the sensitivity of modern Schottky diodes, and the effect can be observed experimentally, and this is a challenge to the experimentalists who are sitting in this audience and in general. Thank you very much.
Questions?
So thank you for a very interesting talk. So actually I have a question which you didn't cover so much in your talk regarding the generation of terahertz radiation. So it's correct so that there is a terahertz gap where generation of terahertz waves is difficult. Nowadays it's actually not a big deal. So the major issue is that the power of the generated microwave. And can you comment how powerful is your proposed source of the antiferromagnet radiation?
Well, it's a good question. the power, if we are talking about antiferromagnetic device of this kind, the power is determined by two things, by the, I'm sorry, I did something wrong. Just a moment. Yeah, the power is determined by the bias current and by the volume of antiferromagnet. If I increase the volume of the antiferromagnet, I will have higher threshold of excitation. So I will talk about the values of amplitude, of the electric field amplitude, about, well, I would say powers in microwatts.
How much?
Microwatts.
How much? Microwatts?
Microwatt, maybe.
Okay, but it's not much.
So it
would be possible to have milliwatts. Would it be possible to achieve milliwatt?
I doubt it, yeah. It's strongly doubted.
Uh-huh. Okay, thank you.
So microwatts, tunable frequency with microwatts will be a good success.
Okay, very good. Thank you.
More questions? I have a curiosity.
Yeah. Yeah, Vincent want to ask me something.
In your final slide, you say that to increase sensitivity, you can include or insert a magnetic tunnel junction. But then, if I'm not wrong, you have like platinum as a second electrode. So how? I don't.
With sensitivity as in a detector, you see the sensitivity depend. Sensitivity. We assumed that the thickness of antiferromagnet is rather small. It's the thickness of a layer is 30, 40 nanometers, not more than that. In that case, you can get the sensitivity which is good, which is comparable to the sensitivity of GaN diodes or Schottky diodes. So there are no miracles here. Because if you will reduce the volume, you will increase the influence of the noise. And signal to noise should be at least higher than 5. So you can't get, without cooling, the sensitivity higher than, say, several millivolts per microwatt.
My curiosity was answered thanks to the question of Vincent, because I was wondering how thick has to be the antiferromagnet, but you answered.
Yeah. I would like to stress one thing. In contrast with many other projects to generate and receive, we are talking only about generators and receivers which can be continuously tuned. Because it's absolutely no problem to generate terahertz when you, say, have a piece of antiferromagnet and you put an optical femtosecond pulse on it. You will generate continuum. This continuum of frequency will contain terahertz. But how to extract these terahertz, how to select them? You will need a resonant receiver, like what I'm suggesting, or something like that. So it's no problem to generate continuum of frequencies containing terahertz. It's difficult to generate quasi-monochromatic signal in a terahertz frequency range which can be continuously tuned. The same is about the receivers. Bolometers work pretty well, diodes work pretty well, but they are not frequency selective. Thank you.
today about the emerging domain of cryogenic magnon fluxonics. And I have been already asked the first question, what is shown on my title slide. So our group, Superspin Lab, is a part of a larger group, nanomagnetism and magnonics. And in this eye-catcher image, it's just illustration of one of research directions which as a group is concerned. It's a so-called directional magnonic coupler. So the idea is to have two or more magnetic conduits, magnonic conduits, and depending on the operating conditions, geometrical dimensions, magnetic field, one can realize different, so various devices operating, and depending on the propagation of spin waves in one, the second channel, or the combination of it. Okay, so in this conference, we have heard about many interesting directions emerging at the interface between superconductivity and magnetism. I think for more than a decade, one of central topics was spin triplet superconductivity. We have heard about the novel phenomena emerging at microwave frequencies when spin polarized currents in the superconducting state, so dissipation-free transport can be combined with the magnetic state of the ferromagnetic material. Interestingly, so far this domain of magnetism and superconductivity, these developments were more or less not optimally correlated. And at the same time, other groups were interested in adding superconducting materials as much as to modify the propagation of spin waves, for instance, in magnonic conduits to build magnonic metamaterials, because superconductors and ferromagnets are materials which possess the highest, in that sense, magnetic contrast in nature because of ideal diamagnetism, or which can modify the ferromagnetic states strongly. And finally, the very recent years, this boom in going towards quantum magnonics research area, which means operating magnonic circuits at the level of single magnon excitation at low temperatures, at millikelvin temperatures, implies the operation also in presence of superconducting circuits, the presence of qubits. So basically, it's not now a time where magnonics will be combined very intensively with superconducting circuits. And in my talk, I'm going to present you some particular phenomena which emerge when magnonic circuits are combined with superconductors in the mixed state, in the phase with vortices. So basically, the foundation for this is a match of typical length scales. So we will be considering superconducting and magnetic systems, and with particular focus on the periodicity of disturbances, vortex lattice and its motion in superconductors, and propagating collective recessions of magnetic moments in the magnonic materials, so spin waves. So this is illustrated here, so the idea. And the efficient interplay stems from comparable length scales involved. So basically, by tuning the magnetic field, so for instance, between a few, like 2 Tesla and a few millitesla, one can tune the vortex lattice parameter. And for exchange dominated spin waves, we have typical wavelengths of the order of 30 nanometers to 1 micrometers in the dipolar dominated regime. So we can tune between these regimes, and by tuning the periodicity in the vortex lattice, we can adjust to our needs. And in superconductivity and spintronics laboratory, basically we have 2 major research directions. We aim at the extension of our studies into the 3-dimensional space, so 2D structures evolve into the 3D, and magnetic investigations in conjunction with superconductivity obviously require low temperatures. So these research lines have already been presented at this conference yesterday and the day before. They were in the dedicated programs on superconductivity in 3D and cryogenic magnonics. What is missing so far, I'm going to focus at this sector of non-equilibrium superconductivity and fast vortex dynamics as a necessary condition, as a bridge towards cryogenic magnonics in the vortex state. And our superconductivity in spintronics laboratory, it's a group which is integral part of a larger group, non-magnetic and magnetic led by Andrei Chumak. And the results I'm going to present were basically connected with research of PhD student Barbara Budinska on fast vortex dynamics, Sebastian Lang-Camarena, who investigates the propagation of spin waves in direct right conduits, Clement Schmidt investigating the interplay between superconductivity and magnetism. And we benefited strongly from the expertise of Andrei Chumak on spin wave physics and micromagnetic simulations of Chi Wang. Okay, so I will have just a very brief reminder so that we are dealing with a mixed state when we have vortices. At this conference, we have already heard about the modification of magnetic properties of materials in combination with superconductors in the master state. Was a talk by Mikhail Silaev. But I will be concentrating mostly when we have vortices in the superconducting subsystem and the interplay with propagating spin waves in adjacent material. So for us, it's important that the individual building blocks in fluxonics are because of vortices. Yeah, it's a typical sketch where you have the order parameter going down to 0, circulating superconducting current, magnetic field set at maximum, the vortex core. The vortex lattice can be adjusted by the value of the applied magnetic field. And as proven by, for instance, scanning squid on tip microscopy, there is a modulation of the magnetic field induction, so stray field emanating from the vortex core in the presence of the vortex lattice. So basically, this property of the induced modulation of the local magnetic field will be used in our studies where we will be building, for instance, a magnetic crystal on the basis of hybrid system, magnetic conduit in conjunction with a superconducting subsystem. In this case, the presence of the vortex lattice actually is a twofold. Not only the distance between vortices can be adjusted by the variation of the applied magnetic field, but also we can apply a transport current inducing a Magnus-type Lorentz force on the vortex system, and its translational motion would allow the displacement of this vortex lattice in the direction perpendicular to the applied current. And in the presence of such a shifting magnetic crystal template, so to say, we will be able to realize Doppler shifts in the magnetic spectra. So the idea is the following. So the magnetic crystals can be seen as media with a periodic modulation of some magnetic parameter. It can be thickness, width, some anisotropy constant, local magnetic field. And the idea is when the spin wave wavelengths coincides with the periodicity in the system, then because of the destructive interference for reflected spin waves, similar as, for instance, X-rays incident to crystal lattice, this leads to the formation of block-like spectra in such a system. And our experimental observations in this regard were based on cryogenic experiments where we considered a hybrid structure, a permalloy, the typical magnetic material, electrically insulated from a second layer, which is a superconducting film. And to probe the propagation of spin wave, we have one antenna to excite spin waves, another antenna to detect spin waves. A field was applied at a small tilt angle with respect to the plane of the heterostructure to ensure to close to so-called backward volume propagation conditions for spin waves and to have small offset component to induce the required periodicity of the vortex lattice. This sandwich structure was placed in a high-frequency sample holder, and the measurements were done at low temperatures, just in the normal state and the superconducting state of the Nobel film. The key point here is to depart from having a vortex lattice characterized just by periodicity in space and to take a look at the vortex lattice in terms of the inverse quantity. So you have the vortex lattice period, which can be converted to the reciprocal quantity, which is a wave vector, which can be introduced to the Brikosov vortex lattice. Also, having a higher order, for instance, like for break reflection, you can have peaks of first order, second order, and so on. So basically, this feature, periodic media, allows one to induce particular band gaps in the spin wave transmission spectra. So first we have a reference measurement. We have a dome for propagation of spin waves without any significant features. A reference measurement is a black line. On the right-hand side, it is limited by the ferromagnetic resonance frequency. On the left-hand side, it is limited by the finite antenna width because we are not able to excite spin waves with wavelengths shorter than the double width of the antenna. Then, when the sample transits in this superconducting state, we see here a series of minima emerging in the transmission spectrum. And these positions of this minima can be tuned by tuning the magnetic field or by the variation of the period of the vortex lattice. And the stitching point is actually the dispersion of spin waves, which can be calculated for such magnonic conduits. And at the intersects of these lines corresponding to the observed minima, it is possible to merge them to particular wave vector number, which corresponds to a vortex lattice realized at these conditions. So generalizing this to a wider range of magnetic fields, it's possible to continuously tune the observed band gaps in the magnon frequency spectrum, and moreover, to tune the location by the application of a current. So the current voltage curve of a superconductor is known to be strongly nonlinear, with a vortex spinning regime, with a close to flux flow regime, when we have a quasi-linear vortex motion as a function of the driving force given by the current, and the nonlinear transition in between. Here there are overlaps of two branches, ascending branches and descending branches. It's a superposition of two plots measured under current polarity reversal. And because of the very particular dispersion relation for spin waves in this geometry, which is characterized by negative group velocity, so the slope here, the derivative is negative, we have an increase of the frequency because of the Doppler effect for co-propagating in the same direction vortices and spin waves, and opposite trend when we change the current polarity. I will skip the details concerning the Doppler effect and would like to mention here that so far most of experiments have been done in the so-called long wavelength limit corresponding to the dipolar dominated spin waves. But when people talk about nanomagnonic devices, it would be preferable to have spin waves with shorter wavelengths, so-called exchange spin waves. They're characterized by shorter wavelengths. They're very close to quadratic dispersion relation, and having a particular structure in the submicrometer range, one would have lots of spin wavelengths on a length interval to operate with these weights. However, the standard approach for the excitation of spin waves by using antennas, so inductive excitation and detection of spin waves, becomes less efficient because of the technological restriction imposed on the fabrication of antennas at such dimensions. Typical what you would like to have, you apply a high frequency current because of the Ørsted field component oscillating around this wire. You have a maximum, minimum, and so on. So the wavelength excited by such an antenna is limited here, so by the doubled width. So it's very difficult to go below, for instance, 100, 70, 60, 50 nanometers, and so on. But in principle, because of its just general wave phenomena in nature, one can think about completely different approaches which are complementary to this inductive, so just to change the paradigm in that sense that waves can be excited by many different waves. And in particular, you might think about the generation of gravity fluids, just water waves, if you have properly placed sources of mechanical perturbation. So basically proceeding from the waves of water to waves in the magnetized systems, what you need to do, you need to have a periodic lattice of magnetic sources. And the crucial condition here that the velocity of these sources should reach the phase velocity of the propagating spin wave in the system according to the dispersion of relation. So meaning that in system, these spin waves should exist, should be possible at these operating conditions. And it's interesting to take a look. I have an outline of works, 2 of them stemming from the magnetism community, 3 of them stemming from the superconductivity community. I'm talking about the Cherenkov type generation of spin waves, which were so far never considered in combination. So basically, there was not much communications with different sub-communities. So in magnetism, people were missing propagating sources which could be used for the generation of spin waves. Here is a theoretical work where one propagating magnetic pulse was used to theoretically predict the generation of one spin wave in front of the object and one behind them with two different wavelengths. And here in superconducting systems, people consider the lattice of periodically placed magnetic objects, vortices. But this was not possible because of actually one severe limitation I'm going to talk in detail. And the distinctive feature of this type of generation would be when we have an array of periodically placed sources, then you will have only one particular wavelength of the generated spin wave in front, because the other wavelengths will be cancelled because of destructive interference. So the crucial condition here, Cherenkov resonance condition, implies that if working with exchange wave, we have a parabolic dispersion, and our vortex lattice, in this case with superconducting vortex, is characterized by linear dispersion. So we need to bring this dispersion curve to some intersection point, and when the condition is satisfied, frequency of spin waves is equal to the washboard frequency of the vortex lattice. Upon the match of wave vectors, we expect a Cherenkov resonance condition. So the idea is good. Implementation is a severe challenge, because these velocities, you see that the slope is very steep, and our sources should be at very high velocities, typical in the kilometer per second range. And we are talking about a vortex lattice which approaches the so-called instability point because of the Larkinov-Chinnikov instability mechanism. So we need to enhance speed limits to the vortex dynamics, and the microscopic mechanism is associated that the quasi-particles escape from the vortex core. You see here a vortex core at rest with many, many electrons in normal state. Then at very high velocities, the kinetic energy becomes comparable with the potential energy of the order parameter variation inside and outside the vortex core. So the electrons escape, the vortex core shrinks, and this leads to an abrupt jump to the normally conducting state much before we reach the dependent current given by the Ginzburg and Landau theory. So basically, approaches can be elaborated looking at the time-dependent Ginzburg-Landau simulations. So you see that instead of having a periodically arranged system of vortices, we need to have a long-range order to work with the perfectly periodic vortex lattice. Close to the instability point, we have a strong deviation from this long-range ordered vortex lattice. And we have deviations both along the edge, most crucial point where instability is nucleating, these blue spots, and the deviation from the long-range order in the volume of the center. So two strategies then can be taken, and we can operate with collective effects, trying to order the moving vortex lattice, or better, to suppress the nucleation of a flux law instability via the edge barrier engineering. Both approaches can be used in our studies, and one of them was the use of a guiding effect, so that if you have a system of unordered moving particles, by adding a parallel system of periodically placed guiding rails, it is possible to bring some ordering into the system and thereby to reach higher velocities. This is just a superconducting film with such guiding rails, which act as a stabilizer. Like for instance, for a bullet, you would, I think, immediately recognize that it is stable, and this actually experimental observation has allowed it to enhance the spin limit a factor of 3 to 5 to be already in the kilometers per second range. However, superconductors have been in moderately clean superconducting limit, and for clean superconductors, we are limited by the range of magnetic fields available. We are not able to operate at higher magnetic fields, and relaxation processes are rather long. So we need to find a way to elaborate a superconductor in a dirty limit, and for this particular requirement, we can apply a direct right nanofabrication technique based on a dual beam instrument, in which we can use focused ion beam and electron beam induced deposition, as already demonstrated in a series of talks at this conference. This particular example is a fabrication of a sensitive element where the resistance of a deposit can be tuned around insulator normally conducting metal behavior. And under the action of the focused ion beam, because of the capillary, we have the possibility to inject a precursor gas in the vicinity of a structure where we'd like to fabricate our sample. You see here molecules from the precursor gas, they are shaken because of thermal diffusion. So ideally, once the complete layer is covered by these molecules, then according to your template, you pass the beam, you let the beam to pass and to decompose these molecules into permanent deposit, which forms your material, and volatile components, which are pumped away. So in this case, it was possible to fabricate superconductors with extremely fast relaxation of electrons behind the vortex cores, because it is far in the duty limit because of the presence of carbon and oxygen in the system. And in principle, even exceed 10 kilometers per second vortex velocities at low magnetic fields, while being above 3 kilometers per second in the regime of high fields. So this system is also suitable and interesting for potential use in superconducting single photon detectors, being compatible in the entire metric of interesting parameters for that. But I am now going to present some details related to the magnonics applications. So this is a particular example how it was fabricated. In blue, you see the layer which is composed from the superconductor and the duty limit. On top of it, you see a direct write material in violet, which is insulating, just to avoid direct proximity effect to the ferromagnetic structure. And the cobalt iron-based deposit is nanoprinted on top of that. And what we are doing, we apply a transport current along the superconducting bridge. We can control the voltages usually. And when the Cherenkov resonance condition is realized, then the vortex lattice present in this region generates a spin wave which propagates from here along the magnonic conduit and is detected by the so-called ladder antenna tuned to its third harmonics. Because of the short wavelengths, we are talking about 36 nanometer, which correspond to the third harmonic of the periodicity of 108 nanometer periodic antenna. So experimental observations are twofold. First, we have the possibility to detect these spin waves directly by connecting a spectrum analyzer in the gigahertz frequency range, just depending on the current bias. When we are in the spin wave generation regime, we directly observe the propagating spin waves. But what is also interesting, in the current voltage curve of a superconductor, we have a very well-defined plateaus just before the instability jumps. And for those who are working with superconducting systems, I mean here both Abrikosov and Josephson systems, appearance of such plateaus are very similar to what is called Shapiro steps for Josephson junctions. And that means that in some similarity to the Josephson generation, in that case we generate magnons, and the presence of this constant voltage plateaus means that we have pumping of energy from the superconducting system, which is spent on the generation of magnons in the magnetic subsystem. Even more interesting is that if we properly represent the generated the voltage at the magnon Shapiro step, and divided by the flux quanta, the frequency of the spin wave, and the number of participating vortices, this is very similar to what people see for Josephson junction. Just the difference is that we just need to take into account how many vortices are in a row and contribute to the coherent generation of a spin waves which propagates in a particular direction. So basically what we have here, we have exactly one magnetic flux quanta. If we link the voltage at the current voltage curve of superconductor to the frequency of the generated spin wave. Another interesting consequence is that the instability points themselves, you see here the comparison of the maximal vortex velocities without radiation of magnons, about 1.55 kilometers per second, are also slightly increasing with the generation of magnets. So basically, the mechanism behind that is since the energy is pumped away from the superconductor magnetic subsystem, we can reach even higher velocities, and this actually is a long sought for interesting mechanism for the so-called dynamic pinning. Micromagnetic simulations corroborate the principal messages of this observation. We see here the hybrid region of superconductor ferromagnet-based structure with very interesting properties. We just apply a DC current, and we see an unidirectional excitation of spin waves. It's a very similar, what we could call, for instance, a beam. So spin wave beam propagating to a particular direction, or like a spin wave torch, whose direction is determined by the polarity of the applied current. This excitation is monochromatic because the spin wave vector matches the wave vector, or just reciprocal of the abrikosa vortex lattice. And this excitation is coherent. Here it's stated shock wave protected phase, but if one takes a look at the time-dependent Gisbel-Hamdau simulation for vortices which emit a spin wave, the back action of the generated spin wave onto the vortex lattice improves the long-range order of the vortex lattice in the superconductor. So it means that there is also collective dynamic ordering effect of because of the self-locking of the generation of spin wave with the periodicity of the vortex lattice itself. Concerning the dynamic pinning mechanism, it was actually predicted a decade ago, and the idea is for system of ordered or unordered moving sources, if you have a situation when the energy is pumped away in a coherent fashion to trigger the motion of a different object, then there is a kind of efficient cooling down of the superconducting system. And for such high frequency, high velocity regime, it's possible to compare the voltage for a reference sample with sample where we have the magnetic excitation. I'm talking now about the case when we see 2 or Shapiro steps, so higher order Shapiro step. One can even estimate a power which is pumped from the superconductor to spent for the excitation of spin wave. Okay, so finally interesting remark is on the wavelengths of the generated magnons. So for good 5 years, it was a hot topic in the magnonics community how to generate short wavelength magnons with wavelengths reported in terms of the wave number. If we take a look at these numbers and compare with wavelengths we have in our experiments, so at least a factor of 2 enhancement can be reached just because of the shift of the paradigm time of excitation of spin waves now by the Cherenkov-like generation mechanism. I think at this point I'm approaching the summary of my talk. The ultra-fast dynamics of vortices has been realized in the dirty limit superconductors with velocities now exceeding 10 kilometers per second. We experimentally observed the Magnon-Cherenkov-like generation of spin waves with interesting features like Magnon-Shapiro steps, or self-locking of fluxons and magnons in high-velocity dynamic regimes. And to my knowledge, so far we have observed in such a way shortest wavelengths magnons. And the missing in this triad generation manipulation is detection. We are currently working on at low temperatures, and this represents one of the main subjects in our current project on fluxon magnonics in collaboration with our Polish and Czech colleagues. And I would like to thank you and all my colleagues for the contribution to this work. Yeah.
Thank you. The talk is open for discussion. Please, take the microphone.
Well, I understand that by changing the magnetic field, you can change the periodicity of a fluxon structure. And so you can presumably get the dispersion law of generated spin waves and check whether it's quadratic or not.
Yes.
Did you do that?
Actually, not yet, but I would assume that the limiting range of parameters, first of all, it's a upper critical field for the superconductor, and the parameter here is size of the vortex core. So typically this type of spectroscopy could go up to 1 hour Xi in size, which the dirtier the superconductor is, would allow you to reach the deep exchange regime. So to say, with limitation, probably for high TC superconductors could be in the sub-nanometer range, which is also compatible with their frequencies. Sub-terahertz frequencies can be reached, which is still below the superconducting energy gap for high TC materials.
The only thing I can say that the work is excellent. I'm impressed.
Thank you very much.
Thank you for the nice talk. I just have a technical question. And the first work that you presented with the two antennas, there is a platinum layer over the ferromagnet. So is it necessary for something, or
no?
So it's just making
We
dumping worse,
didn't
no?
know whether we be able to see the trick here. So that experiment was planned many years ago and successfully realized after 2 years of trials and fails. We expected to see some spintronic phenomena because of the presence of that platinum layer, but the same phenomena are there if you replace the platinum oxide with just silicon oxide. So for us, it just was important to have some spacer. We are not talking about proximite system, so it's just stray field coupled regime. Doesn't matter which type of insulator you would take for that. Idea was a crucial issue to have a superconductor where you have a very long range order of the vortex lattice. And this can be achieved on one limiting case. If you have a like almost perfect superconductor like niobium epitaxial films, which is an issue how to fabricate them because spinning of vortices is strong typically in niobium. But you then limit it to the low field range. Or very dirty superconductors, but they have magnetic penetration depths, which is huge. But then you have to apply it to Tesla, and for the Tesla field, you have a very, very small separation between the vortex lattice is very dense, and then it is very well ordered because they are just repulsively interacting with each other and are arranged in the lattice. The oxide is, in that case, was just, we had a series of samples with this oxide.
Yeah, okay. Then the second question, you are not using any proximity effects, so you can use insulators, for example, for the spin waves.
Yeah, this is the goal of the project. So I have shown that yes, we are going to have this hybridization, and there are some interesting materials which are at the same time superconducting and ferromagnetic at low temperatures. So combine two types of orders, and you don't need to build something artificially, but it's a materials engineering. So actually from the very beginning.
Okay, so this is indeed a very interesting and delicate work. But if one thinks of possible, say, practical application, where these spin waves with very ultra-short wavelengths could be good for?
Well, of course, when people talk about magnonics, they have in mind room temperature applications. But for room temperature magnonics, there are no, as far as I see the developments in the community, not many waves to have just from shelf exchange dominated spin waves. It's still quite challenging. So basically analyzing the basic properties, non-linearities, dispersion, different modes and interactions, this is like a model system. But if we are going towards what is called quantum magnonics or low temperature magnonics, then just for basic research, maybe for emerging technologies, it would also be relevant because vortices are in coplanar waveguides and resonators everywhere, which is coupled to this type of magnonic conduits. But I cannot foresee all possible aspects at this stage yet.
1 second. We have another question over there, and then I will return to you.
Maybe I missed something, but your current distribution is not uniform in your driving current is the current distribution is not uniform along the film, right? Because you're in thin film. I'm saying this because then I would not expect the vortex spacing to be like the speed would not be uniform.
No.
Across.
So basically in the Meissner's test, yes, the current will just go along the perimeter. But once you have vortices, the presence of vortices is known to bring the system to a more or less uniform distribution of current. So basically the contribution of the deviation from this uniformity, so to say, at the edge is negligibly small with respect to what is happening in the volume. This can be proved by both time-dependent Ginzburg-Landau and LLG simulations in conjunction with the time-dependent Ginzburg-Landau. Or maybe experimentally, having your technique.
Sure.
Yeah.
But okay. Maybe we should discuss
For that
this.
reason we discussed this.
Sure.
Okay, we have one more question here.
Well, it's no not so much a question as a comment. I would like to say that the short spin waves are really useful in conventional magnonics for one simple reason. Conventional magnonics is done with thin films. So the in-plane propagation distances are of the order of hundreds of nanometers. But the group velocity of long spin waves is proportional to the thickness of the film, so it's very low. In exchange spin waves, they have group velocity which is proportional to the wave number and to the magnetization. And so you can get waves with large group velocity which can actually carry energy without big spatial losses. So it's very important. But we need cryogenics here, so it's not really practical. But in principle, generation of short spin waves is very, very important for signal processing. Thank you.
Okay, thank you for your comment. Are there any further questions or comments? If no, I would like to thank Professor Dobrovolsky for his excellent talk and to give him, on behalf of the organizers, a certificate as a half plenary speaker.
Thank you very much.
We are punctual, just 40 minutes. Thank you very much. Thank you all. And in 10 minutes, there will be a continuation.
session on novel spin-dependent phenomena in 2D materials and heterostructures. And the first paper in this session will be presented by Oleg Yeziev from École Polytechnique Fédérale de Lausanne, Switzerland. Please.
Okay, good afternoon, everyone. I hope everyone hears me well with this little microphone. So, first of all, big thanks to the organizers of this conference and could you bring it back? And of this session, in particular, Ahmed. So I will give a, let's say, an overview talk, but I mean with our own contributions that covers transition metal Dutch chalcogenides. We heard already quite a bit today about the spin momentum locking in TMDs, about the proximity effect. So my talk is going to be slightly more general, and I would like to start. Okay, I guess the battery is dying, but sometimes it's working, sometimes it's on. This is, yeah, okay, actually. For me, this is forward and this is backward. Depends on how you turn the fan. Yeah, I would like to start by showing this this diagram that we drew for the review article we published together with Andras Kish already like 5 years ago. And this is, let's say, yet another periodic table of TMDs, where in this periodic table we see one of the transition metals that you normally encounter in these layered materials, as long as they have real layered structure. And then the chalcogen is sulfur, selenium, tellurium. And then, okay, so here's, for example, molybdenum and tungsten, and the effective configuration would be D2. So basically, effectively, 2D electrons if you assume all formal charge of the transition metal ion of 4+. And then what you can see in this diagram, okay, first of all, they exist normally in two polymorphs. If you throw away all the distortions, this is H or T polymorph, so they have different coordinations. So let's say was taken with the 3 atomic planes. So for some of them, like for example for molybdenum and for tungsten, both of them can be realized coexist. But normally the T phase would be would somehow prevail. And then some of these materials, metallic, some are insulating. They show distortions on top of this basic polymorph, so maybe charge density waves. Some of them show superconductivity. Some of them have topological phases. So this is what we had back then. But of course, I mean that's not it. I mean then came the issue of magnetism. There was the long-standing discussion on vanadium dicyanide. I mean, probably not valid anymore, so I'm not going to discuss. But I would like to show a little bit on the platinum dicyanide. So the magnetic phase is also kind of relevant to this method. And my talk will go like this. I'll first discuss the structure, then the quantum spin Hall oscillator phase in tungsten dicyanide 1T prime phase, and also the magnetism and magneto-resistive switching in interesting mechanism in platinum dicyanide. Okay. Now, of course, the thanks go to my 3 PhD students. All of them by now left my group, and one of the postdocs also left the group, and number of experimental collaborators. Again, Ahmed is in the audience, and and some funding sources. Okay, so now this is forward. Now, so the simplest question we can ask after looking at this periodic table is, let's say, what defines the relative stability of these H and T phases? Why, for example, for molybdenum and tungsten, the chalcogenides, typically the H phase would be more stable. For the other ones, the T phase is more stable. And this is actually a long-standing discussion in chemistry and physics and material science. So, for example, I mean, I'm a theorist, I don't do any experiments. We can, for example, do calculations, I mean, calculate relative stability using DFT for undistorted phases, and then basically this is the form of the occupation, so that's where the molybdenum and tungsten would be. This is the relative stability of 1T and 1H phases, so they're just the energy difference. And you find this extremely nice diagram. Doesn't matter if you are talking about 4D or 5D transition method that you could use. And typically, let's say the qualitative explanation will go the following. Okay, we put our ion in some kind of coordination sphere. It would be different for these two polymers. The distorted octahedral for the T phase and trigonal prismatic for the H phase. And then, okay, so here's your splitting of the D levels. So in the octahedral it would be G to G, everyone knows. In the trigonal prismatic it would be this kind of 3. Okay, so it would be the following. At the bottom you would have one non-degenerate level, so that that nicely accommodates two electrons, and that's why basically molybdenum and tungsten materials would somehow be more stable. Now, of course, this is all qualitative. How can I put this, for example, to level diagrams on the common energy scale? Can I put any kind of numbers? And then first of all, okay, I mentioned here crystal field argument. Crystal field or ligand field. So crystal field is basically ionic bonding, purely like electrostatic effects. Ligand field would be covalent bonding. So can we argue which one is more important and how exactly this works? Now, of course, I mean, once again, we are going to do calculations, and typically, in physics, you would calculate bond structures, the momentum space representation, which is not very useful if you want to discuss chemical bonding, because chemical bonding is all about the real space representation. That's where our chemical intuition lies, and that basically means that we have to deal with Wannier states instead of the Bloch states, right? Well, one is related to another simply by Fourier transform, but if you act in a multi-orbital space, there is this gauge fixing matrix that gives you many degrees of freedom. Now, so the degree of freedom I will be talking about is we are going to construct this matrix, I mean, according to this formula. So we are speaking about projector Wannier functions. So those would be, let's say, localized atomic orbitals, or functions that resemble them. And then basically you do this Wannierization, you do this procedure, you express your Hamiltonian in the basis set of this Wannier states, and then of course from the diagonal matrix elements of your Hamiltonian you can get all these level diagrams. I mean, the on-site energies, all the crystal field and ligand field effects. And importantly, I can also change let's say the space of the bands I'm going to use for this procedure, and that allows us to separate contributions of ligand and crystal field effects and maybe some other contributions. So this is not us who invented this. This comes from the paper from the group of Nicholas Paulding now in Zurich. Okay, so now the chalcogenide is actually very simple. So that's how the band structure. So for example, tantalum disulfide would look like. So these are S states of the sulfur atoms, these are pi states, this would be d orbitals. I mean, they're nicely separated, so you can easily choose which bands you want to treat. And typically, I would speak about 5-band model. I mean, if I'm taking only the d levels of the transition metal ions, I can also include the p levels of our chalcogenide, and so that would be 11-band model. And if I include now s orbitals of the chalcogenide, that would be a 13-band model. Now I do this Wannierization, and for the largest, for the 13-band model, I find, for example, these Wannier functions, I mean, that resemble closely the let's say simply atomic d orbitals of my transition metal atoms, right? So essentially, in this case, this means that what I extract from my Hamiltonian only the crystal field effects, because there is nothing sitting on the chalcogenide atom. So this is purely electrostatics. Now, if I reduce the orbital space, I go to 11 and to 5 d orbital. I'm progressively including the hybridization effects or the ligand field effects. Okay, so now let's look at the same if I take edge phase, just that, I mean, let's say I'm rotating the frame, but it's also true that I'm going to get totally different numbers. Now, if I now see what I actually get, so this is the 13-band model, so only the crystal field effects. So I mean, this diagram doesn't resemble what I drew before for the qualitative picture, but then as I'm reducing, as I'm going basically as I'm including the ligand field effects, I'm going to get this diagram. So that already fits our qualitative expectations. Now there is actually, and that would already allow us to argue somehow that the edge phase must be more stable. So this level is somehow below that one. We are discussing the common energy scale. But then there is another subtle thing. It actually happens that if you look at this d-band manifold, there is a kind of thing that resembles an avoided crossing. So there is an extra effect of hybridization that we didn't include so far, that we didn't discuss, and actually we can now take this as a separate manifold of Wannierization. And for that one, and we actually figure out that, so the contribution we are separating in this case is intersite hybridization. So d electrons on one atom, something that basically related to the dz square orbital, talking to the other side, not through the ligands but directly. And this is actually now modifying this diagram even more. So you can see that this level goes down by a lot. So, and this is actually, let's say, probably the largest contribution that determines why the edge phase is more stable for molybdenum and for tungsten dichalcogenides. Okay, so then we can of course discuss how this changes across the horizontal dimension of the periodic table. We can build some chemical intuition. I mean, just from these plots we can build a very nice discussion, but I'm not going to go into that. So, brief conclusions, but I guess we have to move on. Now, what's next? Well, okay, so these are, let's say, basic and distorted phases. What is superimposed onto this H and T phases is sometimes the charge density waves. Okay, the same 1T tantalum disulfide is a classical charge density wave material. Everyone knows, so it undergoes this kind of reconstruction into the David star distortion. If you go to the right in the periodic table, so you go to molybdenum tungsten, then typically for the T phase you have this kind of the dimer line pattern. So this is known under the name of 1T prime phase. You go one cell right in the periodic table, so those would be rhenium dichalcogenides, and then there you have this kind of tetramers, so the diamonds, and this is known under the name 1T prime prime phase. So this is 2x1 reconstruction, and this is 2x2. Okay, so what governs this? Because here in the charge density wave we also have atomic displacements, but they're actually very minor. Let's say tenths of an angstrom. Here we are speaking about a fair fraction of angstrom for the displacement of atoms. So these are very strong effects. Okay, and of course this is also discussed since long time in the literature somehow separately for these two scenarios. We just decided to put this on, let's say, on the common ground to devise a unified theory. And of course, let's say for charge density waves, you will discuss some Peierls instability, some kind of a Fermi surface nesting, arguments like this. In the other case, you would probably start thinking about chemical bonding, because that's what basically moves the ions a lot in our lattice. So okay, we just decided to look at everything together. And then, okay, so once again, what are you going to do? You're going to do DFT calculations. If you want to study the distortion, you need to first address what happens with the undistorted phase. Now, what I'm doing here, I'm basically taking 1T phases of tantalum sulfide, tungsten sulfide, rhenium sulfide, so I'm just moving to the right in the periodic table, and these are the band structures. And they actually look very similar, apart from the fact that the Fermi level is kind of moving up simply because you're adding 1D electron with each step. Now, what I'm showing in these plots are the bare susceptibility. So let's say the electronic driving force of the distortion. And what I'm also showing here, I mean, so there are several curves. This is because the black curve corresponds to just normal tantalum disulfide, and the colored curves correspond to the cases when I'm basically removing some D electrons. So I'm actually charging the system. And computations, I can, of course, do this easily. And what I see is that, okay, I mean, as I'm filling my D shell, so I'm moving from here to there. Let's say I have a peak in the susceptibility. It moves to the right, and then, I mean, very quickly, I mean, I'm doing the same also for these materials. It goes, let's say, to the Brillouin zone boundary, to something that is and kind of disappears. So, I mean, this looks pretty flat, right? So there is no really kind of driving force that would give you well-defined periodicity. If I look, so this would be the phonon dispersion curves, and these are imaginary frequencies, right? So these are soft modes that drive actually this lattice instability. And you can actually see that, okay, so for example, for tantalum materials, the position of the soft modes, the minimum corresponds well to the maximum in the susceptibility. So, okay, so this is Fermi surface nesting, works perfectly in this case. Then it moves further to the right, it goes to the Brillouin zone boundary, and essentially, I mean, stays there. So pretty featureless. But the only thing you can say is that in this case there is a strong propensity towards doubling of the unit cell. So T prime, T prime prime, 2x1 or 2x2, and this is not really clearly related somehow to the susceptibility. So susceptibility is featureless. Now, of course, I mean, at this point, okay, so let's say the band structure arguments don't work anymore. We have to look at the chemical bonding. And we are going to do exactly the same as we did before with this one-year function methodology, but now instead of the undistorted phases, we are going to study the distorted phases. And what happens is that, okay, so if the undistorted phase of the 1T prime would be the normal T2G, triply degenerate, EG doubly degenerate, so I mean that's why you are putting your electrons. So once you basically distort the phase in 1T prime, so you have this dimer chains, you instead of these three triply degenerate orbital times 2, so times 2 atoms per this doubled unit cell, you're going to get bonding, anti-bonding, and non-bonding states, and the bonding states would be fully populated. Okay, so this is a chemical bond argument, so that's how basically the 1 orbital would look like. So this is really a chemical bond between these metal atoms, and the argument is very simple. You have basically this dimer chain, which means that each metal atom has two nearest neighbors after this distortion. So two electrons that make two chemical bonds. Very simple. You do the same for the rhenium disulfide, so now you have 3D electrons. The distortion works in different way. Now you have only bonding and anti-bonding states. All the bonding states once again completely filled, and the counting argument gives you the same equation. Now each of the metal atoms in this particular arrangement creates 3 metal-metal bonds. Very simple chemistry. Okay, so basically that sort of kind of tells us is that okay, there are two distinct regimes, weak and strong coupling. So for one of them the Fermi surface nesting works. The other one is more like driven by the chemical bonding, and we understand what are these chemical bonds. So we basically can control this even by doping. So probably someone would experimentally try to do this with liquid with ion liquid gating or something like that. I mean, would be interesting to see. Okay, now topological phases. So now we are coming to the 1T prime phase of molybdenum and tungsten, the chalcogenides. And I'm not going to give a long introduction on the field of topological materials. So this is basically the timeline since 2005 until 2016. Everything beyond is irrelevant to this talk. But what is important is started with the quantum spin Hall effect. So when the first topological phase that was intrinsically observed in materials after theoretical suggestions. So the mercury telluride quantum wells would be the first system. Then came three-dimensional Z2 topological insulators like bismuth slide, bismuth telluride. And the interesting thing is that for a long time, let's say the 2D systems would be represented only by these quantum well systems, which are actually tricky to handle and tricky to manufacture. So the big question in the community would be, let's say, can we find a very good two-dimensional quantum spin Hall insulator? So basically, once again, what is quantum spin Hall insulator? In a K space, it would be a gapped material, so there would be a band gap, but on the edges, on the boundaries, you would have topologically protected modes. So this would be for spin up and for spin down, so they would be counter-propagating, and they're related to each other by time reversal symmetry. So if you change momentum, you also have to flip the spin. And then, basically, in real space, you would have, let's say, the edge states would correspond to counter-propagating, let's say, currents of the opposite spin. Okay. So now, let's say, theory aside, there is one simple formula that allows you to calculate this the so-called topological invariant, this number nu, that is Z2, which means 0, 1. So this is really like binary space. And all what you need to know, basically, you need to know the parities of the populated states at the time reversal invariant momentum point. So if you are, for example, discussing 2D materials, there would be 4 time reversal invariant momentum points. So you basically calculate one product, another, and then if it's minus 1 or 1, you're saying if it's topological or topologically trivial. Okay, so, and then basically, that also already gives you a recipe where to look for such materials. Well, that must be a band inversion material because you must exchange parities of the two bands around one of these time reversal invariant momentum points, but you need a mechanism to open the gap, and this mechanism is the spin-orbit interaction. Okay, so spin orbit materials hopefully with strong spin orbit and with band inversion. Well, historically, the first real proposal for the quantum spin Hall effect is graphene, and graphene is a quantum spin Hall insulator. But as it was already mentioned in the talks today, there is one big problem with graphene. Carbon is number 6 in the periodic table, so spin orbit interactions are very weak, and basically the gaps we are discussing are of the order of 10 to minus 5 electron volt. Impossible to measure unless you do kind of proximity effects to enhance spin orbit interactions, and absolutely useful for any kind of practical applications. So you need another material. And there was actually a very bright theoretical prediction that, I mean, 1T prime phase of the chalcogenides of molybdenum tungsten must be such materials. So this was a paper published in Science. It was purely theoretical. Exactly this mechanism of band inversion, small gap opening due to spin orbit, exactly, I mean, like in the cartoon I showed to you. So that was 2014. In 2017, there was, let's say, first two papers that would demonstrate this experimentally. And surprisingly, in in tungsten ditelluride 1T prime phase, and this is simply because it happens that this 1T prime distortion is so strong that it makes this phase thermodynamically more stable. Okay?
Like 3 minutes.
3 minutes only. No, hold on. I started at 50, so this is 20 now.
Oh, yeah, sorry. 7.
Okay, so what people would do, they would measure the band gap, would be something like 50 millielectron volt, already not bad, at least measurable. So this comes from the angle resolved photoemission spectroscopy. These are the transport measurements, so they do observe quantization. And the material I would be talking about is instead 1T prime phase of tungsten diselenide. Okay, simply because I was involved in this work. And in this case, now 1T prime phase is metastable. 1H phase is stable. But that also means that, okay, so what was done, people would do CVD growth of, no, this was MBE growth on silicon carbide on graphene substrate of tungsten diselenide. Let's say these two phases are close in energy, so the majority would be 1H phase, so insulators thermodynamically stable, but there would be still kind of islands of the 1T prime phase metastable. So that's how it would look like in STM measurements, and there would be interfaces between the two. Now, note that the interface is super nice, yeah? And the edges are kind of mostly very ugly. So once again, even on these small islands, you can do some kind of nano ARPAs. So you do observe the band structure you would predict theoretically. So in this case, it would be 120 millielectron volts of the gap, a little bit better, which is good. So again, pretty much the same from the scanning tunneling spectroscopy measurements. So that's how in STM the interfaces would look like. So 1T prime phase, you know, you have this dimer walls. This is 1H phase. 1H phase has a gap, 1T prime phase has a very small gap. But it's topological, which is important. And we don't quite know what happens here. So there is no really atomic resolution to tell you how exactly the atoms are arranged. But you can already see that there is a difference, I mean, at the interface and within the bulk between the tunneling spectra. And we, of course, as series, we try to devise a model of the interface that would basically somehow local density of states would resemble as close as possible this very much broadened experimental pictures. And this was basically one of the structures, possible structures that we thought is relevant. And now if you look at okay, so here the contrast is not very good. So there must be gray areas that represent projected bulk valence band, and this will be the conduction band. And what is shown is in red and blue are these edge states that are spin resolved, so color coded. And you see, so the topological states, they must connect the conduction band with the valence band. So these are these two. But and the gap would be somewhere here. So, and there are also two pairs of topologically trivial states that do extend in the gap, so they actually spoil everything. They show a little bit of this kind of Rashba splitting. But this is reality, right? So reality is not just ideal crossing of two bands, like a zero cone-like feature. The reality in these materials is much worse. Okay, so what we also did, we also studied the domains between 1T prime and T prime, so two topological phases, simply because the mineralization direction changes. Nothing interesting there. And we also do observe sometimes nice edges of the 1T prime phase. So this is really the edge that runs along the mineralization direction. Well, you would expect. Maybe for the edge states, we would find very nice quantum spin Hall edge states. That would be separated from the topologically trivial states in the gap. The reality is unfortunately not that simple. So basically, there are again many different structures possible for each of the material. And for each structure, you can calculate the band dispersions. And without basically trying to understand what is in these pictures, there are only two cases that look promising. Both of them are tungsten dichalcogenide, so the stoichiometric or the chalcogen-rich edge. And basically, if you do close up, so this would be the gap, and the quantum spin Hall edge states would look like this. So there is indeed some small energy range when they're separated from everything. Okay, so finally I will spend probably 3 minutes on magnetism in platinum diselenide. And platinum diselenide as a bulk material is not interesting at all. So this is a absolutely non-magnetic semi-metal. So those would be electron pockets, and this would be Hall pocket. If you thin it down to a few layers, it becomes insulator. So you're opening a gap, but already from something like 3 to 5 layers, you're closing the gap also experimentally. So nothing magnetic. Nevertheless, what was done in the group of Andras by Ahmed, so he's the first author here, is that they would make different devices, let's say, of many such layers, so those would be metallic, and for these devices they would observe magnet-resistive switching. So basically this would be resistivity as a function of magnetic field, and some of these devices, they would have different thickness. Some of them would show ferromagnetic zero field configuration, and some of them would be anti-ferromagnetic. So FM is red, and the black is ferromagnetic. So they're changing, right? I mean, depending on the thickness, you're going to get one and another. So how do you explain this? And our explanation is that, okay, so I mean, there is some kind of oscillating coupling. I mean, that tells us that probably RKTY coupling plays a role here. And now we are speaking about two, it's really like a giant magnet-resistive junction. So you have two magnetic surfaces in this case, and non-magnetic metallic bulk in between. So what makes the surfaces magnetic is the fact that, I mean, there are plenty of defects in this material, in particular platinum vacancies. But according to the calculations, it happened that platinum vacancy in the bulk of the material would be non-magnetic, but when it's on the surface, it becomes magnetic. So interactions are actually very important in this material. And then you would say, okay, so if there are pockets that couple the, let's say, itinerant electrons that couple these two surfaces come from the pocket that is at the beryllium zone boundary, you would have periodicity that is basically of two layers that oscillates between ferromagnetic and antiferromagnetic. And then when the thing gets thick enough, this layer, I mean, you would, of course, vanish the coupling. So there would be no magnet-resistive switching. So altogether, you would say, okay, so there is, for example, this was just a cartoon for the journal, antiferromagnetic coupling. In this part, then you basically add another layer, and you would have ferromagnetic coupling between the two magnetic surfaces, so spin sleeve on this surface. Okay, so just last slide to show that when you go to monolar, everything changes once again, because monolar, you basically take in one layer, and there is no bulk on both sides anymore. And the ground state of this one actually happens to be antiferromagnetic of this defect, but monolar is a bit special. Okay, with this, I think I have to wrap up my talk, showing again the persons whom I would like to thank for doing this work, my students, and Shanshan, my postdoc, and you for your attention.
Thank you. Paper is now open for discussion. Question?
Thank you for a very nice talk. So just the last slide when you show magnetism for platinum dicyanide.
For the monolayer.
Yeah. So in this case, it's like you believe that, like, I mean, platinum vacancies that contribute more to the magnetism, right? On the other hand, like 1T vanadium dicyanide also known to show the magnetism as well. In that system, they show that, like, selenium's vacancies actually contribute to spin polarized magnetism in the system. So,
but compared to vanadium materials and platinum, the chalcogenides are very different. So if you look in the periodic table, I mean, it's so much to the right, it doesn't resemble all this, let's say, early transition metal, the chalcogenides.
Right, but the point is that, like, I mean, did you look into, like, its structure when you take away, like, selenium vacancy?
No, yeah, but selenium vacancy, this material is non-magnetic.
But when it's surrounding, I mean, when it's surrounded by platinum, so when you take away vacancy,
yeah.
if the exchange it basically spin polarized at, like, platinum.
No, selenium vacancy or platinum vacancy.
Yeah, so the point that, I mean, you know, depend on how, like, Chagoson's vacancies, whether it's located close or far away from, you know, like transition metal, that could change the magnetic ordering as well. Did you look into that?
I'm not sure if I understand what you mean. So we have this is just the normal for let's say structure of transition metal, the chalcogen. Each chalcogen atom has let's say connections to three transition metal atoms, right?
I mean, it's not just only this system. In many other, like, TMD systems.
No, but I mean we did not let's say do a broad investigation of defects in TMDs. I mean, this was done only for this. So I'm not able to speak for vanadium dichalcogenide or any other dichalcogenide from the. We did also defects in molybdenum, the disulfide, but that's a totally different story.
Yes, because what we did is it's like when we dope
Mhm.
magnetically, and then we see that when we have like Jacobian vacancy
Right, so
surrounding.
you have impurities in the
Yes,
transition metal,
and
then
depend
you
on
also have-
how the couple and that could you change
yeah,
the
could well be,
magnetic
but we
properties.
did not investigate this.
Okay, okay.
It's
Thank
an
you.
interesting subject. Thank you.
I think we have to stop discussion. I would like to present Oleg with a certificate on behalf of the organizer.
Thank you.
And now, Alina Kasirka from Bilkent University. Phase change material.
All right, thank you very much for the introduction. Thank you. I would like to thank the organizers for the invitation. So my topic rather lies slightly at the borders, let's say, of the general theme of the conference, perhaps. But I think I can convince you that I'm going to show you some interesting stuff that is directly actually relevant to most of the work in some sense. So, actually, I'm not going to go do a rigorous introduction, but first I would like to talk about why phase transitions. Basically, it's the most ubiquitous concept in pretty much all physics. I mean, we have been hearing about a lot about systems that exhibit basically phase transitions. So, and then, many correlated systems actually are associated with phase transitions. If you look at these examples, for instance, in the case of doped cuprates, all these different phases, they're basically, by changing the concentrations of the copper or oxygen or other ingredients here, you can tune the temperature or the pressure, whatever you like, the extrinsic parameter, where the phase transition takes place. Another perhaps very interesting example that has been recently demonstrated is twisted bilayer graphene, where you have, again, basically phase transitions through various quantum matter. So, in one case, we are dealing with a very complex system, and in the other case, I would say we are dealing with an extreme system where the phase transitions happen at very low temperatures and so on. So, but these are not the only two examples, actually, that we can find. Actually, if you look at this list, there are many other materials, and this is not by far, it is not a complete list. It's a very limited list. So here, I'm going to focus on VO2, and basically, these correlation effects actually lead to the phase transitions that I already mentioned. So I spent quite a lot of time with VO2, so I'll continue my introduction with VO2. In the case of vanadium dioxide, this is a very simple transition metal oxide, which exhibits a phase transition at about the room temperature. And it goes from being an insulator to metal if you increase the temperature, and a structural phase transition is associated with it. This is an interesting transition because, this resistivity changes on the order of 5, 6 orders of magnitude, and it is coupled to this optical phase transition as well. So, in our past efforts, actually, we tried to understand this phase transition, and we applied strain using a MEMS device. And if you could play the video, and by changing actually this gap size, you can see that this phase boundary can be controlled, and this allowed us to extract a phase stability diagram of this material and triple point in a solid state system for the first time. And the insulating phase, if you look at it, is not a regular insulator, and we also studied that in the past, and we basically demonstrated that it is not your regular insulator. This is somewhat expected. And obviously, the dream dream here is controlling this phase transition using an electric field. And the problem is basically, people tried it really hard, but the Thomas Fermi screening length is very short. So basically, you know, it's quite difficult to modulate. But I took my shot on this one as well. So we milled down, we developed a method to mill down VO2 crystal, single crystal, that's very important. And we try to, you know, gate it, but unfortunately it is not a gateable material. So, you know, even if you have a very thick VO2 crystal that is freestanding on an HBN substrate. So this is very interesting and good, but these major limitations actually somewhat put me away from the studies of VO2. Now, back to the drawing board, we have these systems and we have this table. So I want to figure out ways to obtain simple materials that can exhibit phase transitions through the strong electronic correlations. So if I take a step back and show you the kitchen of this thing, the examples that I showed you on VO2 is about basically by using these nanobeams. And there's a very good reason. If you use epitaxial films or these sputtered polycrystalline films, the interaction between different crystallites actually hinders the mechanisms that you expect to observe, or the phenomena that you expect to observe, I'm sorry, in VO2. And same goes for these epitaxially grown films. You know, basically in epitaxy, your crystal follows the substrate, and this exerts a strain on the crystal. Thus, it leads to complications and thus irreproducibility in measurements. So this extrinsic effects must be controlled. So we need to have single crystals, pure forms, so that we can study these effects. So the best way to do it, you know, the best way to obtain a crystal, in my line of work at least, is chemical vapor deposition. You put the precursors, you put your substrate, you close the lid, and then you have a working recipe, hopefully, and you obtain high-quality crystals, right? It's easy to implement. It has low running cost, but you know, the recipes are typically very irreproducible. You know, you cannot, even if you know, if you make slight changes in your system, you cannot reproduce your recipes. It's a black box, so you cannot optimize. So how can you, you know, synthesize new crystals with such a system? Well, it's not possible. So we had to design something new so that we can fabricate new crystals. Now, the idea is, you know, have an optical window, have your CVD happening here, and then observe the crystal synthesis in real time. Well, we performed some thermal simulations and some preliminary work, and you know, also there has been some trials before what we introduced. And then we created this complicated looking setup. So this is now our CVD furnace, this aluminum box here. And it is basically placed under an optical microscope, and you have your crucibles inside, and you can see it glowing actually at 950 degrees Celsius, and you can see the substrate. So we can observe the CVD process in real time while controlling all the parameters, the gas flows, and so on. So this gives us a real-time feedback, perhaps. So if we could play this video as well. This is an early example. What you're looking at is taken at 790 degrees Celsius, 4x, and this is the scale bar. These crystals are tungsten diselenite monolayers, and actually you can see different growth modalities taking place in the same growth. So by doing that, we can, I call this the Ferrari of CVD furnaces, because I can put the brake, slam on the brake, and then I can freeze the growth, then characterize what's happening. And this, I'm going to skip, this allowed us to synthesize novel materials that hasn't been synthesized in single crystalline planar form before. Now, there is, I cannot say a library now, but you know, a small library perhaps of materials, and we are basically limited by the number of setups we have and number of people we have. If you name a material, I don't want to oversell it, but at least we can see what's happening and we can have an idea about the growth. Now, I'm gonna give a glimpse of some of these materials. I'll just very quickly glance over them. But the focus, you can see, you know, we don't have basically much data on these. That's why I'm not going to talk about them. But all of these materials exhibit very interesting phase transitions. At the moment, our focus is, you know, materials that exhibit these phase transitions. One case is V2O3. Since I'm a VO2 guy, you know, I always showed interest in VO2. But to be honest, our first goal was to synthesize VSE2, not V2O3, but you know, sometimes you get what you get. And you know, there are interesting questions that you can raise with very thin V2O3 crystals. And we basically studied the fundamental properties of these crystals. And perhaps an interesting point about V2O3 nanoplates that we synthesize is that you can exfoliate them. You know, it's not a van der Waals materials, but like ilmenite, where you can obtain monolayers, actually can sort of exfoliate. I don't want to call it exfoliation. This is not in the sense of, you know, you exfoliate van der Waals materials, but this is more like cleaving in the plane axis. But still, if you look at these steps, they're not optically visible. You can see actually, you know, it grows or it follows the unit cell of this material. And it's very important, actually, this ability to transfer these crystals is very important in the study, because now I can freely move around this phase diagram and I can study the full details of the phase diagram, unlike the previous studies. So I'm just going to go very quickly through these slides. But one other thing, you know, I had this dream of controlling the metal insulator transition using the using electric field. Now, actually, we are doing some very preliminary work to show, you know, these are preliminary results. We are working on it actively at the moment, but we have, it's showing hints of gate modulation. And thus, perhaps with better devices, not like these sketchy devices, better devices, we can control the metal insulator transition. But also, now we are working on suspending these nanoplates over these trenches where we can control the gap size and apply strain on these 2D material. Well, I don't want to call it 2D, but thin crystal, and modulate the phase transition at various temperatures. Another one is manganese oxide nanoplates. You can find it in very different morphologies. Actually, you can buy kilograms of this material in the powder form, and it comes in very different morphologies. And this one is particularly interesting, at least for me, a guy who likes 2D materials. And but you cannot find single crystals of this thing until now. And basically, we can grow these crystals. They can be quite thin. Actually, we've recently found a 3 nanometer thick one, which is the record at the moment that we have. And if you could play this video as well, and perhaps speed up, because I realize that I have 20 minutes, not 30 minutes. So if you could speed up, like jump to a later point, maybe, so we can see. At the moment, we are torturing the device. We are applying 150 volts, maybe slightly forward. Yeah, you can see this phase boundary moving with the applied voltage. And basically, we studied this in detail, and we realized actually what we have is this layered structure that has potassium and water intercalated across the layers. And by applying this electric field, that was an exaggeration. Actually, you can induce this ionic motion at much lower temperatures. But this is a material that is intrinsically doped with potassium and perhaps water, and you can move them. And further, actually, there's the example. I mean, even with 10 volts, actually, you can separate them. And it gives this very nice hysteresis curves. And again, I'm going to quickly go through these, but this is a slow process, and it can be used as a memristive device. And we also showed that you can mimic the synaptic response in such KMNO2 device. And now we have, I'm going to skip this one, but we also now have sodium MnO2. And imagine making a junction of these two materials. Now you can make things like sodium-potassium junctions where you can transfer different ion types and perhaps like lithium and calcium, so you can manipulate the charges in the system. Another interesting example that exhibits these phase transitions is Cu2Se. Again, you could find it in various morphologies, various forms, as thin films and so on, and people demonstrated that it exhibits this very peculiar phase transition at about 350, where it shows this colossal Seebeck effect. Then we approached this material and tried to synthesize, and after synthesizing, we realized that actually it has these cute corners that has different color contrast. And actually, again, these are videos, and you know, if, so it's hard to see, but you know, once we apply this 1.5 volt, actually you can, I'm not sure if it is clear, but yeah, now you can see the copper ions actually within the crystal are moving, and it results in a different type of phase transition. I'm going to skip the next video. And basically what happens is, you know, if you push it too hard, actually you can find copper ions that are leaking into the gold contacts, but the phase transition mechanism is actually different. This shows a 5 orders of magnitude change in the resistivity, and you can control it optically as well as electrically. So this is another material. So I don't have much time left, but okay, all right, great. So, but basically we can explain this by the motion of copper ions. This is a superionic conductor. What happens is basically copper ions can occupy different sites in the crystal. One of them is tetrahedral, the other is octahedral, so it can make jumps across these sites. This causes the, this is the reason we believe that for the phase transitions we observe. So to wrap up, basically, you know, this is the way to find, I guess, fascinating new physics, the correlation-induced phase transitions. And we are trying to synthesize novel materials to aid this task. Before finishing, I would like to thank my group and my collaborators and you for your attention. Thank you.
Now paper is open for discussion. Questions, please?
Thank you. It's really interesting, and then you look to the resistive switching. But you have a 2-point contact, and this, and can you also expect some interface between gold and your crystal structure? This is my first question. Second question is about you have really nice the triangular crystal structure. Is there some kind of the angular dependence of this kind of? Did you try this one?
Okay, thank you.
Thank you.
So the first one, I don't think it's a resistive switching. It is something that I can really define as a phase transition, because it's not like we are applying too much current to induce the phase transition. And basically, you're creating sites that are more suitable for copper ions to occupy the octahedral sites, which for some reason that we are not fully aware is, you know, 5 orders of magnitude more conductive. And once it's in that state, it is a metastable state. It remains in that state. So I'm not sure if it is really a resistive switching mechanism. So probably not. And for the shape of the crystals, I think it is dictated by various parameters that involves, the temperature that you grow your crystals, and the substrate, and also the symmetry of the material, symmetry of the unit cell. So, sometimes we can get hexagonal shaped crystals because of the 6-volt symmetric nature, but that happens, let's say, higher temperature growths. Sometimes we get triangular crystals that happens at lower temperature growths. And for the this accumulation of different phases, it's an entirely different story. I mean, I couldn't possibly fit in a 20-minute talk. I should have talked entirely on CU2SC so that I can explain it in detail. But again, there are two factors: the substrate effect, as well as the how rapidly you cool down the system. They affect how these phases are distributed within a crystal. I hope this explained your question.
Thank you. Thank you. We have to proceed. I think this is a certificate of participation.
Thank you.
On behalf of the organizers. Now we have the third talk in this.
Okay, thank you for the introduction. So the paper that the results that I'm about to talk about were recently published. So with that, I would actually like to start with the acknowledgements of my collaborators. So the guys at Clermont University in France. So these guys did the theory. They worked on the rate equations and adapted the coupled oscillator model. The guys in Tokyo, the University of Tokyo, and Riken, these guys grew our thin film and also performed the initial magnetometry of our thin film. And then also University of Dortmund, so these guys did the magneto-optical circular dichroism, measuring the spin dynamics, and this fed directly back into our rate equation. And then everyone else at the University of Sheffield who helped me with the magneto-optical spectroscopy in a tunable microcavity. So we've probably heard quite a lot about the basics of transition metal dichalcogenides from an experimental point of view. I want to highlight the fact that how easy they are to isolate these monolayers. So we actually buy them in bulk. You can see an example over here. And then just through micromechanical exfoliation or the sticky blue tape methods, we can quite easily obtain monolayers. And then from an optics perspective, we see that the band gap goes from an indirect indirect band gap in bulk and switches to a direct band gap in the monolayer limit. And this is formed at two equivalent values at K and K primed in the Brillouin zone. And then thanks to the inversion symmetry breaking in the monolayer, this lifts the degeneracy at the K and K prime, or the K plus, K minus values, such that the spin states in these two values are opposite. So when we get down to a monolayer, the optical properties of these materials are highly excitonic, so we get about 15% absorption based on these excitons. And so the neutral exciton, which is just an electron hole pair, this has a very large binding energy due to the quantum confinement in the 2D layer. And this leads to very large binding energies, so about 200 to 700 depending on the material. And this is clearly visible at room temperature as well as low temperature. However, most of our studies are done at low temperature. We can see some more slightly exotic versions of excitons. So here we have the negative trion, which is simply an exciton with an excess electron bound. So this has a binding energy of about 25 MeV. And this is very prominent in the PL spectra and also the absorption spectra at low temperature. So again, most of our work is done in a zero-dimensional tunable microcavity. So when we place a highly absorbative material into our cavity, so this is a graphic of our cavity. This is an actual photo. So we have a series of 8 piezo stages. So we have X, Y, Z in both top and bottom, which control the bottom dBr and the top dBr. And then we also have 2 tilt stages, which make sure our confinement between the 2 dBrs is maximal. So when we have everything aligned, we just tune the Z stage, and you tune the cavity mode into resonance with our exciton, and then the onset of this polaritons is quite clearly defined by this anti-crossing between the LPB and UPB. And you can see if we focus on the LPB, so negatively detuned from highest resonance, we're highly photonic, so the cavity mode, and then as we tune through the resonance and beyond, we become highly excitonic. And then at the point of maximum Rabi splitting, defined as the minimum distance between the UPB and the LPB, we actually have maximum 50-50 share between the exciton part and the cavity parts. And then the strength of this Rabi splitting is related directly to the cavity mode volume and also the oscillator strength of the excitons. So in a fixed cavity mode volume, our Rabi splitting is directly related to an oscillator strength of our excitons. So the material that I would like to present here is molybdenum diselenide. It's one of the first TMDs studied. It's well studied at this point. So the low temperature, we can see that it has highly excitonic optical properties, and you can see that the neutral exciton has a very large oscillator strength, and naturally the trion has quite a smaller relative to our neutral exciton. And what's quite interesting about MOSI-2 is that the band structure combines a coupled spin and valley physics, so that with the chiral optical selection rules, and this means that you can optically address one valley or the other through our circular polarization. So you address K plus with sigma plus and vice versa. So in this work, we use a thin film of europium sulfide. This is deposited onto our top layer of DBR, silicon dioxide, via E-beam evaporation. So EUS is an insulating ferromagnetic material. It has a very weak and broad absorption beginning about 1.65 electron volts, which comes into play a little bit later. It also has a Curie temperature of about 17 Kelvin. This is a squid measurement measured at the time of growth. And then we transfer our molybdenum diselenide monolayer on top via PDMS transfer. In our studies, we actually see no ferromagnetic influence of EUS on the molybdenum diselenide. We think this is for 2 main reasons. Firstly, the PDMS transfer means that the interface between these 2 layers is very weak. Basically inserts a barrier between the 2 of them. And then secondly, we found recently that the EUS layers actually oxidize quite quickly. However, what we do get from our EUS, thanks to the growth process at 16 degrees Celsius and the low sulfur vapor pressure, we actually see that the sulfur atoms during growth re-evaporate, and these sulfur vacancies act as electron donors. And potentially by controlling the growth process, we could potentially get a controlled doping via EUS into our molybdenum diselenide. But in the study so far, that's not been verified. We can repeatedly get the same level of doping, so about 10 to 12 excess electrons, but we haven't played with changing the growth parameters just yet. So when we cool down our sample and introduce magnetic fields, so initially, thanks to our large N doping in our PL emission, we we actually only see the trion resonance. And this is due to the large amount of doping, so we have a high Fermi energy. However, in absorption, you can see both resonances, so trion and exciton. And what happens when we introduce a magnetic field, we see our 2D electron gas gets fully spin polarized at about 4 Tesla. This has been confirmed in previous reports as well. But what this means for us, because in molybdenum diselenide, our ground state trion is intervalley, so that, say, at sigma plus over here, if you introduce an electron, it bounds with an excess trion situated in the opposite valley. So plus 8 Tesla, we have our 2D electron gas situated in the K minus valley, and this leads to a high oscillator strength of our sigma plus trion state. And the vice versa is true. So if you introduce a trion and sigma minus, you actually have 0 electrons to couple to, and this gives you a 0 amount of oscillator strength. We see that the PL is closer to 80% degree of circular polarization compared to 100% in the reflectance contrast. And so this means that we see some kind of depolarization mechanism due to the non-resonant circular wave pump laser. And this is the rate equation that we developed. So when the pump is activated, we form excitons very rapidly, so sub-picosecond kind of timescale. And then these excitons bind with the excess electrons to form trions. And we know that bound trions, thanks to the intervalley constitution of them, these depolarize quite quickly over the course of a few picoseconds. And then when these trions decay, they leave an excess electron, which is now depolarized. And free charges take a much longer time to realign with the magnetic field, so over the course of a few nanoseconds. So the ratio between the two, so the depolarization and the repolarization, is about a factor of 1,000. And we can also see that we're still in a linear power response regime, so we're not having any saturation effects. And you can see quite clearly this degree of circular polarization decreases as we increase the power. So what this means when we put it into our cavity, so when we tune our cavity mode, we can see very clearly a Rabi splitting between the LPB and the UPB. And I should mention as well that since strong coupling occurs about the absorption resonance, this is labeled here as TRC, and our measurements are in PL. So the cavity mode, when it's highly excitonic, tends towards the PL. So this is where our reservoir of excitons are. However, the Rabi splitting happens about the absorption resonance, and this gives us a strong Stokes shift, again thanks to the amount of doping, and this means that the LPB actually pins back, bends back towards the PL state. And then when we introduce our magnetic field, you can see that the spin polarization of the 2D electron gas actually means that we get this spin selective strong coupling. So in sigma minus, you see that the cavity mode essentially travels straight through the resonances, whereas in sigma plus, we get this large opening of the Rabi splitting. So in order to compare the two LPBs, we just form this waterfall plot as a function of piezo voltage. So this controls essentially the cavity length. As we increase the piezo voltage, we decrease the cavity length, and we tune the cavity mode towards higher energies. So at 0 Tesla, we see that both sigma plus and sigma minus act in the same way. However, again, at 8 Tesla, we see that the sigma plus actually starts to get pinned by our exciton resonance, whereas the sigma minus continues to travel straight through our exciton resonance, trion resonance. And this opens up a very large Zeeman splitting between the two LPB modes. And if you plot the valley Zeeman splitting as a function of magnetic field, in the bare flake versus our trion polariton, you see that the bare flake has a G factor, valley splitting G factor of about 4, which is to be expected, When you go to a polariton mode, you actually expect it to be half, because you are half cavity, half excitonic. Whereas here, because of this spin selective strong coupling, we actually see an increase in our G factor of about 5 times. So again, thanks to the depolarization mechanism that we can see in the bare flake, we increase the power in the cavity mode, in the cavity state. And you can see that, again, at 0 Tesla, these two modes are exactly the same. And then when we introduce magnetic fields, you get the cavity mode traveling straight through our resonance. And in signal plus, it opens up to a maximum. As we increase the power, thanks to this depolarization mechanism, we actually start to see a Rabi splitting open up in the sigma minus, and it starts to decrease slightly in the sigma plus polarizations. And then by about 500 microwatts, you can see that they start to tend towards the same, back towards our kind of equal state between the two polarizations. And then what's quite unique about this system is that when we look at, for example, the Rabi splitting versus laser power, our highest nonlinearities occur at our lowest laser powers. And so when we look at the effective interaction strength over here, we get our largest interaction strength at our lowest powers. And this value of 0.2 is actually about 10 times larger than is previously reported in molybdenum diselenide trion polaritons. And this, again, is all thanks to the spin selective strong coupling. So hopefully I've managed to convince you that EUS might be able to effectively dope monolayer semiconductor. We can do it reliably. Potentially we could do it controllably if we experiment, if we wanted to go in that direction. We've shown an all-optical tuning of the 2D electron gas spin polarization in our doped monolayer molybdenum diselenide. And in turn, when you place this into an optical microcavity, we've shown an all-optical tuning of our Rabi splitting. And then we've shown valley selective strong coupling leads to a very high effective Zeeman splitting, over 5 times that in the bare flake. And then also that the lowest laser pump powers offer the highest nonlinearities. Again, I'd like to thank all the collaborators that helped with this work over the course of a couple of years, and then also you for listening.
Thank you.
Thanks.
Questions, please? I have a question. You have shown in one of the slides a very different G factor for two modes.
Yeah.
Can you explain how come that G factor changes by time?
So this calculation is based on the difference in energy between the two modes. So when you measure this at the bare flake trion, you get what is essentially the same as the shift in the valley state. So this represents the actual Zeeman splitting between the two, the K plus and the K minus valleys. Whereas thanks to this spin selective effectively pinning our sigma plus LPB compared to the sigma minus, which effectively just keeps going, you can see that this opens a very large Zeeman splitting. So this calculation is based on the energy difference between these two modes, just to highlight the kind of the extent at which the increase in what we'd expect.
You transferred the molybdenum diselenide in air?
Yeah.
Have you, just in order to improve the interface, have you tried to do annealing after transferring?
We've not done annealing. We're looking at doing stuff in a glove box, so we're trying to avoid the effect of air. And we're also kind of just trying to characterize the amount of how much the EUS oxidizes and how quickly as well. We're not sure, because it's grown in Japan and they need to ship it over.
Yes.
It's not always perfectly viable to do everything in one place. Initially, we wanted to see this kind of magnetic exchange. So yeah, that's what we wanted to see. We didn't see that at all. Instead, we get this this kind of different direction, which kind of worked out. It's something that we're trying to circle back to and trying to understand a little bit more and see if EUS is actually a viable material to do that. Our current results suggest it might not be.
Thank you.
Thank you.
Thank you, Daniel. Certificate for participation to the revised paper.
Thank you.
Thanks everyone for participating. And now
thank you very much. First, I would like to thank the organizers for organizing this very nice workshop in this amazing place, and also Ahmed for the invitation. Well, I will talk about Orbitronics, which is, it's not what's been discussing that much here, so I will spend a good time of my presentation with some overview. Well, most of the work I've been doing, I will present, is done in collaboration with this group from the Fluminense Federal University in Rio de Janeiro. Luis Canônico also is a former student who is now in Barcelona. Although we have other collaborations, these are the main behind the works I'm presenting today. Okay, so let's start from the very start, motivation to see what's going on with this orbitronic physics. So the idea is that, as we know, our society is in need of, exchanging data and storage, and the information technology industry is always on search of more efficient and small devices for the industry, right? And of course, 2D materials are promising as a new set of, as a new part of devices in that area. Well, but spintronics normally plays an important role in this area by encoding information in both spin and charge of the carrier. This we all know. And if we want to manipulate spins in solids electrically, we have a problem because the spins, they don't interact directly with the electric field, right? So to do this type of manipulation, we need to use two possible ingredients. One is magnetism. In a simplified picture, imagine we have the localized magnetic moments in a solid, and then they produce an exchange interaction in the carriers, in the spin of the carriers. We have a shift of the spin up and spin down bands. Then we have spin polarized states at the Fermi level. And this is at the heart of several of these phenomena, from magnetoresistance to, for example, spin torque. Well, there is another interesting ingredient, that's the spin-orbit coupling, that of course modifies magnetism, but it's used in solids because actually it couples the spin with the momentum of the carrier. So in this sense, it actually mediates the interaction between the electric field and the spin without the need, for example, of magnetism. And this, of course, we all know, we've been discussing here, there are several effects that are related with this interaction. Well, but I will talk about orbitronics, and orbitronics is basically an analog of spintronics, but instead of using the spin to manipulate, instead of manipulating the spins, we manipulate the orbital angular momentum of the electrons. And the first question we would ask is, okay, we are manipulating spins, why on earth we would like to manipulate the orbital angular momentum, right? Well, one of the first answers is exactly because, as I told you, there is no direct way to manipulate the spins with the electric field. In the case of the orbital angular momentum, even if you think about a very simplified picture of the orbital angular momentum of electrons in an atom, we know this is related to a charge distribution, and at the same time it has a magnetic moment. So in this way, with an electric field, you can actually act directly on this magnetic moment without the need of spin-orbit coupling or magnetism. So this is one of the basic ideas. And the other way to think about that is that if you don't need spin-orbit coupling and if you don't need magnetism, well, then we have a large pool of materials that you can use for this type of manipulation. So you can think about a green technology and also look of materials that are not scarce, are not dirty, like heavy metals, and are not scarce. Well, so this orbitronics is kind of new. But actually the name was coined almost 15 years ago, more than 15 years ago, in a work of Bernigvig, Hughes, and Zeng. But not much was done for almost 15 years. And only in the last 2-3 years, we're beginning to see more activity in this field with new theoretical results and finally some experimental results as well. So if you want to know about more about this, you can look at this perspective. And basically what we have is many analogs or counterparts of the spintronic effects in orbitronics. And one of them is the orbital Hall effect, which is basically the same idea as the spin Hall effect. So the spin Hall effect, we know that if we have a material with strong spin-orbit coupling, we apply an electric field, we're going to generate a transverse spin current, right? Well, the orbital Hall effect is basically the same idea, but when you apply an electric field, you see an orbital angular momentum current or an orbital angular momentum accumulation. And this doesn't need any spin-orbit coupling. Well, most of the original work in this orbitronic fields was made in this orbital Hall effect. Up to now, it's mostly orbital Hall effect, although we have other things. Well, similar to what happens in spintronics, if we are thinking about doing anything with this orbital angular momentum, we need to inject it, we need to manipulate, we need to detect. And when it comes to detection, it's kind of tricky because, well, you have magnetic moment, and the spin also has a magnetic moment. So it's very difficult to know if you are detecting, the way you detect is more or less the same. So it's difficult to know if you are detecting spin or you are detecting the orbital angular momentum. And well, this has been going on for a while, but in the last year, there are experiments in 3D metals where they explore it quite well. And the basic idea is to use materials with very weak spin-orbit coupling in a way that if you see anything, it has to be related to the orbital angular momentum. And so last year, we saw the first very controlled experiment when they actually measure orbital angular momentum accumulation in titanium with MOC. And then they compare this with the same type of spin accumulation, but in platinum, which is much heavier, right? Well, this year, we saw also a similar experiment, but trying to characterize the inverse orbital Hall effect. As we know, there is a spin Hall effect, and we should expect an inverse orbital Hall effect. And this was done also thinking about using light metals to generate this orbital Hall effect. Well, there is also the orbital torque. I think Matthias Klau was presenting here 2 days ago, and he was showing some results where instead of using spin currents to manipulate magnetic layers, they're beginning to use also orbital currents. So there are a set of new experiments and theoretical proposals on this. And even before that, many works on spin orbitronics already were pointing out that probably orbital currents were also responsible for part of this effect. So this is more or less what's going on in the field, and the experiments are mostly in 3D materials. So let me now move to 2D materials, which is more what I do. And we've been working on this since probably 2019 in different 2D materials, but I would like to focus today on 3 works that are all related to TMDs. And I think it's nice because we've been discussing TMDs a lot here, and I will bring a different perspective to the same materials. So as we all discuss here, we probably all know about TMDs. They have transition metals atoms in one of the sublayers of this honeycomb lattice. Then we have the chalcogens in the other sublattice. If we are talking about H, and some people use 1H, 2H, but this is a monolayer, okay, TMD. We have a system that has broken inversion symmetry, and because of that, we should expect also valley physics. And if we look at this picture, we know this material has spin valley locking. So depending on the valley you are, the top of the valence band has a different spin characteristic. But although we do have it has a neglecting spin Hall effect in the vicinity of the band gap. So before I begin to show my results, let me just show for someone in theory that wants to know how we calculated this. We basically use the same type of Kubo formula that we use to calculate spin Hall effect, but instead of using a spin operator, we can use an angular momentum operator. In this case, it's atomic. And with this, we can calculate either a spin projected Berry curvature or an orbital projected Berry curvature. And when we integrate this, we obtain the orbital Hall conductivity or the spin Hall conductivity. So let me begin with a simplified 3 bands model to study this system. So this is the basis that we are using. This is LZ in this basis. And we can calculate the band structure with spin-orbit coupling and without spin-orbit coupling. Well, before I go to the transport results, I would like to show you we've been discussing spin texture, but I want to discuss orbital texture. So if we look at this valence band and we look at the orbital textures, I don't care about the arrows here. The important thing is that the blue and red colors are positive and negative LZ. And we can see that we have actually an orbital valley locking in this system. And it doesn't matter if I have spin-orbit coupling or I don't have spin-orbit coupling. This picture looks exactly the same. So what we actually have in TMDs is that we have an orbital valley locking, and when we turn on the spin-orbit coupling, so we have each of these subbands here acquires one spin polarization. So this precedes the spin valley locking. Well, if we now look at the orbital and spin Hall conductivity, so in blue is orbital and in red is spin. So we can see for the system with spin-orbit coupling that we do have spin Hall conductivity, but inside the gap it's 0, and close to the gap it's almost 0. But the orbital Hall conductivity has a plateau inside the semiconducting gap, which was quite a surprise, right? Now if we turn off the spin-orbit coupling, the plateau doesn't change at all. So it's a plateau that doesn't depend on the existence or not of spin-orbit coupling. So let's try to move, well, before I move forward, some people could argue here, okay, but there is an orbital valley locking, and we know that there is a valley physics in the system. So this is just a way of looking at the valley Hall effect. So what we are seeing here is just valley Hall effect, but in the form of showing the orbital conductivity. Well, we had these questions as well, and to sort this out, we decided to do the following. Let's look at the MOS2 bilayer. Why the bilayer? Well, because in a bilayer, you recover inversion symmetry. So in principle, there is no valley physics in this material, right? It's inversion symmetric. You shouldn't have any LZ polarization, spin polarization, nothing like this. And we can again, now with DFT, we can calculate the orbital Hall effect of the monolayer and the orbital Hall effect of the bilayer. And the surprise is we still have the plateau, and not only we have the plateau, but the plateau is twice the size of the plateau of the monolayer. So, well, there is something going on. It's not, we know it's not a Z2 topological insulator, there is nothing like that, but that should be something topological because we are getting twice the plateau here. So we kept working on that to understand, in the same work to understand a bit better what was going on. We decided to look at a very simplified model. This model, for a single TMD bilayer, it has a monolayer, it has only 2 bands. And for the bilayer, it has like 4 bands. These are, this is the basis. So I think 1 and 2 is related to the layer. And then we can calculate the band structure, and then we can look at the Berry curvature of the system. And of course, if we look at, if we're projecting layers, the Berry curvature at K and K prime, when we sum the 2 layers, has to be 0 because the system is centrosymmetric. But when we calculate the orbital Berry curvature, the orbitally projected Berry curvature, they are actually, they have the same sign in the 2 layers. So they sum up, and we have a finite orbital Berry curvature that then we can actually use, not exactly like that, to calculate a Chern number. So to calculate a Chern number in this system, we cannot calculate the Chern number of the Hamiltonian. This one is 0, but we can, and it's exactly possible to do that, to calculate the Chern number of a given operator. So we have a projector of the operator of the angular momentum. We project it in the valence band, and if the system is gapped, we can calculate this Chern number. It is, we calculate this Chern number, and it's 1 for the monolayer and 2 for the bilayer. But again, this is not a Z2 topological insulator. It has something about topology, but it's not a Z2. Well, we can ask, okay, you have this plateau, this is crazy. This is an insulator who is carrying the orbital angular momentum. But in fact, people working with TMDs might know that if you cut the TMDs in a zigzag orientation, this system has edge states. And the edge states, they cross the gap. So they have in-gap edge states, they cross the gap, and they also have, in the monolayer, they have orbital polarization. In the bilayer, no. I think the gray colors cannot be seen here. So in fact, the monolayer has edge states, but instead of having a pair of edge states, as in the case of Z2, it has 2 pairs. And the bilayer has 4 of these pairs. But still, in principle, there is a possibility of carrying this orbital angular momentum even in the insulating phase. So these were more or less the ingredients we had at one point. And there is something about topology in this system. There are these edge states, so what can you find more? So, and this is where I move. Before I discuss the relation between TMDs and higher order topological insulators, let me just comment a few things about these materials. So one possibility to look at is to look at the other possible topological phases that a material can have. One of them is the higher order topological phases, where instead of these basic symmetries of the Hamiltonian that protect these states, we can have special symmetries, the crystal symmetries, protecting gapless topological states. So we can have in-gap states that are protected by these symmetries. So this is basically a generalization somehow of the crystalline topological insulator. And the idea, the name is higher order because of the following. In a Z2 topological insulator, when you have a 3D system, the topologically states, they live in D minus 1. In a 2D material, they live in edges. In a 3D material, they live in surfaces. In high order topological insulators, they can live in D minus something else. It can be 2, for example, as in the case of 2D materials, because in 2D materials we are restricted, right? So in 2D materials, if you have a higher order topological insulator, it will lead to in-gap corner states in these materials. And there are several classifications. That's the complicated part about these materials. They have several classifications depending on the different symmetries that are protecting these states. It can be a two-fold rotation symmetry, a CN rotation symmetry, inversion, etc. Another interesting feature about these materials, that several of them, they present also polarization, bulk polarization. It's a topological polarization, and you calculate this with a Berry phase. So why I'm talking about these materials? Well, because in a very recent, two very recent works, the 2H TMDs were classified as topological insulators. And they were classified with this classification. That's, I think it doesn't matter that much. You can calculate, it's similar to that calculation that was shown before, but you can use the eigenstates of the rotation operator and count them, the difference between them in some symmetric points compared to other symmetric points, and then you end up with some classification. And from this classification, we can also calculate the charge of the corner states that you get. But you can also cut the system. In a way, it preserves the symmetry that's protecting the state. So in the case of C3 symmetry, you have to cut this flake in an armature cut. And if you do that, you see that you have edge states, corner states, exactly inside the gap. This is what you see in red. Well, okay. And there is also a polarization. Not only we have the charges, and then you have also a polarization in these materials, which is perpendicular to the zigzag edges. And what's the importance of this? Well, it means that this polarization and even this corner charge, if you cut the system in a zigzag orientation, which is perpendicular to the polarization vector, you end up having charge accumulation in your system. And this is why you have metallic edge states. So every high-order topological insulator that has this type of polarization will have in-gap edge states if you cut in appropriate orientation. So now we have a class of materials that can have an orbital Hall plateau and present a way of conducting these states. Well, till now, 5 minutes, I still can discuss a little bit of this. We can also establish a connection. I won't go into details, but there are many ways to build simplified models for high-order topological insulators. One of them that was used for bismuth is to use 2 copies of the BHZ model. That's a model for normal topological insulators. So a normal topological insulator can be written in this base, for example. And if we calculate the orbital Hall effect, we can see that this system is a Z2, but has also orbital Hall effect and 1 pair of edge states. Now, if we duplicate the number of copies, but preserving the symmetries that are necessary for this high-order topological insulator to exist, we will see that, of course, the system is not a Z2 topological insulator anymore. It has like two pairs of edge states, like we saw in TMDs. And although, for example, the spin Hall effect would not survive, not in this case, but in another, the orbital Hall effect still survives in a situation like that. So this is also a way of trying to find these orbital Hall insulators. Well, we extended this analysis to several 1T TMDs because we began with the 2H TMDs, and now we calculated this for many of them. And in this case, we do have inversion symmetry, so there is no valley physics at all. We can classify the high-order topological insulating phase as Z4. They also have edge states, and they present orbital Hall effect, which is different from the other one because the L can be oriented in different directions, as in low symmetric TMDs for spin. So for orbital is the same, but it doesn't need to be that low symmetric. Finally, I won't have time to discuss this that much, but the idea we are building now, it's that it comes from bosons. So in bosons, if you want to construct a topological insulator, we don't have spins, right? So what they do, for example, in photonics, is they use as a basis, as spinors, they use the linear combination of px, py, and d orbitals to construct agent states of Lz as a basis for this type of operator. And they construct pseudo-time reversal operators that act in these states as a time reversal operator. So what's happening in these systems is that we do have something very similar. But instead of having just these states, we still have spin. So if we don't have spin-orbit coupling, which is strong enough to invert the bands, but we still have a gap where we have the pairs of d or p orbitals being inverted, we do have a situation when we have spinors that are being represented by process of pseudo-time reversal symmetry operations. And this is the typical protection they have, instead of something which is what we normally have in other materials. Well, I don't have that much time. Just to conclude, well, we showed that in multi-orbital 2D materials, we do have orbital Hall insulators with sizable plateaus. And if we have Hotties, they provide the edge states, but there is still a lot to think about, like orbital Hall effect mechanism, relaxation. What we could learn from this is that orbital angular momentum can widen the pool of materials that can be used for spin arbitronics. Thank you very much, and sorry for taking.
Thank you for this talk. Is it on? Okay. When you find these two pairs of edge states, do they interact, or can you scatter from one to the other? Because in real space, they might be close to each other.
They are close. Well, this is a good question. Oops, sorry, this goes in the other direction. Okay, if the system has broken inversion symmetry, you can see they are orbitally polarized. So they are very much separated by the symmetries. Even in this case, what happens is they are somehow protected by symmetry. So in general, they cannot go from, you cannot scatter from one to the other. But this is something we need to study a little bit more, what happens in centrosymmetric materials. In non-centrosymmetric materials, we know, for example, in this case, it's impossible to scatter from one to the other because they have totally different LZs. So it's not possible at all. So they are protected somehow.
Thank you.
Any other questions? So maybe then I have so if we keep adding layers, right? I mean, this edge states will evolve into surface states.
If we
keep adding the layers,
I think so.
Do you have any statement about the dispersion of the surface states? I mean,
not yet, no. But what we saw with this, so we can, with these higher order topological insulators, this model that I was showing is for bismuth. So, of course, this is 0, but if it's not 0, this is bismuth. So, in principle, I believe that, yeah, you have surface states in bismuth that they have somehow orbital angular momentum. You can, generate orbital Hall effect with them.
Okay, let's finish one screen.
Oh, sorry.
Thank you. Thank you. First, I would like to thank organizers for inviting me for this very nice conference. And before I start my talk, I also want to thank my students and our lab technicians for their work, which made possible this work, which enabled this work, as well as our funding sources. Today, I will talk about ergodic, which is history dependent, and non-ergodic, which is non-history dependent of charge carrier dynamics at the atomic length scales. And as a disclaimer, I can tell you that this talk is a little offspring compared to the main theme of this conference, at least this session, because it has nothing to do with the spins and or magnetic materials, but we are more concentrated on inorganic materials. So the very first question is that why we are interested in inorganic oxides. First of all, they have their material properties are tunable. Particularly, we can tune their electronic properties without changing or without sacrificing from their other properties, such as their chemical properties. And they are ideal substrates for high temperature superconducting films, for instance, iron selenide films. And they can be used as substrates for complex oxide epitaxy because of the ideal lattice match with other materials. And they have a wide range of applications for renewable energy and electronics applications. In addition to that, the next question or the next logical question that we can ask is why we are interested in time result characteristics. By measuring time result characteristics, we can reveal the charge carrier dynamics, which are the dynamics of electrons, holes, or vacancies in the materials which carry charge from one location to another. And we can measure these charge carrier dynamics with spatial and temporal length scales. And of course, by measuring these two, we can reveal local defect energy barriers, which may be interested for spin-based materials for you, and effective activation barriers, which is like the effective activation barrier for one vacancy or one charge carrier to move from one spot to the another. And we can look at these properties as a function of surface and or bulk defect density. Of course, this looks cool, and this may give us some interesting physical or chemical background, but the question is, how can we measure time result properties? I believe majority of you has used or has at least heard about atomic force microscopy. And when we talk about atomic force microscopy, there are basically two different modes. And majority of the people are interested in amplitude modulation, which is based on the measurement of the oscillation amplitude and demodulating the tip sample separation by using these two. And this is a mechanical technique, and it has mechanical limitations, which is like it scales with the quality factor of the oscillating probe. For this reason, the obtainable time resolution is limited within the order of seconds or half a second. In the order of seconds is the right term. The next modulation technique that can be used is frequency modulation, which we can modulate the tip sample separation by demodulating the resonance frequency shift of the atomic force microscopy cantilever. And physically, there is no mechanical limitation for this technique because frequency shift is an instantaneous phenomenon. There is no time delay between these two. And when I began to work on the institute, we unfortunately didn't have any microscope that was capable of achieving this, and we had to do some engineering, and that part may be interesting for you as well. And we had a Vico enviroscope scanning probe system. So it's a very generic atomic force microscopy system. If you ever use atomic force microscopes, you probably has used something like that, which is pretty good for topography measurements. But the main challenge for us that we want to enhance the system, and we wanted to integrate frequency modulation capacity in order to conduct time result experiments with this system. So the regular control architecture of AFM, probably if you use like AFM under, it has a control architecture something like that. You have an oscillating probe, and then you demodulate the oscillation amplitude, and then you control the tip sample separation by working on this control of the oscillation amplitude. However, we wanted to implement frequency modulation, which means that we wanted to get the instantaneous frequency shift of this oscillating cantilever. So we had to employ some others, we had to integrate some other control hardware to existing hardware of our atomic force microscopy system. To be able to do that, we had to have actually a second controller which works totally independent from our existing controller. And then we had a separate lock-in amplifier to modulate our resonance frequency shift and oscillation amplitude and phase, while correcting and automating the experiments with MATLAB and Python algorithms. So there was some engineering to some extent in order to enhance the capabilities of our microscope. And as I mentioned, in order to conduct time result measurements, we had to employ MATLAB for resonance frequency shift corrections, as well as Python to automate our experiments. So after this upgrade part, which may be interesting for you if you want to do something beyond topography measurements with atomic force microscopes, we were able to do time result measurements. And we conducted time result measurements by applying electrical pulses, between our cantilever probe and sample surface. And when we apply the electrical pulse to our material, we actually create an electric field within the proximity of the cantilever. And when we create this electric field within the proximity of our cantilever, we have a time-dependent Coulomb interaction within the surface. And the collective motion of charge carriers, which can be electrons or holes within the material, are reflected as time-varying force, and this force can actually be demodulated as a resonance frequency shift. So it's actually quite simple in that respect. We apply a pulse, electric pulse, and we just measure the resonance frequency shift. And this resonance frequency shift is due to the time-dependent change of Coulombic interaction within the surface. And when we did something like that, we were able to actually get the effective activation barrier of strontium titanate. And we conducted this experiment with spatial resolution, and we conducted this measurement as a function of temperature. So when we conducted this measurement as a function of temperature, it was possible to get the effective activation barrier by using this Arrhenius plot. And as we did this experiment as a function of with a spatial distribution, it was possible to get at which parts of the surface we had longer time constants, at which parts of the surface we had slower time constants. So we had some sort of spatial distribution, and it was possible that we also get some indication that either strontium or titanium terminated surface had difference in their time dependent characteristics. So on top of this, we also looked at the temporal variation of the measurements, which means that we also looked at the history-dependent effects. So here, it's very similar to the very first experiment. However, we changed the delay time between individual pulses. So if we don't give the material enough time to recover itself, and if we just electrically excite the material after a short period, for instance, after 100 milliseconds or 10 milliseconds or 200 milliseconds, we observed that the charge carrier dynamics are absolutely different. So actually, the very first measurement is different than the very last measurement if we don't wait long enough between the measurements. So there's a history-dependent effect for this charge carrier dynamics. And this may be particularly interesting because when you do a transport measurement, for instance, you apply a bias voltage, and this bias voltage may affect the measurement itself. So you may actually change the physical properties of the sample that you are trying to measure by just applying a bias voltage. And we also quantified this effect, and we have seen that if we have very short time delays between individual pulses, in this particular case, we measured like 10 millisecond difference between individual pulses, the effective activation barrier is monotonically increasing for the motion of charge carriers. And then this is independent of the temperature. So even at higher temperatures, which was like 75 degrees Celsius in our case, the material does not have enough time to recover itself, even with increasing temperatures. The next effect that we looked into was looking at the spatial extent of this temporal effect. Particularly, we looked into, we found two different surface spots with similar time-dependent properties. And then then we increased their distance. We had like two similar stops with within the order of 400 milliseconds. And then some other spots with like 50, 100, and 300 nanometers separation between our reference points. And then we kept this delay time as a short delay time. So when we increase the spacing between two different spots, we had observed that this time-dependent and history-dependent properties has actually an extent of up to 400 nanometers. When we, in the spatial extent, in the lateral direction, and the measurement or the previous pulses affect a region with a radius of 400 nanometers, 400 nanometers. So the take-home messages for this very first part is that local variation of charge carrier dynamics is possible for materials like strontium titanate. And it was possible to get the temporal variation of vacancy dynamics by tuning the delay time between individual pulses. And then we also looked at the spatial extent, how much distance these effects are preserved by looking at the spatial extent of these temporal variations. As a spin-off of these measurements, we actually did a second set of experiments at which we excited the surface with ultraviolet irradiation. It's a very similar experiment that we excited the charge carriers within the proximity of the surface by applying an electrical pulse. However, we induced surface oxygen vacancies on titanium dioxide, and we looked at the effect of these surface oxygen vacancies for the charge carrier dynamics within the proximity of the surface. So there's an UV light that shines the surface, and then we have an electrical pulse, and we do the same thing. We just demodulate the resonance frequency shift here, and then we apply the pulse, and then here at this part, and then there is zero bias here, and we just demodulate this resonance frequency shift in order to get the effect of surface oxygen vacancies for bulk charge carrier dynamics in titanium dioxide. When we did this, we first had to compare vacuum measurements with ambient measurements in order to justify that our ambient measurements are not dominated by the relaxation and motivation of surface adsorbates. And we see that they are statistically the same, the effective activation barriers of surface and bulk charge dynamics. And then when we looked at the effect of ultraviolet irradiation, we have seen that the time constants associated with charge carrier dynamics is actually decreasing with ultraviolet irradiation of the surface. So this means that when we irradiate the surface with ultraviolet light, the surface oxygen vacancies motivate the motion of bulk charge carriers. So this was an interesting result. And then we also compared quantitatively how this ultraviolet irradiation changed the effective activation barrier within the bulk system. And we have observed that the ultraviolet irradiation, which induces surface oxygen vacancies, actually makes it difficult for bulk charge carriers to move. So which was an interesting result on its own. And then we have seen that this reversible, this effect, this ultraviolet irradiation is a reversible effect. So when we stop irradiating the surface, we have seen that the effective activation barrier recovers itself as it was apparent in this time-dependent measurement as well. So when we turn off the ultraviolet irradiation, the charge carrier dynamics time constant has recovered, and we have also observed that its effective activation barrier is recovering itself within the same time frame. In addition to that, most recently we also measured on similar sample systems for their multidimensional characterization of contact potential difference measurements. Contact potential difference is simply the difference of the Fermi level of the surface as well as the scanning probe tip, which is in thermodynamic equilibrium when these two are in close proximity. And we have seen that with increasing temperature, the Fermi level shifts towards the conduction band for intrinsically end-doped materials such as strontium titanate or titanium dioxide. So in this measurement, we actually did like force spectroscopy measurements as a function of bias voltage, and then we reconstructed tip sample interaction force for this for this individual force spectroscopy measurements, and then it was able to we were able to recover contact potential difference, which is an indication of the Fermi level of the surface, as a function of tip sample separation. And when we did so, we have observed that the contact potential difference decreases between the tip and the sample with increasing temperature, which means that the Fermi level shifts towards the conduction band for strontium titanate, which is an intrinsically end-doped material. And then when we did a similar experiment for titanium dioxide, we have seen that its Fermi level again shifts towards the conduction band. However, for gold, which is a free electron material, there's a minimal difference, there's a minimal variation of the contact potential difference, which is more clear in this aspect. So for the gold-coated silicon, which had a gold thickness of in the order of 50 nanometers, the contact potential difference was minimized compared to the other end-doped materials as a function of temperature variation. So after talking about this time-dependent and non-history dependent aspects of my talk, I also want to say that I'm actively looking for multiple PhD students, and we will continue with, I have like two different projects. For my first project, we are interested in the measurement of equilibrium and non-equilibrium dynamics of vacancy migration at the nanoscale. For this project, we are looking at how the bulk and surface oxygen vacancies in titanium dioxide change the charge carrier dynamics. And then we have two different pathways. We will either irradiate the surface with ultraviolet irradiation, or we will change its preparation recipe in order to change the surface and bulk oxygen concentration. And we are interested in measuring the charge carrier dynamics by using techniques similar to that I have mentioned. In order to rationalize this project, we actually established a multi-million-dollar laboratory for scanning probe microscopy system at University of Quebec. So with this ultra-high vacuum, low temperature, helium-free system, we can work uninterruptedly at less than 10 Kelvin and under ultra-high vacuum conditions. And we can do simultaneous atomic force microscopy and scanning tunneling microscopy experiments, which reveal the local electronic properties of the samples simultaneously with the same atomic tip. So if you are an interested PhD student, or if your students are interested in this type of topics, you can let them know. And for a second project, we are interested in nanoscale characterization and aim-specific design of amorphous materials. So this has absolutely nothing to do with spin or magnetic materials, but we are interested in amorphous metals. So for these amorphous metals, we want to characterize them with atomic resolution by using our brand new microscope with a chemically activated tip. So what we will do is that we will put an oxygen carbon monoxide molecule at the end of a metallic tip, and then we will do simultaneous atomic force microscopy and scanning tunneling microscopy experiments at low temperatures in order to reveal how non-crystalline materials behave. And for this project, I'm looking for 3 different PhD students and at least 2 master's students to work on this project. So again, I would like to thank organizers for giving me the opportunity to talk about my research, which had nothing to do actually with spin or spintronics or magnetic materials. But it was nice to attend this very nice conference, and I would like to, if there are some questions, I will be more than happy to answer them. Thank you.
I'm sorry, I missed the first part, so I'm sorry if I'm asking something wrong.
Sure. No problem.
So, do you have ambient control in your setup?
Yes, we have ambient control in our. We have two different microscopes in our VICO microscope, which is VICO Enviroscope system, which is the old microscope actually. We can either work under ambient conditions or we can work under vacuum conditions, but it's very mild vacuum. It's like 10 to the minus 5 millimeters.
Okay, so the experiments that you performed,
yes,
the temperature-dependent experiments, were they performed under vacuum or
strontium titanate experiments, the first experiments, they were conducted under vacuum conditions, but for titanium dioxide measurements, which we had to induce oxygen vacancies, they don't work under vacuum conditions because we need water in order to reduce surface. So they were conducted under ambient conditions, but in a controlled atmosphere.
Okay, so this comes to my actual question now. So the temperature-dependent surface potential difference that you showed.
Yeah.
How do you make sure that it's not coming from, some weird ambient effects or moisture operation or something like that? So could you comment on that?
Yes, we measured by using different types of cantilevers, and the most important part is that we are measuring the contact potential difference, not the actual Fermi level. So any change in any chemical change in the tip, which may be induced under ambient conditions, may affect the absolute value of our measurement. So we did like recycled measurements. So we measured the properties at different temperatures, and we went back to the original temperature that we measured. Also, we used different types of cantilevers. And on top of that, in order to make sure that we don't have any adsorbate on our tip or on the surface when we do these potential measurements, we looked at the energy dissipation maps of the surface, because if there are more adsorbates on the surface, the energy dissipation would have increased, and this would show up in the signal in our signal that we drive our cantilever. So this is actually a property that we can physically measure, and we measured it, and we didn't see any statistical difference when we did cyclic measurements and over the course of the measurements. So if you look at the manuscript, actually for the paper for this one, we had all energy dissipation values for the excitation for each and every single measurement, and we checked and we verified if there's any variation because of absorbates and because we applied bias voltage. So this was some potential, and we checked that. We didn't see any effect. Thank you. Thank you.
Hello, Dmitry, do you hear me?
Yes, I can hear you. Can you hear me, guys?
Yes, very well. Okay, very good. So we actually 5 minutes ahead of schedule, but you can get this 5 minutes extra in favor of your talk. Are you ready to start?
Sure.
Okay, so then I'm presenting our last speaker in this section, who is Dmitry Ovchinnikov from University of Washington and I guess also University of Kansas. Now, and the title of his talk is Control and Harnessing of Chiral Edge Modes in Topological Magnet Manganese Bismuth Telluride. Thank you, please. You have half an hour or plus 5 minutes.
All right. Can you guys see the right screen?
Yes, but yes, we see it. I think that's the way it's supposed to be.
Okay, sounds good. Let me fix some things here. Just a moment. Okay, now we should be good to go. Thank you so much for staying so late, and thank you for the introduction. I also want to thank organizers for inviting me, especially Ahmed Afshar, and also Oleg for introduction. Anyway, I'm Dmitry. As Oleg mentioned, I'm in between the jobs. I'm in the Department of Physics, University of Washington, and in a few days, I'll start my own group in the University of Kansas. And today I'll be talking about this manganese bismuth telluride, a layered topological magnet. All right, so this work was done in the group of Professor Xiaorong Xu. So I want to acknowledge him for help and continuous support, and also people involved, in particular Jiaqi, Zhong, Zayao, and Xiong are people with whom I share first authorship on the works I'll be presenting today, and also collaborators who did various types of measurements, help, and also provided very high quality crystals. For example, Jiachang Yan from Oak Ridge National Lab, and also, of course, the funding agencies. So today I'm going to talk to you about topological quantum matter, which is a little bit different from the rest of the session. And very briefly, what it can be seen as is when we think about topologies of band structures, we can think about these shapes. So we can have, for example, a sphere, a cup, and then something like a mask. So these objects are topologically different in a sense that there is a different amount of holes in these structures. So when scientists look at topology of band structures, they think in a similar way. And one interesting aspect of this is that, for example, you can deform your sphere into something which looks like a cup, but without a hole. But creating a hole, you need to do something very special to the band structure of the material. And this moment here, pau, represents when this change actually happens. Another way to look at it is to actually put these different objects on this ladder. So, for example, we have something without holes, then cup, glasses, and this pretzel. And on this ladder, the steps represent the quantization of electrical conductance. So even if you guys will rush now for example, for a poster session, or you just get bored during my talk, what I want you to kind of take away message is the following. So in this talk, I'll talk to you about this manganese bismuth telluride. This is a bulk crystal of it. So it's a layered material which can be cleaved. We use Scotch tape to cleave it down to several layers thick. We load it into the cryostat, often in the dilution refrigerator, and then we can completely reproduce this ladder, measuring devices made out of this material. So the first representative of topological materials is, of course, quantum Hall effect, as you are all familiar with it. It was measured by von Klinzig in two-dimensional electron gas. So here, what happens when you cool the sample down, it's essentially a layer, two-dimensional layer of electrons down to low temperatures. You apply high magnetic field, and you get electrons inside this material to orbit. And you get, if you measure Rxx and Rxy, in Rxy, you get this beautiful quantization and get steps as a function of magnetic field. So later on, after von Klinzig, Thales, in fact, from the University of Washington, developed a theory which explained that these numbers here can be called Chern numbers, and they can be extracted from knowing the Berry curvature of the band structure and integrating it. And basically, different Chern numbers, they inform us on different topologies of band structures. For example, Chern number 0, most of the time would be topologically trivial, but non-zero Chern number would be topologically non-trivial. And this is the way we can distinguish them. And then a very simple way to actually know this, for example, if you are not a theorist, is to just measure Rxy and Rxx in topological materials. So then you can learn about Chern number in quite easy way. So that was the first example of topological materials, but now we know that 20 to 50% of all materials are topological in some sense. It doesn't mean that all of them are topological insulators or, for example, quantum Hall effect, but it means that some aspects of band structure are topological. So in this talk, what I'm going to talk to you about is I'll show you how we can engineer non-trivial topologies of band structure in various ways. I'll show you phase transitions between states with different topology and how we can visualize and measure it in atomically thin devices. In particular, I'll be talking about how material which has a normal or trivial band gap, as it's shown here, can be moved through critical point to an inverted band gap to essentially get a topological and non-trivial state of matter. And lastly, I'll talk about what's happening inside this gap. In particular, I'll show you how dissipationless edge modes form and how we can use them in some sort of simple devices. And the material system I'm going to talk to you today is this manganese bismuth telluride. I already showed you bulk crystal. So this is just a side view of a single layer of this material. So it has these slabs of tellurium, bismuth tellurium, and then manganese in the middle. It provides the magnetism pointing out of plane. So I'll show you how in this material we can engineer different Chern numbers. We can go from Chern number 0 to Chern number 1, for example, going through this critical point here, and also how we can add additional edge modes, so further tuning Chern number in this system. So the key physics here originates from something which is called Chern insulator or quantum anomalous Hall effect. And the way you can think about it is the following. In case you take a three-dimensional topological insulator, which is a bulk material in which you have special types of surface states. So the bulk would be insulating. It can be seen on this schematic at the bottom where conduction band and valence band are separated by the gap. And in this gap, you have a surface state. So bulk has a gap, but surface doesn't have a gap. And the surface state has Dirac-like dispersion and has certain spin momentum locking. So in case you can thin this material down, so make a thin film out of this magnetic topological insulator, and then essentially introduce magnetism into the lattice of your topological insulator in some very gentle way, what you will find is that instead of a gapless state like surface state here, you will start developing a mass gap on the surface of the material. So your material will become insulating not only in the bulk, but also on top and bottom surface. And the only conducting state left would be the edge state. So the edge state is depicted here as this green line, and it's called chiral edge state. It's a state which winds along the perimeter of your material. So ingredients for building such material are the following. Currently in the community, people normally use bismuth and tellurium, bismuth telluride type of materials. They are very well studied, very well understood. So they learned how to very carefully tune these materials so that they are intrinsic enough. Because, for example, you want your Fermi level to lie in the gap. You don't want to be somewhere far away in conduction or valence band. And then you also need to introduce magnetism very carefully, but in a way that it doesn't destroy other aspects of this topological material. So during the last 10 years, there was a lot of progress in chromium or vanadium doping of these topological insulators to get into this very interesting physics. And eventually, experimentally, it was demonstrated in this paper by Suzu Chang and co-authors in Science in 2013. And later on, many groups reproduced these results. For example, this result is from Goldhaber-Gordon group in Stanford. So what you can see here, and if you look very carefully at the scale bar, you can see that this sample is several millimeters in length and probably 0.5 millimeter in width. So it's a film grown by molecular beam epitaxy. But then if you cool it down to very low temperatures and apply some gate voltage to tune the Fermi level in the gap, what you will discover is this beautiful ferromagnetic loop with quantized RxY and basically zero RxX. So this is a very, very beautiful state. And the challenge of this state that it's rather fragile. So, I mean, of course, I'll talk more about the potential of this type of electronic state, but in reality, in experimental systems which we have right now, quantum anomalous Hall effect cannot be measured above 2 Kelvin. So 2 Kelvin is more or less state of the art. And the main challenges are related to disorder because this material is grown by MBE. It's not a stoichiometric compound. So you essentially create disorder by introducing magnetic ions. And those disorders, they affect mobility. They affect, for example, Fermi level distribution, etc. So there is a challenge of the need to improve such type of state. But we might ask ourselves a question: what if we have an ideal state like this? What this topological quantum matter could bring us? In this particular example, it would be quantum Hall, quantum anomalous Hall state. So there are many things. One is that it can bring us this low dissipation electronics. I'll talk more about it later in the slides, but essentially this edge state, which forms chiral edge state, it has very low dissipation. So regardless of the length of this edge, you would get exactly the same resistance. Also, these modes, they can be the direction of the propagation can be controlled. So this allows to have non-reciprocal devices made out of these materials. There are other aspects. For example, you could locally control your number and create some sort of PCB board, but out of topological material. In fact, topological quantum matter is heavily used in metrology. The resistance standard we have is quantum Hall standard, which can be measured up to very high precision. And now quantum anomalous Hall samples also approach the same level of precision. And there are a lot of proposals essentially to use these materials for topological quantum computing. There are discussions on how we can make this, for example, quantum Hall states interact and also combine superconductors with topological insulators and use them for some sort of non-abelian quantum computations. And on this graph here, the bottom part would be the applications at very low temperature, and upper part you would ideally want to have something which works at room temperature if you want to use that in some sort of practical devices. So now alternative solution to all this quantum anomalous Hall or Chernow insulator physics is to create an intrinsic material. In fact, it was created in this breakthrough paper published in Nature in 2019 by Mikhail Otrokov. He had a talk on this conference on Tuesday. These bulk crystals were grown and then investigated by various means. So what they and other groups demonstrated in the beginning is that this is a very promising system, first of all, because it's created from a different familiar topological insulator. For example, in this case, it's lead bismuth telluride, but then you substitute lead by magnetic ion manganese, and then you create all this physics. And the good thing is that around Fermi level, you don't have much contribution from this magnetic ion. So your low energy physics is basically topological insulator physics. It's just manganese provides magnetism, which is introduced into the lattice by having it. And another aspect of this material is that it has very rich magnetic phase diagram, so you can have different magnetic states. So in ground states, it's layered antiferromagnet between the layers, but then you can apply an external field, cant the spins to have canted AFM state, and finally ferromagnetic state. And for us, people who work in 2D materials, it's very good because it's available in cleavable form. So we can cleave these devices and we can cleave these crystals and essentially create this very nice, for example, this is 50 by 50 micron flake of homogeneous thickness. And then we can use it in a stack with other materials, for example, with superconductors or with other magnetic materials. So it gives us a lot of opportunities in creation of novel quantum states. So in this talk, I'm going to present you results which are mainly concerning transport measurements. But when we were studying this material, we were looking at it from multiple points of view. So our approach is not only combining transport, but also using something which is called microwave impedance microscopy, which can locally map out the conductivity in this material. So we can say locally if material is conducting or insulating, and then change the gate voltage, magnetic field, etc. And we also looked at the magnetic states with magnetic circular dichroism or Kerr effect. So essentially, we know with a micron resolution if we have any domains, or what's the magnetic state of the flake we are looking at. So with transport measurements, I just want to go briefly through things we can learn from it. So as I already explained, we can know the Chern number, but then essentially what I'm going to show you is I will show you some sort of maps here. So these maps are plotted in the following way. On the horizontal axis, we have gate voltage. In this case, it's shown as Ng. On this axis, we have magnetic field, and this color map represents measurements of RxY. So this essentially, looking at the Chern number here and RxY, we can learn what kind of Chern number we have on this map. And here, ticks represent different magnetic states. So we can go from antiferromagnet to canted antiferromagnet and then to ferromagnet. And then gate voltage allows us to change the Fermi level position because our materials are atomically thin. And then finally, in many of our devices, we have dual gates. So we can, independently from changing carrier density in the material, populate top and bottom surface with electrons or holes or nothing, and then create a certain electric field inside our material. So all these are tuning knobs which we will use. All right, so I spoke a little bit about edge states. So let me show you how they look like when we use this microwave impedance microscopy. These measurements were done on our devices in collaboration with Professor Yantao Tsui at the University of California in Riverside. So we take a whole bar of this material, we choose a small area here, and we make maps, so spatial maps by mapping this MIM signal. So the color scale here represents dark is insulating, bright is conductive. And what we can see is when we change gate voltage, when we go from something which is in the valence band through the gap to the conduction band, we find that our material is uniformly conductive when we are in valence band. But in this region between 30 and 40 volts, something interesting happens when we only have the edge state which shows up in conductivity. One more thing you should note is that this scale is nonlinear, so the difference of conductance between this edge and the bulk is orders of magnitude. So you can think about it as logarithmic scale. We can take one of these gate voltages in particular where we see this edge state, and we can conduct transport measurements. So transport measurements at high magnetic field inform us that the Chern number is indeed 1 or -1, depending on the sign of magnetic field. So not only we can see that there is the edge state, we can also know exactly that there is one chiral edge state, so we can know the nature of it, and we can also know the Chern number of this system. So we established now that we have edge states there, and let's see now what happens with the bulk. So with the bulk, the measurements are a little bit more tricky, but bulk measurements can inform us on what happens with band structure, because when we do transport measurements, edges essentially shunt our bulk, so we cannot know much about it, but still there are ways to study it. So in this map, I'm showing you the bulk conductivity, and we measured it in several ways. I'll just show you one for simplicity, for the sake of time. And again, insulating state is something dark, and conductive is something bright yellow in this case. We know Chern numbers. We measure edge transport independently, and we can know that there is Chern number -1 here and Chern number 0 here. So now let's look carefully what happens when we tune magnetic field and carrier density in this material. So when we are on the left side of this plot, when magnetic field is set to 0, our material has a Chern number 0. So we know that the gap is most probably not inverted. And we can see how the Fermi level moves across the gap. And here in the middle, we see this insulating state. On the right side, we have the same situation, but with chiral edge state in the middle. And I already showed you how this chiral edge state looks like. And we can tune Fermi level through this material. And what you can see is that when we have Chern number -1, the bulk is highly insulating, which makes sense because that's how it's supposed to be. And at the bottom, I have my magnetic states outlined. So antiferromagnet, candidate antiferromagnet, and ferromagnet as we increase our magnetic field. So let's look carefully at this gap behavior now, how it evolves. So nothing happens up to practically 2 Tesla. And then there is some interesting event here. So you can see a kink in resistance, and also that resistance starts to kind of deviate towards the bottom of the plot. At this point here, what happens is that you essentially form a conductive state. When you tune the gate voltage, for example, if you would make a vertical line cut here, you would see that you meet this conductive state, and both of these gaps kind of are not very pronounced. And then when we increase the magnetic field further, we start to open this much more pronounced gap here. And then essentially what we can see here is that it's a prime example of topological phase transition when you have Chern number 0, Chern number -1, and then you tune through that transition by magnetic field by changing magnetic state. So what we just observed in this nanoscale device is topological phase transition. And in the schematics I showed you previously, this topological phase transition shows up as this pow sound, essentially when you open a hole in your band structure. So you change the topological class of your band structure. Now we continued working on this material, and what we found is that in principle we can build much higher quality devices. And I just briefly want to mention that the key transition, the key magnetic transition, is transition from antiferromagnet to candidate antiferromagnet. In high quality devices at very low temperatures, we observe that as soon as we apply this critical field HC1, we immediately get to Chern insulator state. So quantization happens very, very rapidly. So, and this state is the key. And just in comparison with this device generation 1, which I showed you before, there is this broader transition here, and this transition here happens very fast. And there are several components to why this transition is broad. One is disorder in the crystal, another is disorder in samples. So these samples are cleaner, they have higher mobility, and also they are fabricated in a cleaner way. But also there is an electric field effect, which I'll briefly discuss further on in the slides, and this allows us to essentially tune the broadness of this transition. So now I want to further show you the richness of this phase diagram. So I already showed you this map, but let's have a look at it again. Again, it's carrier density magnetic field map, and we are measuring RXY here. And essentially, we have a certain electric field applied in this dual gate device. So what we found is that there are several states, right? There is chair number 1 state, chair number 2 state, chair number 3 state. So chair number 1 state, I already discussed with you. It's essentially a Chern gap state. When we have inverted band structure, we create this type of topological state. But then through many measurements and many tests, in which I will not go into details, we found that essentially Chern number 2 is combination of Chern gap and Landau level in the conduction band of this material, because the samples have higher quality, so we can also observe Landau level physics. And Chern number 3 within our parameter space is also Chern number 1 plus Landau level index 2. And you can kind of see the unusual situation in this particular material from the following plot. If we make a line cut here through the purple line, what we can see is that first we develop Chern number 1 state as we increase magnetic field, and then Chern number 2. So this is unusual. This is not typical way it happens in quantum Hall systems, but that originates from the fact that these two states have different topological origin, essentially. So it's not a standard sequence of Chern number versus magnetic field. Let's now focus also on this point. I want to briefly show you how we can control this topological phase transition, essentially, or this critical point with electric field. So we have dual gate. So if we park magnetic field at given number close to that transition, we can change two gates and then change electric field and also change the carrier density in the material. What you can see here is this oval outlined like this, and inside it we have RXY, which is above 95% of H over E square, so the Chern number is approaching 1, and also RXX is low, so both are clear signatures of formation of Chern insulator 1 state. And then you can see that as a function of electric field, we can move in that state and away of this state as it's shown on these line cuts here. So by just applying small electric field in the order of 0.2 volts per nanometer, we can control this state quite well. So we were wondering what's the origin of this, if we are controlling magnetic state or maybe we are controlling the band structure. And again, we did a bunch of measurements to be able to understand it. As I mentioned in the beginning, we also did magnetic circular dichroism, which informs us on the magnetism in the material. We found that electric field doesn't do much with magnetic state when we are parked at a given magnetic field. It's the carrier density which is affecting essentially the magnetic state, but it's inconvenient for us in a sense that carrier density changes also Fermi level, so we control both Fermi level and magnetism. So what we found instead is that the explanation of this effect is rather simple. We have two surfaces on which we need to align Fermi levels to form a Chern insulator state. Both of them are gapped because of the magnetism, but then essentially we need to get to a certain sweet spot, if you like, so electric field at which top and bottom surfaces are fully aligned with respect to energy. So when we align these two gaps, then we can observe a very nice Chern insulator state. But as soon as they are misaligned, essentially we have conduction on both top and bottom surface, and this edge state doesn't form. And similarly, if we apply opposite electric field, we can also switch this chiral edge state off. All right, so I showed you these 4 different distinct topological states. I showed you how to hop between them, how to move on this ladder. And this is exactly the ladder I was talking in the very beginning, that by changing electrical conductance, we can create these different shapes with different amounts of poles. And in this particular material, we can move in this ladder with magnetic state, electric field, and doping. So now in the last 3 minutes, I'll quickly show you some more results which we got. So another way to control the chair number in this material, which we found, is just thickness dependence. We found that in thinner flakes, we can have chair number 1, and then in thicker flakes, we can have chair number 1, 2, and 3. And essentially, just to give you an idea of how we can use it, we can try to combine these two flakes. So what we can do, we can search for flakes which have natural steps. So we do exfoliation, we find, for example, step between 4 layers and 6 layers, and we expect this situation to happen. And we did measurements to essentially map out the chair number in this material. So in each domain, we can separately measure chair number, and then we can see if we can recreate this situation in a fixed point of our phase diagrams. So we map out in chair number in each of these domains. We know that in domain 1, there is a chair number 1 located inside this space. And in domain 2, there is chair number 2 and chair number 1. So we can just overlap them and see that there is this yellow part of phase diagram in which this condition should be fulfilled. And now we can actually test the idea and see if there is a chiral edge state in between. So the way to do it was to essentially build special types of devices with many electrodes and think about geometry and think about how chiral edge states are moving around in our samples. So if our assumption is true and we can create this situation, winding edge states clockwise in this material, what should happen is that we should send our electrons from this terminal, and we should be able to detect equal amount of electrons terminals 8 and 9, because one chiral edge state should move along the perimeter of this domain, and another one should move along this junction interface, in case our assumption is correct. And that's indeed true. You can see it when you measure drain current going to terminals 8 and 9, and you see this perfect division 50-50 in this yellow shaded region. So you can see now that this junction actually acts as a beam splitter for electrons. So you send 2 electrons, one goes right, another goes left. And I won't go too much into details, but essentially we did other types of tests. One of them was to demonstrate that regardless of the length of this edge state, the situation is indeed exactly the same. So again, it shows the topological nature of these types of modes here. And we did all other measurements confirming essentially that this configuration of edge states is correct. And you would say, well, there are a lot of literature on chiral edge modes on the step edges of topological materials. In our case, the situation is slightly different because we can essentially tune this. We can couple it to transport. Our edges are very long. In this case, it's mechanically exfoliated, but it's 100 microns, which is a lot for our types of devices. And it also enables complex device geometry. So this particular domain is in the order of hundreds microns, as I mentioned. Another way to look at it is to see how this relates to other similar systems. So in quantum Hall, we know that we can create p-n junctions, for example, and we can create these chiral edge modes on the interfaces. So in magnetic topological insulators, you can write domains with magnetic force microscopy and create similar edge modes. But in our work, what we see is essentially a unique situation where sharing insulator state and quantum Hall interplay with each other, and then we can naturally form these junctions by just choosing different thicknesses. Okay, so I'll be wrapping up. I just want to briefly mention that we can also control this state with essentially using both magnetic field and carrier density. What I'm showing you here, I'm kind of going a little bit quickly, but what I'm showing you is the measurements when, again, we are sending current from terminal 1 and detecting it at 8 and 9. So we can control the behavior of the system. We can have it as a current divider. We can turn off this chiral edge mode, so essentially going from terminal 1 to terminal 8 only. And then we can also completely switch off the topology going to low magnetic field. And this completely reproduces this phase diagram. So lastly, the important aspect of these materials is that essentially going to high temperatures, high by means in cryogenic sense high, for example, in this case, we went up to 60 Kelvin. This behavior does change. So this essentially topological current divider becomes worse in the sense that there is deviation from perfect behavior, but you can still observe that even going up to 60 Kelvin, basically, still has this behavior. And this correlates very well with our and other people measurements on topological states in this material, which in fact survive up to liquid nitrogen temperatures in case you apply high magnetic field. All right, I hope I demonstrated to you a little bit of what we learned from this material manganese bismuth telluride. There are many interesting aspects of it, but to be more simple, I hope that I showed you that we can create easily these different shapes in terms of topology of band structures using this as a model system. And we found a lot of ways how we can change the topology, so we can change these shapes and essentially create new states, and then we can further combine them. All right, that's what I have for today. Thank you very much, and feel free to ask me questions or email me questions. Thank you.
Thank you, Dmitry. So the talk is open for questions. Question number one.
Thank you very much, Dmitry. Hi, can you hear me?
Yes, I can hear you.
Okay, so I have two questions regarding your talk. So one is, how insulating is the bulk of your system? And the second one is, can you comment on the formation of domain walls in your system, because I think that's bad for your dissipational transport.
Yeah, so question number one, the bulk, for example, in this measurement is above 1 mega ohm. It's in the order of 2 mega ohm, and it's a two-terminal measurement, so not very precise. And this measurement is done at 2 Kelvin. When we go to millikelvin dilution for each temperatures, bulk there is probably giga ohm, so very, very insulating. In terms of domains, we have not seen yet domains in a sense. When we map out the magnetism, we cannot see much domains. Domains do form if you, for example, combine different thicknesses. For example, in this case, I mean, of course, you have two domains, so there might be domain wall kind of pinned to this, but it would also depend if thicknesses of these flakes are even or odd. We studied a little bit the dependence of even and odd layer number on the magnetic state, and we found there are some differences. So in case you, for example, form 3-layer and 4-layer domain with the crystal step, then you would indeed have different magnetic states in these two domains because the critical fields would be different. Did that answer your question regarding domains?
Yes. So I think in chromium-doped bismuth telluride samples, I think usually the domain walls are forming, and they are around 500 micrometer in size. Do you know any kind of magnitude in your system?
So in our case, we mapped out domains with RMCD. So we have micron scale resolution, and we did not see them in the flakes ranging from, let's say, 10 to 100 microns. If you take a homogeneous flake of the same thickness, you don't see domains. But I mean, there are MFM studies of similar systems where people indeed can see some domains, and I honestly don't remember the order of magnitude. It's probably small because we cannot see them. So it's smaller than 1 micron.
Oh, okay. Thank you very much.
I will ask one myself. So Dmitry, the chiral edge states are expected to have some well-defined dispersion characterized by the Fermi velocity. Is there any way you can assess this quantity in your measurements?
We haven't done that, and honestly, I'm not sure how we could. I don't know, maybe some STM colleagues could help or something. Maybe from there we could learn dispersion. Yeah, we cannot tell it. We just, basically we know the Cherry number, and we know that it's quite robust in the sense that we can measure quantization up to rather high precision within what we have in our laboratory. So that's what I can say, but yeah, we don't know Fermi velocity.
Okay, thank you. Are there any other questions? Last chance? No? Okay, let's thank our speaker once again. And I am closing this session. Thank you, everyone.
Thank you.
the poster session will start at 6 p.m. We passed, I think, around 7 minutes. So the first, each speaker has 5 minutes, and the first speaker is Anna Vorobyova. Here? Oh. Okay, we are so sorry you are late. Could you open her presentation? Did you give your presentation before? So, if, you can use this microphone or the other microphone. It's up to you. Anna Vorobyova. Lomonosov, Moscow State University, Russia, chemical department, and we'll talk about low dimensional magnetism in new layered nitride complexes, right? The file name. Is it lost? In this session, there is no question after the presentation at the corridor or in the gala dinner. Whatever you want, you can ask about the presentation. Because each speaker has very small time. Yes, the presentation is lost. I understand that. Is there an online no. The next one is also, yeah. You will mix? No. Is that arrived you? Thank you, Mustafa Ji. Whatever you want, you can open. It may be changed, no problem, right? Between them, only 5 minutes. Yeah. Yes. The first one is here.
So, my name is Anna Vorobyova, and I want to introduce my work, low-dimensional magnetism in new layered nitride complexes. So the nitride complexes due to the geometric feature of the nitrate group is ANO3, can exhibit some different properties, and the crystal structures also can be from different dimensions. For example, the transition atom can link to each other by the nitrate group and formed some anions like chains, ribbons, layers, or three-dimensional structures. In this work I present different compounds. For example, this compound on the right part is cobalt nitrate with two water molecules, in which each cobalt atom linked to another cobalt atom by bridging ligand group to form a square layer. And such layers connected to each other by hydrogen bonds of these water molecules. We measure the magnetic properties, and in the compound there is a metamagnetic transition and antiferromagnetic ordering at 20 Kelvin. Also, the interesting these two compounds, they have the similar crystal structure with the transition metals in these nodes. And interesting that the cobalt compound has a three-dimensional magnetic ordering and metamagnetic transition, and the nickel compound demonstrates two-dimensional magnetism. Also, this compound in it we has a Kagome layers, and these Kagome layers connected to each other also by nitrate groups, and we can see the exchange in these Kagome layers and between them with different crystallographic. So it's AB plane in the crystal structure, and this is the C axis. So like this Kagome layers, and like this they're connected to each other, these Kagome layers. And the magnetic properties of them. There is a three-dimensional exchange, and we see also phase transitions like structural phase transition and magnetic phase transitions at lower temperatures. But we can see on this slide in this temperatures is about 5 and 10 Kelvin. But that's all I think about this presentation.
Thank you. There is no question. The next speaker is the same scientist, which will be talk about synthesis and characterization of lithium iron arsenide single crystal with the electron and hole substitution in the cationic sublattice, right? Here you are.
From also my address, I have sent 2 emails. Two emails from my address, and there are 2 posters, different emails. Yes. Yes, thank you. So on this slide, I present my theme about the synthesis and characterization of lithium iron arsenide or single crystals with electronic and hole substitution in the cationic sublattice. The lithium iron arsenide has a crystal structure shown in this picture. There is iron arsenide layers which separate from each other by lithium cations, and it's known that it's superconductor with Tc is about 17 Kelvin. Okay. the synthesis was made by a self-flux method. So we put the initial reagents in the crucible. The crucible was put it in a niobium container with ergon atmosphere, and then this container was put it in a vacuum quartz ampoule and heated like this temperature profile. So we have obtained the crystals with the substitution on the iron, partial substitution of iron atoms on cobalt, rhodium, palladium, vanadium, and ruthenium. And here we can see the magnetic measurements of these crystals. So with the increasing of substitution of iron atoms, we see the decreasing of critical temperature of superconductivity transition. But if we make a whole doping with vanadium, there is no superconductivity at all. But in only in this compound, we can see the nematic fluctuations that we can't see in other doping crystals. So I think that's all about this also. Yes.
The next speaker is Madan Sharma, right? And also there's a certificate. Yeah. Second one will be prepared in the next conference. We will give it to you. The next speaker is Madan Sharma. Is that here? Madan is online? No. Madan Sharma, Indian Institute of Technology, Delhi in India. Is that not here? I think so. We pass to next one. Dr. Mikhail Bozovero. I am so sorry. From Moscow State University, Chemical Department in Russia. Trifluoroacetan complex compound with different dimensions based on magnetic cations, structure, and expected properties, right? If you want, if you can use this.
Hello, I'm Mikhail, and I think it was very bad to look it. And then I told you about in words, and if you're interested in my film, you can see it in the basement hall. Okay. Okay, thank you. My objects is three-D metal consisted anions, and we do the. Can you scroll some? Yeah, what? This is the main object of my work. It is anionic structure of 3D metal. It is maybe interesting for physics because there are if the metal have antiferromagnetic ordering, the frustrated system at low temperatures. And my talk about more about chemistry or physics because we only start the measurements. But it may be also interesting for someone. In the first part of our work, we try to make anionic structure when anions so far each other, and in the right column we have the oldest structure, and left column are obtained, and we obtain series of 6 compound, and the distance between anionic fragments we increase by the synthesis condition from up to 13 angstrom, and then we then exchange interaction between anionic fragments where exclude. And I want to talk that if maybe you can scroll some up for this picture. It is maybe to name this van der Waals materials, because in 2 dimensionals the chain have large of hydrophobic groups which exclude interactions between the chains. And the second part of my work, it is the right part of poster. We try to connect the anionic fragment by the number of organic bridging molecules. For example, dioxane and pyrazine, and see may they anionic triangles interact between these molecules, and then we obtained 2 cobaltum compounds, this and this one, with the target structure. And for this we now have literally 2 days ago I have text message from my supervisor that this compound is paramagnetic, and because we do not add a plot of this poster, but for nickel maybe antiferromagnetic ordering, because there are some paper in this. There are. I think that's all. If someone interested, I can try answer the question later. Thank you for your attention.
Thank you very much about your information. You're Mikhail Buzovara. Here you are. Thank you very much. And the next speaker is Andrei Shilov from Moscow State University, Chemical Department in Russia. He will talk about the new superconductor structure type. Here you
are. Thank you very much. My short talk today will be as an extension for Igor Morozov lecture that was this Wednesday. So in our work we tried to get new layered bismuthides, and we've discovered a new superconductor in barium gold 2 antimony 2 structure type, and also we found that probably, can you scroll a bit down please? Okay. That this structure type can be described in literature somewhere wrong. We were able to refine its space group and also found a disordering in one of the layers in the structure, which wasn't reported before us. So we obtained our crystals with a pretty standard cell flux technique, which can be found everywhere. We just used a simple alumina crucible, which was sealed in niobium tube, tube, and later this tube was sealed in a quartz sample to prevent it from oxidation in a muffle furnace. So we were able also to measure magnetic susceptibility, which can be found on this plot. We found that we have a superconductive phase change at about 5 degrees Kelvins. So later we tried to get a clean resistivity plot, but at the moment we performed these measurements. We had to use conductive glue to make contacts that was attached to the crystal, and unfortunately it reacted with our crystals. There is interesting that we despite of this fact, we were able to identify all 3 phases. And interesting there is that 2 phases that were formed during the degradation process is superconductors too as well. So and both of them can be achieved during simple synthesis. As example, barium bismuth superconductor can be achieved only at high pressures like 4 gigapascals, and gold 2 bismuth can be formed only during low temperature synthesis below 300 Celsius. So in the future we wanted to measure the resistivity more carefully using indium contacts exclusively to avoid any degradation, and there will be interesting to measure more transport data like an Hall effect, and probably use some DFT calculations to because the conductive layers in this structure is bismuth gold layers, and bismuth and gold, both of them, they have a huge spin orbit coupling effects, and it will be interesting to look into interplay of these effects and superconductor properties. I think that's all.
Thank you very much. Andrei Shro. Thank you very much.
Thank you.
Yes. Yeah. The next speaker is Stefania Pizzini, CNRS Institut and in France. Is that here? Online? Nothing. So Stefania Pizzini is not here, I think. So the first session is finished. The next session about van der Waals materials. So on that session, the first, second speaker is Christos Pomorsky, Dr. Pomorsky. He will talk about, you will see because the long sentence. Erilog simulation. Is it? Yeah.
There is some, perhaps one can magnify those 2 plots which are here. So and then next stage there is quantization of equations of motion that can be done in 2 different ways. Of course, very old scheme is Bohr-Sommerfeld quantization scheme, so the system have integer value of net angular momentum. And more a kind of deeper way is by introducing two particles interacting perturbatively in Schrödinger formalism. And also it can be done in tight binding model. So could you please magnify maybe those two plots just to see, because probably visibility. So our target is to implement this simple simulation to hardware description language in Verilog, and so one can construct the controller, hardware controller of a nanorings that can work in an effective way. So that's it. Okay. So this is yeah. So that's it.
Okay. The next one is also your presentation.
Yeah. So.
It's about modeling classical statistical and function from a game of life.
Yeah. So could you make it full zoom, please? Full screen mode. Okay. So the interest is basically that right now you have transition from classical games to quantum games that can be run on the quantum computers and expressed by quantum hardware. So the starting point is well-known classical Conway game of life. So there's 3 rules. If a dead cell has exactly 3 neighbors, it comes alive into the next cycle. Another rule is if a living cell has 2 or 3 neighbors, it survives in the next cycle, next time moment. And if cell has a different number of neighbors than mentioned above, it is going to vanish or be dead in next cycle. So this is deterministic Conway game of life that can be expressed on 2-dimensional lattice, right? So then can we move a little bit downward so I can see there's another plot. Yeah, so can you magnify those two, please? Yeah, so then we can perturb the rules of deterministic Conway game of life by introducing the stochastic rules for transition. So transition, there were rules that were described above, are with certain probabilities. And then we can come using 2 different measures of entropy that, for example, if there are fluctuating barriers, one can witness the saturation of entropy with certain level of noise. And this is like thermodynamics law, but here the mass preservation of this is not conserved. So that's kind of characteristic for that. So this is like expression of a classical stochastic game of life. And then, of course, that first thing that comes into intuition, if you have 2 different reservoirs, you can have perturbative interaction if you introduce some small holes when cells can go through this cellular automata. And then, of course, you can use the well-known methodology of statistical physics, classical statistical physics, so you can define entropy, so system maximizes entropy. And then, of course, you can define the notion of temperature by ds over dE over ds. But then you need to define the notion of energy. And so how we are going to do it? Okay, before that, we can shift into a kind of continuous existence of life's vividity between like 0 and 1, right? So there is a kind of obvious analogy of quantum mechanics that we can somehow assign the 2-dimensional wave function that is defined on this lattice. And could you go up to this? Yes. Excuse me. Could you go up to this? Yeah. Thanks. Can you magnify it a little bit? Yeah. So basically, we can describe these transitions from one state to another state by constructing artificially made Hamiltonian for the system. So the equations of motions are preserved as in quantum mechanics. And then there is some analogy to a single electron devices that can be expressed by tight binding model. This is localized energy on the left and right quantum dot and transfer the Hoping term. So basically one can define very Hamiltonian that has some non-locality behavior. So this is so it's like annihilation of state in one place and a creation of another place, and there is this dependence of the term which depends on the neighborhood. And can we go down? Yeah. So then could you magnify this, please? Yeah. So basically here we also deal with anomalous features of Hamiltonian and non-harmonicity features, which can assign for dissipation, which is a good thing, because the dissipation is like non-conservation of mass or normalization of a wave function. So we can describe starts to becomes alive or that dies out. So this is like expressed by an imaginary part of eigenenergy in a way. So that's this direction towards quantum game of life. There's also a continuous version of that is not yet presented here, but we are working on that. So having this notion of energy introduced by such type of Hamiltonian, we can also define temperature in our convex game of life, and then we can broaden this concept. Thank you.
I will give you one more paper. Thank you very much. And next speaker is Igor Morozov from Russia. Your colleague, I think. That's okay. Oh, your supervisor is not here, but you are here. Good. So this session is finished. The next session, only one speaker we will talk. Vivek Kalkani, graduate student from USA. Is that here? Not here. The next speaker in the next session, Nadim Kaiser. Am I right? Kaiser. Nedim Kaiser. 2 and 3D dimension, 3D materials based sketchable and flexible electronic in the perspective of biomedical applications. Here you are.
Hello, my name is Nadim Kaiser. Thank you for giving me this opportunity. So I will talk about how we can use 2D and 3D materials for working now. Hello. Okay. So I will talk about how we can use 2D and 3D materials to get a better performing stretchable and flexible electronics in the perspective of biomedical applications. So I have a lot of checks to understand how it really affects all these things. So I will go briefly on 2-3 different perspectives. So number one, for example, we will take copper as a material, and then how this copper-based microfluidic actuator can help for our daily applications. So as an introduction, the stretchable and flexible electronics are the devices which are actually, you can stretch them and flex them or bend them, and there will be no difference or any effect on their performance. Like your electronic gadgets or wearable watches or all those electronic devices. So I do study their design and mechanics to improve the performance of those devices. So let's see this figure. So in this figure you can see there are a square shape. So that's called island. So that island has electronic components. So you can implode those components on those islands, and there are a few like stretchable interconnects. So using this specialized design, you can stretch your electronic device. Okay. So for this case, I use copper, and we developed a microfluidic actuator. Okay, can you go down, please? Yeah. So you can see I have used a copper-based microheater. Okay, and on this heater we spin-coated polymer that is expandable. So when you turn on electrical signal, so it will expand here, and it will actually let or allow pass through a fluid. So that will like a electronic pump or electronic switch or something. So we call it microfluidic actuator. So based on copper. Another example, can you go up please? Yeah, here. So another example is using a CNT, carbon nanotubes. So I developed this point of care real-time monitoring human muscle swelling. So in this patch, using the CNT, so it's actually a piezoresistive sensor. So you can implode this sensor on your this chin part, okay? So if there is a mumps or any infection, so you will have a physical expansion. So this patch can give you the, or track the physical expansion of your muscle, okay? And the most, I mean, the remarkable thing is we can track on phone. So your doctor can just see the swelling pattern over the time and can decide beforehand. Okay, so third example, this is, you can see here, like we tested on, you know, like dummy, and then we can see change in resistance, and it has very repeatable, you know, all the performance. And this is the function of muscle motion. So these sensors can also be used to detect the human motion for security purpose or all these things. Third one is graphidine-based on-skin sensor. So this sensor also was developed to track different pressures and different functions, pressure, temperature, all those things were embedded into one single patch. Okay, so this work also, this is just accepted into ACS Nano. So that's it. Just I wanted to highlight how we can use 2D and 3D different materials to enhance the performance of stretchable or flexible electronics. Thank you very much.
I just opened. The next speaker in the next session, Sandeep Kumar, Indian Institute of Technology, Delhi in India. Is he or she here? Not here. So, the first speaker in the next session about advanced in quantum materials, Dr. Krzysztof Pomorski, Krakow University of Technology, Poland. Here you are.
Hello, everybody. Yeah, so it's my pleasure to describe my last poster. So this is about description of coupled field-induced Josephson junction in curved Ginzburg-Landau equation. So the idea is as follows. So we do have a superconducting nanowire. On the top we place ferromagnetic strip. We can place insulator in between. So quite obviously there is modulation of superconducting order parameter coming from the existence of ferromagnetic strip. We can also use external sources of vector potential that mimics behavior of ferromagnetic strip. And in such way there is certain defect in superconducting order parameter that is induced. So this is like field-induced Josephson junction. Well, here we have cases of straight lines, but we can deform lines, so that's why it can be curvy of any shape. And also we can introduce the polarizing current that is generating vector potential that affects superconducting order parameters. So this is the case of curved field-induced Josephson junction. It can be also expressed in 3 dimensions. Well, we also have two-dimensional versions of that, so we can have a network of Josephson junctions. We can place ferromagnetic or non-ferromagnetic strips, so we deal with unconventional Josephson junctions. And here, what is underlined in this poster, perhaps we can magnify this part, is that we express this by we go around one wire. Could you please magnify it, this part? Yeah. So because it's a little, yeah. So we have 3-dimensional Ginzburg-Landau equation, but these operators can be defined by S parameter. So effectively, 3-dimensional equation can be reduced to quasi 1-dimensional of this form, where the curvature is encoded in these functions. So can we go down, please? Go down, yeah. So we finally end up in such type of equation. So we have this F and Fs and the GS functions that encode the curvature of a system. So this term can be seen as part of dissipative term. However, we still can also think backward using analogy to vector potential. So we can have a imaginary and real component of artificial vector potential that is introduced by curvature of a cable. So anyway, having the curvature y equal ax square, we deal with such type of effective equation where alpha and beta field is dependent on x. And can we go maybe to this part? Excuse me, to this bottom part, the top, this part. Yeah, could you please magnify? Yeah. So yeah, we can have alpha coefficient. So we take a cable that is straight, it has alpha coefficient as given here, or has two defects like normal metal in between. So we can bend it, and then let's go a little bit downward. Excuse me. Yeah, go down. Yeah. So then we obtain we use relaxation algorithm that minimize free energy functional, and for those two cases we get distribution which is in red of superconducting order parameter. So it's a general methodology to describe an inductively coupled field-induced Josephson junctions, and that's still under the progress of development. Okay, thank you.
Here you are. You're welcome. Is that last? Yes, the next speaker is Dr. Mustafa Akdoğan from Bolu Abant İzzet Baysal University, Turkey. We'll talk about price, performance, benefit of induction heating of magnesium diboride iron wire production. Dr. Mustafa Akdoğan. I think he is not here.
Turkish company. You are seeing the pretties and meshes on the bottom. We have applied.
It's online. Mustafa gelsene oğlum şuraya bir. Yeah, Dr. Mustafa Akdoğan, you have a 5 seconds. If you are not here, I can shift the next one.
Hello everyone, I'm Mustafa Akdoğan from Bolu Abant İzzet Baysal University. I'm going to talk about price performance benefits of induction heating on iron sheeted MgB2 wire production. We are applying in-situ process on our wires. Actually, we bought our powders from Pavisium, which is Turkish company. You are seeing the pretties and meshes on the bottom. We have applied our mixture 3 hours ball milling and with a speed of 300 RPM. We have also applied drawing to our wires to reach the final diameter. At the beginning, our iron sheet outer diameter was 12 millimeter and inner diameter was 9 millimeter. You are seeing the drawing machine in our laboratory and groove rolling machine. These are the dies. Finally, we get 1 millimeter diameter of wires, and we closed each end with the mechanical press, and we have applied induction heating on these wires. Actually, we tried different temperatures, and finally we get the result from the 900 Celsius for 1 minute. And we have applied for technique on our samples cotton from the center of these induction heated wires. Here are the results of our samples. Left one is for 1.9 millimeter diameter and right one is for 1 millimeter diameter. You are seeing the resistant temperature behavior of our samples. Actually, the difference between them is the bottom broadening of the TC offset behaviors of the wires. So you are seeing broadening on the 1.9 millimeter diameters offset value. So this was expected actually, because we were thinking 1 minute may not be enough for the reaction of the MgB2. So you are seeing the differences between the diameters at the bottom. So 1 millimeter diameter transition is better than a 1.9 millimeter diameter. So as we mentioned inside the topic, if we apply heat treatment on our samples with a tube furnace, it may take 6 hours to reach this kind of behavior. But if we apply induction heating on our wires, actually it takes just only 1 minute, and power consumption nearly equal to 90 watts. So there are huge differences between them, and this will be beneficial for the industrial application. Thank you for your attention.
Thank you very much. The next speaker is Dr. Hakan Güngüneş. Yes. The next one is Çiğdem Dönmez Güngüneş. The last one is Dr. Alexey Pakhornchik. He's not here, so the game is over. Everything is finished. Thank you for all of you.